Sì, altri 2 minuti. Altro 1 minuto, 2 minuti, che stanno entrando le persone.
Possiamo farla parlare prima lui, no?
Sì, 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 e poi lei, proprio poi lei. Ok.
Good morning to everyone. Welcome. I am Giovanni Apollone. I am the scientific director of the Italian National Cancer Institute in Milano, and really thank you for your presence and participation at this very interesting meeting. Of course, the topic of the meeting, that is the role, value, added value, and implications in our clinical practice and our research of artificial intelligence, is very timing. There's a lot of discussion about its presence and its role in our today everyday life, and of course we need, because we are clinicians with some responsibility versus our patients, and we are researchers, we need to talk at scientific level of all the tools and programs that we are using already in our life, in our clinical practice, and of course in research. I think that the program is very interesting. It covers all the topic that are relevant. I've seen that there is a lot of very interesting lectures and I hope discussion about its application in clinical practice, in research, and also in the so-called real world, because the combination of artificial intelligence tools to real world data in order to produce real world evidence to complement what we obtain from clinical trials is, of course, very important. I welcome you, I thank you, I thank also, of course, Dottoressa Arcela Prelai, that has put together a very nice audience, I see, very nice faculty, and a very nice and interesting program. I take the opportunity to remind to Arcela and to tell you that Arcela recently has been appointed as coordinator of one of our 4 lines of research, and this is just the line that regards the utilization of innovation tools in the real world, and of course big data, database, data sharing, data integration, and artificial intelligence is one of the topics. So welcome, and have a good day.
Thank you to everyone for being here. I'm Filippo De Bro. I'm the Chief of Department of Medical Oncology and Hematology of this institute, and I'm very proud that you are here and that you are working together about this topic of artificial intelligence, because on my point of view as medical oncology, we must be aware that in the last 5 years has been approved more than 350 new indication or new drugs in oncology. So that means that FDA is approving roughly one new drug or new indication every week, which is going to complicate and to give us a lot of opportunity to treat those patients. Plus we have 1,000, I would say millions of pathways that we are analyzing as prognostic factor, predictive factors, and with all the omics that we can use because of the technology we have now. And so we need how to understand how to improve and also how to focus our research. So I hope that this approach is going to help us to focus our research, because if we're thinking that now from chemotherapy and hormonal treatment, we are moving toward ADC, antibody-drug conjugated, radioligand, combo of immunotherapy with TKI, and combo with all these things with probably chemotherapy and still radiotherapy. So we have a completely new world that is opening in the last, I would say, 10 years, but probably even less. That is going to give us the opportunity probably to obtain a really very good result treating cancer. But on the other side, we should probably focus a little bit more our research. And because of so many data, so many opportunity, we need to find the methodology to focus our research and even probably to divide ourselves in networks that are able to discover new things and to utilize in the best way the tools that we have that are available now. Which is not really easy because we are a customer, all us is a customer to work on his field of research and to publish, and there is all this progress, but essentially the cooperation sometimes is very difficult when there are so many opportunities to do. So I hope that with this kind of approach we can really finalize the possibility to have a priority, because now it's timing to obtain priority and focus priority according to the willing and the opportunity that we have as a researcher in different fields. And if we will be able to find a common sense on how to fight cancer, working on the metabolism, working on the body, working on the immune system, working on the characteristic of the tumor, but probably putting together all this information to find a common way when it's possible to increase the percentage of patients and that is going to be treated for cure, even when we are dealing with a metastatic disease, or even better, if we can increase the number of patients curable, because of course, even if the disease is diagnosed in an early stage, sometimes we never obtain 100% of cure rate, and even it's rare for few diseases we obtain more than 60-70% of cure rate, which is not satisfactory this time, on my point of view. So I hope that this day of thinking, because according to the program there are so many interesting topics that are going to be discussed, is going to be helpful for us to network together and to focus our research. So I thank you very much for being here.
Thank you. So good morning, everyone, and thank you to Professor Apollone and Professor Debro for their introduction. I'm very happy, I can say, and honored. So to have all of you here in this room, and also the people connected remotely, and also for all this outstanding faculty and all the network that we have created these years, since I really think that this will be a whole long day, so we have to start very soon. Hopefully also an exciting day, so I'm really counting on every one of you to have your thoughts and also to stimulate discussion today. But we have plenty of coffee, so okay. So I think that we can start with the first section, and I'm very happy to invite my two co-chairs for this first section. So I will invite Vanya Miskovic. She is a bioengineering working with us at Istituto Tumori. She's a postdoc and also working with Politecnico di Milano. Together with me, she's involved from more than 1 year now in many projects. And to the other hand, I have Laura Mazzeo. She's a medical oncologist working at thoracic unit at Istituto Nazionale di Tumori. And she also is one of our next generation oncologists. She started just now a PhD in bioengineering. So Vanya, please.
Good morning, everyone. Thank you, Ursula, for the introduction. I'm very glad to introduce our first speaker, my colleague, Francesco Trovò. He is Associate Professor in Politecnico di Milano, and he is part of Department of in Electronics, Computer Science, and Bioengineering. Today he will give us a short introduction about main AI methodologies, their future, how can they be applied to the real-world data.
Thank you. Thank you, Vanya, for the introductions. So, hi, everyone. I hope that this will be interesting. So, since I'm the first speaker, I will start with an introduction about AI. I'm from the computer science department, so I want to be sure that the definition is, let's say, widely acknowledged by everyone. And then I will present some of the most interesting application of AI we had in the real world. And finally, which are the challenges we are facing in the health sector. So let's start. Let's start with the a little bit of history. So when AI was born, it was born, I would say, as a definition in 1956 with this little guy, McCarthy and Minsky, which started with this, I would say, is similar to the summer school we have right now. And they started talking about agents which were able to solve automatically some task as a human would do. So here we are not talking about philosophy, we are not talking about developing androids or something like that. We would like to have some automatic tools which are able to solve a really complex task in an automatic way. Unfortunately, in the 80s, they start working on this kind of technique, but in the 80s, since there were no outstanding results, the hype about the AI was somehow decreasing, so the funding were cut, and we were in the so-called winter of AI. Luckily, in the next year, we started shifting completely the approach and starting to use those techniques, which are now called machine learning techniques. Here, the main difference is the fact that here we would like to introduce the data. So we want to try to infer from data some algorithms directly. So instead of trying to understand how a task would have been solved by a human, we would like to understand how data can help us in performing a specific task. This seems really similar to what IT guys are doing, but actually it is not, since the standard computer programming is when you know exactly which program you want to implement. So you have some data and you already have thought about the program and you produce a specific output. While in machine learning, the focus is on creating new programs, creating new algorithms, which are able to somehow understand the relationship between input and output data. I know that at some point somebody would have asked exactly which is the relationship between AI, machine learning, and probably deep learning. Well, they are one a subfield of the other. So AI is way more general than machine learning, and deep learning is just a set of techniques inside the machine learning field. If I had to give some percentage at the moment, probably machine learning is covering something like 80-90% of the AI field, but still there are some techniques which are not machine learning, but still in the artificial intelligence field. If we focus instead on machine learning, we have different typology of techniques which will be useful in different problems. So we have this called unsupervised learning technique, which are able to understand if there is some structure in the data, while the supervised learning techniques are the ones that are trying to approximate some input-output relationship between data. And finally, I would say the most recent research is mainly focused on reinforcement learning, and reinforcement learning are those techniques which are trying to prescribe a policy, so prescribe a strategy on how to act on a specific task. So far, I only provided you with some definition, so it seems that everything is somehow related to the academic, but it is not. So if we look at the application of AI in the real world, we have several fields where it has already been used and it already has been applied in order to improve the capability of the field. And in the space here, I just listed some of the most interesting field where it has already been used, for instance, in the IoT, in the agriculture, retail, security, and finance. Clearly, here, depending on which kind of field we are looking at, we need to somehow be aware of the fact that AI has also some limitation. For instance, in the field of finance, we need to have techniques which are able to understand if the final results is somehow trustworthy from the user point of view, and also from the institution which is providing these services, and also provide some fairness. So we cannot assign a risk score to a person only by basing on the gender, for instance. So we need to be aware of this fact. And here the EU community is trying to work on this topic by drawing some guideline on ethics and AI. There has been also some report telling exactly how much the AI is pervasive in our world, and here there has been listed around 400 applications of AI in different fields. On the left, you can see a heat map where we have the different technique on the column and the different fields on the rows, and it's telling us how much that technique has been used in that specific field. I highlighted the pharmaceutical and medical products, and here you can see that the distribution is almost similar to the other fields. In particular, on the rightmost part, we have the traditional supervised learning technique, while on the leftmost part of the table, we have the reinforcement learning and the most advanced technique. And as you can see, the classical one has been used way more than the new one. The same has also been, this kind of scouting has also been done by the EU. In particular, they wanted to understand exactly what might be the advancement in terms economically, I would say here, by applying the artificial intelligence technique to different fields. So they identified three crucial sectors: industrial IoT, future mobility, and smart health. And they estimated that in the next year, that would, by using the AI, we would have an increase in terms of economic gain of the hundreds of billions. And again, here they also try to understand exactly which are the causes for which this AI tool hasn't been applied yet, and which might be the action in order to provide a best way of using these techniques. So let's switch. Okay, so far I didn't tell you exactly what AI might do specifically. Let's go through some examples. So let's start with a really, I would say, silly example, in the sense that we would like to have an automatic agent which is able to play video games, okay? So it's like a kid who wants to try to beat the record in standard or in the classical video game field. Here, by using deep reinforcement learning, so a combination of deep learning and reinforcement learning, the researcher by, I think it was Google Brain, no, DeepMind at the time, they were able to provide some results on these video games, which were even better than the human would do. So on the left you have the performance, so the largest the bar, the largest the performance, and you have an horizontal line, which is when the computer was able to perform better than a human in that specific task. And as you can see here, most of the games have been beaten somehow by the machine. And nowadays, this is the first experiment. Nowadays, we were able to use more advanced technique in order to beat human in every game from this Atari game suite. Well, how it has been possible to achieve such a result? Well, with video game, you can play as many game as you want, and even if you fail, you can restart and you can create a huge data set, a huge amount of information without any hazard. Well, this cannot be directly translated also in the medical field, because here the games are somehow related to the patient, and clearly we cannot use patient as let's say lab rats. Okay, so the point here is that we cannot use directly this kind of technique unless we have a huge amount of data. The same has also been developed also with another really interesting game, which is the Go game. And in this case, the same researcher were able to beat the world champion. So again, this is just a proof of concept of the fact that artificial intelligence can perform something, can perform even better than a human in some specific task. Maybe you already heard about this example, the AlphaFold. So this is a way of simulating the structure of a protein just by looking at the chemical, formula, I would say. So they were able to understand exactly the angle and the position of each proteinic residues, and over a well-known data set of protein, they were able to have really good results. So more than 92.4% of the molecule were accurate enough, I would say. On the right part, you can see the difference between the results given by this AlphaFold example in blue and the real real experiment where they had the protein in green. So as you can see, they are quite similar in this case. Clearly, this is something which was already been outlined, the fact that we have a lot of new drugs, a lot of new products, and these kind of approaches are able to speed up the process of creating something new product. Let's go really fast on this example, because I think that you all know exactly what autonomous driving is. And well, in 2006, we thought it was just something academic, while here we have self-driving car nowadays, which are working. Here, the problem might be the fact that we are not sure about the responsibility of this kind of technique. So if we have an accident, who's responsible for this accident? The one who sold you a car, yourself, the one who developed the algorithm. And clearly this can be somehow translated also to robotic surgery, and we have exactly the same problems. As last, I know that this is somehow the elephant in the room. The last advancement is given by ChatGPT, so a software which is able to create some text. Here, clearly, it's no magic. It's just a statistical way of predicting the most probable word that would fit into a specific phrase. And clearly, this the advancement with respect to previous tools is that in this case, ChatGPT is also able to understand exactly, to have some feedback from the user and adapt with respect to the feedback. Here, clearly, it is really I would say, useful for generating tests for general purpose. We should be aware of the fact that there are this kind of effect called hallucination, so that there might be some text which are just created by just opposing different information, so creating something which is not real, I would say. So again, even in this case, we should use ChatGPT, but being aware of the fact that some of the information might not be true. So far, I presented some of the approaches which can be used in the medical field, and some other not. I would like to outline some of the points which are crucial for adopting all this technique or part of this technique in the medical field by using real-world data. So I identified 4 points which, in my opinion, are the most critical for applying easily this kind of task in the field. Let's start from the first one. Usually when we do machine learning, we do machine learning by using the data which has been already collected on previous clinical trial. But this clinical trial had a specific goal, and so the selection of the patient might be biased somehow on the fact that we had that specific goal. And machine learning would clearly learn with respect to that bias. So a way of mitigating this kind of problem might be to try to put together many clinical trials from different regions, for different purposes, and have a data set which is more robust with respect to this phenomenon. And clearly, the long-term solution would be instead to have a systematic registration of all the data we have from the patient. Clearly, still with some informed feedback from the user, but still having something which is not just for specific clinical trial, but for all the data we are collecting. Another problem is dealing with missing data. So sometimes when we have a clinical record of a patient, we have some data which has not been inserted, but also we have this called missing not a random data. So for instance, depending on how many exam has been performed to the patient, we might have some information which is completely missing from a specific patient. Or even we have the problem of sensor data. So if the patient has not completed the treatment, we do not have enough information to have a clear picture of the patient. Well, there are already some technique in the machine learning field which are able to mitigate this effect. For instance, the data imputation technique. But still, in my opinion, the next step would be to specifically craft new algorithms which are able to deal also with a large portion of missing data with our methods. The third one is the fact that we might have unbalanced classes. What I mean with unbalanced classes, for instance, when we have a treatment, we might have a common treatment and then very rare treatment. When we are trying to learn, clearly those treatment which has more sample will be favored in the machine learning methods. So the machine learning methods somehow will be biased toward these classes. Clearly, there are some way of dealing with this by reweighting the patient somehow, so trying to be more fair even to those classes which are outnumbered, I would say. But still, I think that there might be room also for improvement from a machine learning point of view by developing new algorithms. At last, and that's the most, I would say, critical point is the fact that we are dealing usually with a small number of samples. So even the largest clinical trial has order of magnitude less sample than the one used to develop the application I showed you before. So here the mitigation is to use appropriately selected models. So models that are simple enough that are capturing the information from the data, but they are not too biased towards the specific data set. And clearly, the long-term solution, again, is to systematically get the data and have large biobank, large data set in order to exploit those kind of data set in order to have the machine learning models more stable. So, well, that's what I wouldn't suggest to do. In conclusion, I would say that we are in the spring or summer of AI from an industrial point of view, in the sense that industry is starting to use a lot of AI technique in order to improve their performance, but this has not been passed directly to the medical field. So again, we need to improve the quantity and quality of data we are having in the medical field before starting use this technique. And clearly, the second step would be from, I would say, my side, so from the machine learning expert side, to develop specifically crafted algorithm in order to deal with health data, health-related data. I hope this was interesting and enlightening somehow. If you have questions, I think that we will have a session afterwards.
Yeah, so thank you, Francesco, very much for this very kind presentation. Thank you for highlighting already just from the first presentation, I mean, some of key messages that I'd like to give you today. So just to remind that we are going to do the discussion section at the end of all the presentations. And please remind the people that are remotely connected that they can do questions. Please do questions. And at the end of this presentation, we will do that. So I'm very happy to present the second speaker, which is another real next generation oncologist. He's Julian Vibert from Gustave Roussy. He's a medical oncologist, a resident doctor medical oncologist, and also a PhD in data science and computing. He's a very, very smart guy. And he's going to present, and so especially to involve us a bit with deep learning techniques based on images, but also on genomics, which is a very kind topic. So.
Thank you very much, Arcela, for the introduction and for the invitation to this great Congress. I'm very happy to be here in Milan. So I'm going to talk about deep learning models for imaging and genomics. So indeed, I'm a medical oncologist. I'm finishing my training in Gustave Roussy. I'll be working in the drug development department, and I have a PhD in systems biology, bioinformatics. So the object, I think, is to give you some elements for clinicians, I would say, so I won't go into the details of the mathematics, and also in the end give you an example of how we used in France AI during my PhD project for a tool that is now used in clinical practice. I will skip the first slides because, as you see, it was already detailed by my previous colleague with a great presentation. But of course we can come back to this if you want. I'll go directly to, let's go to applications to oncology. So I will begin with imaging, which is not necessarily my specialty. I know that we'll have great presentations after that, but it's really to give you some elements of history also and of how we can apply deep learning in oncology. So as you know, deep learning is a very powerful technique, and it's mainly used now in medicine for imaging. As soon as you have data that is complex, such as images, so you have a lot of specialties using images such as radiology, pathology, but also ophthalmology. And so a lot of these specialties have already tried to use and apply those tools. You see some examples here on the slide. I wanted to focus first on this paper that in fact is already 6 years old. It was the first paper in Nature describing a tool which was supposed to do classification of skin cancers and especially trying to distinguish between melanomas and non-melanomas. As you know, as clinicians and dermatologists, it's a very difficult question, and so this deep learning tool was supposed, after training on a lot of annotated images by dermatologists, to be able to discriminate between melanomas and non-melanomas. And what was really interesting, I didn't show it here, it was that of course its performance was very good, and as compared to highly trained dermatologists, it was very comparable and sometimes even better. So that was one of the first example of how AI could really do as good, I would say, or sometimes even better than clinicians, the object being, and that is the message that I will come back to, that we should work together with AI, I think, and not necessarily try to beat each other. Pathology, of course, is another specialty where you have lots of images and lots of training data that can be fed to deep learning algorithms. And that's what was done. I just put one example here because, well, it's also a French paper because it's an Okin, which is a startup. So you also have startups doing those kinds of works. And it was interesting because it not only tried to distinguish different mesothelioma histologies, but also could predict the prognosis of individual patients only based on their histologies. So it's all about having lots of data, very well annotated data, and then feeding it to a machine learning and deep learning algorithm that is then going to be able to give you an answer that is very, in fact, good. Radiomics will be another topic, but I will introduce it here because as soon as you have radiology images, but also for radiotherapy, where you look at images of scans, of TEP scans, you can try to analyze especially things like the texture, so the pixels around each lesion, and in fact, using deep learning on texture features, you can also try to predict things like response to treatment, prognosis, etc., etc. So that's really a field also that is really fashionable right now. This is a nice review, very lately published in Cell, that you can go and read because it recapitulates quite a lot of tools that have been used up to now in cancer research. So I will not necessarily focus on this. As you see, you have different tasks that can be used. So risk stratification, diagnosis, prognosis, treatment selection, whether it be radiology, pathology, or even detecting breast cancer from mammography, which is a really important task for us. Let's go to genomics and transcriptomics, which is more my area of expertise. Here it's also a kind of overview slide of what we can do with current machine learning tools, and especially deep learning tools, whether it be for diagnosis, prognosis, but of course trying to predict response to treatment or even monitoring treatment response. As you know, we have now tools like liquid biopsies that have a lot of molecular data that can be analyzed by machine learning, and so trying to have those insights that we can use for the clinical management of patients. You can see on the bottom of the slide some different machine learning models that we can use, especially for cancer genomics and transcriptomics. In fact, not all of them are deep learning. As you see, support vector machine, random forest, all of these are not. I will not detail all of them, but it's just to tell you that deep learning is not the only machine learning tool that you can use, especially in genomics and transcriptomics. As you know, the data here is, especially for transcriptomics that I know well and that I will detail afterwards, it's high dimensional because for each sample you can have up to 50,000 features, for example, in an RNA-seq experiment. And so having this high dimensional data fed into a machine learning or deep learning tool is really going to help us to analyze, but also to try to predict some clinical outcomes for our patients. I will introduce this paper because I think it was quite seminal in the field. So it's also a few years old now. It was published in Nature. So it's on central nervous system tumors. What's really interesting here, so you know that these are tumors that are very difficult to classify even for pathologists. The classification are modified every few years. And so they did in Heidelberg this work of profiling central nervous system tumors with DNA methylation chips, EPIC chips. So you have about 50K features for each sample. So this is supposed to be high dimensional data. And so they fed this into a machine learning algorithm. In fact, this one was not necessarily deep learning, but it's just to show you what we can do with machine learning. And so you see this representation in 2D, which is called a t-SNE. If you don't know about this, these are techniques like t-SNE UMAP that I will show you afterwards also, that are machine learning techniques that try to represent a high dimensional space in 2 dimensions so that it is visualizable by humans. And so in fact, having one point here, which is one tumor close to another one, is just a way of saying in transcriptomic space or here in DNA methylation space, these tumors are really similar. And so you see those groups of tumors that cluster together and that are supposed to be DNA methylation close. And so what was very interesting in this paper, so it's totally independent of pathology, but only with DNA methylation, you are able to recapitulate most of the pathologist classified central nervous tumors, even discover sometimes some new entities, not only on DNA methylation. And what was really interesting also, so using DNA methylation, you can then classify very accurately. So the kind of plot that you see on the top, if you're not familiar with this, it's called a confusion matrix. And it's a type of evaluation of machine learning tool where you have on one side the real annotated diagnosis here by pathologists, and on the other side, what is predicted by the computer. And if you see the diagonal, which is red, it means that basically just is very concordant with what is supposed to be the gold standard here. Of course, we can discuss about what exactly means gold standard here in those questions. What was really interesting on the bottom of the slide is for discrepant cases where AI and the pathologists were not concordant. They did additional testing to try to know exactly which of AI or the medical doctor was correct. And for 93% of cases, it was the computer diagnosis that was finally confirmed. So it's really interesting to see that sometimes we have, I think, really to be helped by AI, not necessarily replaced by them. Just a slide to say that if you're familiar with genomics, we like to think about gene regulatory networks, but also in other fields that you see on the right for protein interactions, but also drug discovery, where we try to predict drug targets. We can use, of course, deep learning also when we have a lot of data that we can feed to neural networks, such as this one, which is a graph neural network, which is quite adapted to those networks. We can also predict some very important outcomes for our patients. You can see this on the latest review, but just a kind of overview slide of all the tools that here are already regulatory approved, at least by the FDA. So you have some tools that can be used right now, at least they are approved by FDA. And now I will focus on this use case because I think it's interesting as clinicians to think about what we can do right now using AI for our patients. And this was a nice example during my PhD 3 years ago when we used AI for really from a clinical case. So I was working in Institut Curie in Paris, and we received this 30-year-old male patient in a clinic. He had very rapid degradation of health status. You see his TEP scanner on the right with diffuse, especially bone lesions, but also an abdominal mass that you see here on the PET scan. And so, in fact, he was addressed to Institut Curie, where we are reference center for sarcoma, saying, well, probably it's bone sarcoma, we don't know exactly. He had done already 2 reference centers in Paris. And so in Curie, our pathologists are very specialized. They say, no, it's not bone sarcoma, it's carcinoma, but you just can't classify it. So it's unclassified carcinoma. Of course, you know this entity of carcinoma of unknown primary, which is in fact quite you have 2 to 3% of patients where you don't discover the primary when you have diffuse lesions. And so when you propose treatment is very unspecific chemotherapy. We were very unsatisfied about discussing in the tumor board about doing FOLFIRINOX as treating as a pancreatic cancer for this very aggressive cancer. And so we said, but here in Curie, we do RNA-seq for all our patients with sarcoma. So let's just do it and try to see if RNA-seq can help us about the diagnosis. So it's just cancer of unknown primary, you know this entity, CUPS. So even if you do pathology, additional markers, radiology, you don't find exactly which was the primary tissue where the tumor came from. And of course, you know that knowing this is probably very important to tailor the treatment. So could we identify the tissue of origin in this patient based on his transcriptomic profile, which is about 50,000 features? So to make a long story short, and in fact, we were very lucky because during my PhD, I had already at the time reprocessed all the TCGA data that you know is a really treasure trove of transcriptomic data. And so my objective here that we did in 2 weeks was like, okay, we are going to do RNA-seq, and then we're going to try to use machine learning to predict the tissue of origin based on reference data, which is transcriptomic data. How did we choose this model that I show you here, which is a model that is supposed to be a deep learning model? It's called the variational autoencoder. It's quite popular in the latest years, but at the time it was not so. What was interesting for me when I browsed through the literature is that, so it uses 2 neural networks, and I won't go into the details, but its objective is really to have high dimensional data that you want to make sense of, and it's going to encode this into a kind of optimal low dimensional representation that will be more amenable to interpretation, visualization, or classification for us clinicians. So it's a mathematical operation where you're trying to compress all the high dimensional data into a set of low dimensional features. And it does this very well, and after that you can do a classification or also generative sampling for other things. What was very interesting for us, it was used for imaging data, of course, and what was very impressive is that for images, this kind of tool could extract some meaningful features from the data without having ever known anything about human faces, as you see here on the right, or as we discovered for transcriptomic data. So it extracts combinations of meaningful features, as you see for images. It could really extract vectors corresponding to color of the hair, to the gender, to the age, to the color of the skin. So really putting really showing its expertise to extract some meaningful features from high-dimensional data. So we were very impressed about this, and we said maybe we can use this tool to extract also biological features, which will be not only useful for classification, but also for interpretation, which is very important, as you know, for us clinicians and patients if we want to use these tools in clinical practice. So this is the kind of workflow that we used for this study. So this is a UMAP representation of the reference samples that I used for the training of the algorithm. So this is based on TCGA, as you all know, about 10,000 RNA-seq samples of about 30 cancer types. But also we chose to introduce some normal tissue samples so that the algorithm is not biased by tissue samples, which would be mainly just normal tissue. This was the confusion matrix of the tool on the reference data, and you see that it's quite correct. I won't focus on the discrepant cases, but which make sense clinically, such as uterine carcinosarcoma, which is confused sometimes with uterine corpus endometrium carcinoma. So we did this very quickly, of course, because the patient was not in good shape, and it was not our hypothesis, but it was predicted as a kidney cancer. In fact, more papillary here. And so we were quite surprised, but not so when we asked our specialist in Gustave Roussy, Laurence Albiges. She reviewed the case. She said, well, in fact, it's very rare, but it fits well because, well, he has, of course, bone lesions, but you have in young patients sometimes some extra-renal kidney cancers. You don't see anything in the kidneys, but it's probably a remnant of the embryonic migration. You have some cells which remain in the abdomen and then become tumorous at one time. So we tried to, we said, okay, we're going to trust this tool and treat this patient not with FOLFIRINOX chemotherapy, but with immunotherapy and anti-angiogenic therapy, which is adapted to renal cancer, of course. He had a complete response, and that was probably the best argument for us to say that this was probably the right diagnosis, because FOLFIRINOX, as you know, does not work in renal cancer. We were very impressed by this result, and in fact, this patient is tumor-free 3 years after that. And so we decided to use this tool on all our CUP patients in Curie, but also other hospitals in Paris. So we don't have a lot of patients at the time when we published the paper, so 48 CUPs that were reclassified here, you see on the UMAP. In fact, to be honest, so this is the paper afterwards, but it's about 80% of cases that are quite well annotated. The other 20% are not even with this tool predicted to be a specific tumor type, and so we can discuss about this. What was very important for us in using and designing this tool was the kind of interpretability that we want to have as clinicians. I'm not saying this is very interpretable and very easy to interpret, but at least having 100 features, which is the number of low-dimensional features with this tool, allows us, as we know each of those features very well, to go into each sample and to see what was the feature that allowed this sample to be classified in this or this tumor type. So it's really important for us to interpret the result. So this is the paper. What's really interesting is that this tool was the impetus to include CUP as a national indication in our national genomic profiling program. It means that right now, since about 1 year, all the CUP patients in France have the money to have RNA-seq, and our tool is being used for every one of them. And of course, we have a national multidisciplinary tumor board, where this is not only the only information that we use, but it helps us in discussing the cases and tailoring the treatment for our patients with CUP. Of course, it makes a lot of noise in the mass media, so they are very excited in France of having this tool. I don't have a lot of time, but it's, you know, that CUP is really a big question in oncology, and we have other AI tools. I'm not saying ours, and probably if I had to redo it, I would do it differently. I would go quickly, but you have deep learning on genomics, whole genome sequencing here, but also on pathology slides. This was a Nature paper because I think this is really important. You don't do RNA-seq for each of your patients in each area of the world. So having a deep learning CUP classifier on pathology is really interesting. And finally, so I think that in medicine, a lot of questions can be answered with AI, deep learning. As soon as you have data, good enough data, genomics and transcriptomics are well suited, low number of samples, and I think really it's going to help us. It's not going to replace it. We should be better together. Of course, we should be also trying to have interpretable tools. You have to validate it in external centers, of course. And I would like to thank all of my colleagues, patients in Institut Curie, but also Institut Gustave Roussy, that made possible this work.
Thank you, Julian, for your inspiring presentation. So I want to present the next speaker. I'm very proud to present her, Professor Alessandra Pedrocchi. She works at Politecnico Milan, where she teaches neuroengineering and biomedical. And she's a founder of NearLab, a neuroengineering and medical robotics laboratory. So today she will talk about a hot topic, especially for clinicians, explainable AI. Thank you.
Thank you very much, Laura, for your presentation, very kind presentation, and I'm very honored to be here. Actually, first of all, for those three guys who are working in our lab and here active in the Instituto Cancer Institute, and we are very proud of this collaboration. So, despite the wonderful output that we can see from AI, we acknowledge that there is still something that lacks in having a real translation of AI to clinical practice. And I think that this point, this gap, deals with the problem of explainability and trustworthy. Next. Oh, sorry. Before starting, I need to disclose that I hold shares in two startups company active in exoskeleton, so not really a conflict of interest today. So my presentation will go through these steps. First, we will move from AI to explainable AI. Why? What are the reasons for moving to trustworthy AI? And then we'll give some hints about the methodologies to be used in order to do this explainability, and then see a few examples. I'm a biomedical engineering, and so my comments in the examples would be much more well commented by our colleagues. But anyway, let's start. So we are inside, we are living a digital healthcare revolution. And the ingredients that has brought us to this revolution are those four. So we have large clinical data set, so big data set of clinical information about the patients. But more than that, we are starting having a lot of unstructured data coming from wearable sensors, which are health related, so the Internet of Medical Things. And we have improved a lot the capability to store and to organize data into datasets. And so the data storage with proper security procedures are in place and make the data really available. And so these three elements are a service for applying artificial intelligence and specifically machine learning. So machine learning needs data. It's based on the availability of data. And actually data are to be effectively used by artificial intelligence and machine learning needs to have the famous 5 V's. The volume, the velocity, the value, the veracity, and the variety. In healthcare, it's quite easy to understand that we can cope with these requirements. I would like just to comment about the veracity. Veracity is the assurance of the quality, integrity, credibility, and accuracy of the data. Actually, I do not doubt that the medical data are of quality, of integrity, but we need them to be structured in a way that this quality is coded and readable in an automatic way. And this, it's a lot of work. We need to put a lot of effort in order to curate the data. And data curation means data are standardized, are interpretable by an automatic system, which doesn't know that this, it's quite good, it's 0 or 1. It needs to be coded. And this data curation, I think, is one of the main challenge for huge clinical hospital to make the real difference in the application of AI. So what is the revolution from AI to trustworthy AI? The first message is that AI has introduced by Francesco and also by Dr. Bilbert is based on a process of learning which leverage on a large data set and a large set of examples. And this allows the system, the automatic system, to learn a function. And this function is a possible recommendation to the clinicians. So the whole project is based on the accuracy in predicting the function on the training data set. Now, the user received the recommendation and has to decide, because the final decision making is still the user. But to take the decision, it comes out a lot of questions. How was this suggestion coming out? What is the logic of this suggestion, of this recommendation? And it's not just the statistics of a 99% of accuracy that makes the difference. So explainable AI is dealing with this problem. It's adding a layer between the machine learning and the user. And this layer is aiming at making the machine learning model interpretable and clear in its logic to the final user. And actually, when we started talking about the possibility of studying how machine learning is producing the output, the very accurate output, we have realized that some biases might be there. And this was a very important point which came out in the last years, that of course, if you train data, if you train a machine learning on a set of data, and in the set of the training data set, a part of the population is underserved, the accuracy you will achieve is not that high for the underserved population. And so that means that we might have a lot of discrimination depending on the construction of the training data set. And of course, in medicine, we want that the whole population benefits of the suggestion of the machine learning. And we need to be well aware of these possible biases. And of course, both the public but also the policymakers are very worrying about the ethical and the trustworthy aspects of AI. Just to show you, in 2019, the European Commission has published these ethic guidelines for trustworthy AI. And actually, they highlighted these main ingredients to make AI trustworthy. So first, we need diversity and non-discrimination and fairness. So the training data set needs to map the target population properly. Then we need transparency of the model, so explainability. Then we need accountability, so the possibility, the reporting of all the effects, the accounting of all the positive and negative story. And then we need to have the human agency. So we need that to acknowledge that the final decision is a human. And this human needs to be the agent and an oversight of the machine learning system. And then, of course, these ingredients goes with the accuracy and the privacy. Let's now move to how can we make an AI and machine learning system interpretable. Actually, there are two main approaches. On the one side, and every time we can use transparent models. A transparent models is what Francesco was calling traditional algorithms, where you have a sequence of rules, a sequence of pathway, a sequential order of the logic of the algorithm, which you can strictly follow to understand what the algorithm is doing. So you can look inside the model and see what the model is doing with your data. However, for very complex data set, where nonlinearity, time variancy, where a lot of more, let's say, complex and integrated data are present, the use of transparent model often fails. And while neural networks and machine learning models can achieve a higher accuracy. So we want, of course, a better accuracy, but then we need to associate to our black box model. So now it's no more transparent, it's black box. We need to associate to our black box model an explanation system. And we call this as a post-hoc explanation, because the model is trained on the data using a black box model. Once the model has been trained, you can open it and look inside of it. And there are, of course, multiple approaches in order to read inside a black box model. For example, we want to see how much each single feature, each element in the input is relevant to producing the output of the model. Or, for example, we want to work on a local explanation. Local explanation means that when an input has an output like this patient is a responder, then you can move the data of that patient and see when this noise on the data switch the output of the network from responder to non-responder, to understand how the different data are acting inside the model. And it's a local explanation because it's around some examples, some specific instances. Or for example, you can have model simplification. So you can reduce the number of features and understand how much the accuracy is reduced. And so this way you go back and understand the impact of the different features. Now, let's move to just two examples where I would like, again, I'm a biomedical engineer, and so my comments on the specific medical oncology output might be better corrected by them. And if it is the case, please do it. So, okay, first, we are facing a huge explosion of papers, of research, where the problem of explainability and interpretability, trustworthy machine learning is applied to medical oncology. So this is an example of real-world data, 480 patients with real-world data, so no radiomics and no genomics, and we used multiple different algorithms, multiple different feature extraction. So we played with the data and with different machine learning approaches. Now, let's look. The best is that on the output, which is the overall survival at 6 months, we can predict with 83% accuracy on the test set, so not on the training data, but on new data, we can predict whether a patient is likely to survive after 6 months or not. 83% accuracy. I was told that it's quite a good result. Now, and this way you put your data of the patient and you got, yes, overall survival class 1 responder, no responder. But then you don't know how can I trust this information, this output? And so we worked with a feature relevance methodology. And here you can see that this algorithm is applied over, so post-hoc, over the machine learning, and it ranks the features for importance. So the most important feature for the algorithm to give the prediction are the performance status, the NLR, the ANC, the TNMIO, and so on. So this is the most important. And then for each feature, each single dot is one patient of the training set. And actually, you can see that the right side of this graphs indicated the good responders is moved to the class 1 good responders patients. And we can see that good respondents are having very low performance status, which means that they're in a good shape. And these values so low, so now we are moving to the colors. So the blue is a performance status lows is associated to the right side of the graphs, so to responder class. And now you can play and say, okay, I have 2 patients. The yellow patient is given as a good responders, and I can put the yellow patient inside this graph and see, yes, it's a good responder because there is this data, this data, this data. So his data are inside this graph, located in a specific position, and makes a lot of detailed suggestion on how the decision was taken by the algorithm, and then the whole information, the reason as well as the final decision, are provided to the clinicians to take the decision, the final one. And this second application is about radiomics. So we have mammographic images, and there is a training algorithm that predicts the probability of malignancy. So gives a probability of malignancy and then predict whether the lesion is benign or not. Of course, this works like a crystal ball. You feed the algorithm with your image and you got a wonderful answer. Then you can try to understand how this answer is built. And for example, there is this level of explainability which tells you, yes, the probability of malignancy is low, the prediction is benign, and actually these are the pixels of the images which has been mostly important in order to take this decision. And this is already a good level of understandability with respect to the first one, the crystal ball. But now we can go even deeper. So inside the lesion, there are two areas recognized by the algorithm. One has indistinct margins, and so it's increasing the risk of malignancy, while the second one, which is bigger, is very circumscribed margins, and so it reduces the malignancy. So overall, the probability of malignancy is low and the prediction is benign. And it's immediate to understand that for a clinician to have this kind of information is totally different from the very first crystal ball approaches. So to conclude, I think that trustworthy AI is essential to give us informative relationships between the input features and the predicted outcome. This is essential to explain what the modeling is doing, to getting clinicians and patients buy-in, so really involved and secured by these approaches, and also to diagnose potential problems in the algorithms. And of course, the way the journey is long, I think we are addressing quite well understandability. We still have a lot of work in putting together the information from the algorithm and the clinical expertise. And this is my final message, I think that we need a new transdisciplinary experts, oncologists, data scientists. And those three girls are examples of the attempt we are doing in this direction. So thank you very much. We take the question now. Okay.
Thank you, Alessandra, for your presentation and for highlighting the need for a new generation of data scientists and oncologists. I would just like to invite here Professor Trovò and Dr. Vibert here so we can open the question section. And I would just like to remind the audience that is following online that they can ask questions on the platform, and we will read their questions.
There is any question from the audience? Yeah.
Pronto? Hello? Yes, I'm Mattia Boeri. Thank you for the great presentations. I have questions, especially for the two non-clinician guys. You came from university. You never work in the health system or in the oncology field. So when you first came in our institution and start collaborating with us, how were the data you find and the data set we
The director is
collect?
done.
No, because training is essential. We learned that training is essential. So if we were able to use already collected data, we have more data that you can use to train your algorithm. But if we have to start to collect the data you can use, it's a different.
Yes, it works. Yes. So that's an embarrassing question, actually. No, it's not true. I mean, what we have here, it's an impressive amount of data. Impressive. And very well collected. What we have been working for 1 year before being able to apply automatic machine learning algorithm was all about the standardization of the data and the curation of the data set, which is not immediately. And I mean, for sure, when you work on retrospective data, you need to check each single data and to standardize it, give rules, work with clinicians. And this is a real side-by-side work with clinicians, biologists, with clinicians, let's say, in general. Of course, I think that this huge effort has also produced an empowerment of the clinicians in order to try to feed as much as possible the database already with clear and standardized data, which is, I think, a gatekeeper for prospective studies. So data are wonderful, are a lot, are very well collected, but still needs a lot of curation. Especially because most of the data are kind of meta, unstructured data where the doctor might say, writing comments or giving sentences where, of course, one colleague doesn't understand immediately, but for an algorithm, this immediately doesn't apply. And so it's there is a passage there.
If I may add just a detail, I would say that the data which are already in place are usually collected for a specific purpose. So sometimes the purpose of the clinician is not exactly in line with the purpose of what a machine learning expert would do. So I think that they are useful, they should be exploited as much as possible, but we should also look forward and try to understand exactly which data or which metadata we might add in order to have a proper data set to be used for machine learning purposes directly, I would say.
So, thank you. There is another question from the audience. Okay.
Yes, thank you again for the presentations. My question is for Professor Trovò. Since you mentioned basically one of I'm also a researcher, one of our main issues when we analyze clinical data, that is the unbalanced data set. So the labels that we are going to analyze are usually not well balanced. And I want to ask you if you can briefly mention what is for you one of the best approach or one of your most used approach when you try to solve some clinical issues like clinical outcomes, response, and so on.
Do you want the trick of on how to solve the problem or how to solve the problem really? Okay, I think that there might be two different approaches. The first one is to properly define or to redefine your output. So for instance, Professor Pedrocchi outlined the fact that we studied a case in which we were looking at overall survival below or above 6 months. So if you set directly the number of months which is corresponding to the median, you will have balanced classes. But that's again a trick. That might be something which is not useful for clinical practice, but that might solve the problem. The other possibility is to use directly machine learning techniques which are able to cope with this problem. For instance, one of the way of dealing with unbalanced data is to replicate the under number class and have a final dataset which is a little bit more balanced. Or the other possibility is to have specific machine learning approaches which will weight differently the different data. So you will have that the focus of the machine learning will switch from the most probable class to have a more balanced proportion to every class. But again, these are, I would say, standard technique. We are working on that.
Yeah, just another question. But for the second approach, you will use the let's say you oversample just for the feature selection part, or even to define your final model?
Okay, that's kind of a specific question, so it really depends. As an engineer, I would always answer, it would really depend on the specific case. Even the fact of oversampling the low number class or undersampling the largest class would be two opposite choice. Which one might be the best one? It really depends on the application, I would say.
Thank you. Yeah, so just 1 second, Luca, like before, because we have also some people connected, at least 130 people that are connected, so I'd like to thank you them. And we have one question from for Vibert, so from Irena Zali. So once you have new RNA-seq data, do you retrain your ML model?
So it's a very good question, and in fact that was what we did in the beginning, but it was quite computationally intensive, and after that it was just a trick of redesigning the model so that we could feed directly a new sample into the encoder and then just get the encodings and map it on the UMAP. But yes, indeed, that was one of the processes that we had during the work. So first we just retrained every time because we thought that could be better. But in fact, we compared the two strategies, and of course, computationally, it's much more efficient to not retrain every time.
Okay, thank you. Luca. Yeah, thank you.
Thank you. I'm Eugenio Santoro from Mario Negri Institute for Pharmacological Research. A question for all of you. One of the factors limiting the use of artificial system, for example, in the diagnosis field, is that there is a lack of prospective studies, and in particular of randomized clinical trials. Most of the studies are retrospective studies. What do you think about it?
Yes, I can begin. Of course, the gold standard would be to evaluate prospectively all those tools. Usually it's probably due to all the clinical constraints. For example, the tool that we used here in Curie for cup classification, we tried to evaluate it prospectively, but in fact the gold standard would be to do like a prospective randomized trial where we would use the classifier in one group and not the other one. Here in our specific case, but in many other cases, it's really the clinical limits, the constraints. We don't have a lot of patients. But I agree, and in fact that's one of the things that we are looking into, is really to evaluate this tool, and I agree with you that this should be the gold standard, and we should all strive to go around those clinical limits to evaluate those tools properly.
Just a comment. I think we should not pose in contrast the two approaches, because of course the strong output will come out from prospective studies. But at the same time, I think that the whole data we have already is a treasure. So we should try to benefit the most also of the information which is already there. And maybe the best way to, let's say, conceive in a unique framework these two aspects is to work on retrospective study in order to give clear hypotheses in designing prospective study, which are then the final real output. But I mean, it's not contrasting one with each other.
Okay, fine.
Thank you very much. Quick question for Julien Vibert. You know, our institution is involved in rare and very rare disease. The transcriptomic approach, unfortunately, dramatically fails. What are your suggestions to overcome this issue?
Thank you for the question. In fact, I didn't mention it, but my PhD, my expertise is in soft tissue sarcoma. And in fact, the tool that I used, initially I was working on a tool for transcriptomic classification of sarcomas, and especially for rare entities in sarcoma. And so we have a tool which is the cousin of this tool, which is running right now in Institut Curie internally to classify sarcomas based on transcriptomic data. And we have entities, of course, in sarcomas where we only had 3-4 cases with RNA-seq. And in fact, it depends on the entity. You have some entities, I'm speaking about sarcoma, but with specific translocations, which have very specific transcriptomes. And even having only 3 or 4 cases is enough, in fact, to have a very well-defined group on the UMAP or even on the transcriptome profile. And having 3 or 4 cases in the database is enough, in fact, when you evaluate the performance of the algorithm on a new case of this rare entity to classify it. So I would say it depends really. The number, in fact, I agree, is usually a big limit, but when you have some entities which are really, really specific and different from all the other ones, in fact, our experience here in sarcoma is that it's not really a limit, at least when you have 3 or 4 cases.
If I may add just a comment, I would say that I totally agree. In the case you have a few number of data, usually in machine learning, what you do is you try to integrate the expert information into the system. So if you have some additional information coming from medical practice, you can start from that and then, let's say, switch a bit the information you have depending on the data. So the more the data you have, the more you will be following that information. Otherwise, you will stick with the standard medical expertise.
So I'm going to read a comment that has come from Pier Albino Colombo, which I think it's a really good message. So he said, I'd like especially to thank Professor Pedrocchi for emphasizing the importance of data sets. So I'd like to amplify this concept by adding the following thought. So data ownerships should be domain experts, so physicians and biologists, and only domain experts know how raw data has been generated. And domain experts should be able to transform and manage the flow knowledge to structured and queryable knowledge base. So they should be able to query the data set. And we can have a wonderful model, but garbage in and garbage out. Now, I really like this comment. So we have a last question because we can have, we want to save some minutes and go ahead with the second section. The last will come from Professor Mario Colombo.
The example of breast cancer benign versus malignant decision is quite risky, being the small part of the lesion could represent the part going to progress, having digest the capsule and collect malignant cells at one edge. Does exist a follow-up of an outcome post-AI-based decision already? It's not specified to who, so if someone would like
I
to...
think to Professor Pedro.
I'm totally incapable to comment on this.
That's why
I had to admit. I mean, it's a paper and I'm not a medical oncologist, so
one of our
please.
immunologists and experts. And so I really like to thank for the question. Yeah, I think there are still, it's debatable, I mean, but it's a good...
But still, the question, I think, comes from the explanation we are providing. Yeah. So the fact that you know that there are two different lesions with two different typology might lead the oncology to two different outcomes, even an outcome which is different from the one of the machine learning expert, the machine learning system. So having the explanation somehow triggered this question. So I think that, again, here we are demonstrating that explainable AI is something which we require.
Yes, actually, let me comment. I need sometimes some. I think it's true. We have triggered the reasoning of the clinicians, and the clinician is the one who takes a decision at the end. So he can disagree with the system, but has received additional information, like a second opinion, like a colleague who has triggered a more deep understanding, reflection about the patients. And that's the goal. We don't want the crystal ball. We don't want the clinician to just, okay, the algorithm, it says that, and I go. No, it's, the algorithm is intended to help the clinician, to give additional information to the clinician, to give but of course, the clinician at the end can disagree with the algorithm. That's not, I mean, that's possible, absolutely possible. So we do not have to defend the algorithm. We have to explain the algorithm so that the clinician leverage on additional information coming from that. It's not like the video games.
Yeah, since we have another minute, we are going to finish with another comment from, again, Pier Albino Colombo, which I think it's a very interesting comment, and we will touch it in different speech. So, yeah.
I would like to point out the risk of underestimate the power of ChatGPT, and more generally, the large language model and transformers. ChatGPT is not merely a text generator. That's why the fathers of AI are warning the world against the ethical risk of chatbots. Yesterday, Geoffrey Hinton, one of the fathers of AI, left Google. Do not underestimate ChatGPT or these models. Healthcare R&D institutes should have their own chatbots, like more general architectures, trained on domain-specific raw data sets, validated and managed by domain experts. The ethical risk to rely on cloud chatbots, trained and acknowledged, which is owned by others, is huge and it's real. That's why the warning for many AI experts.
I would say that I totally agree in the sense that as any tool, it should be used properly. So you should use ChatGPT for some task, and for some other, you should use your common sense and understand if the answer given by ChatGPT is somehow reasonable or not. I think that we are going through a process in which we are not trusting ChatGPT anymore. And so probably in the future, we will see some system that will also provide us with the source where ChatGPT is taking information. So we can even track the information path and understand if the sources are trustworthy or not. Still, I agree. I mean, I cannot disagree with Hinton. So I think that this might be still a warning.
Okay, so we are going to close this first section. I would like again to thank all the speakers and my co-chairs, and welcome the second section's moderators.
Okay, thank you very much, Ursula, for your introduction, your invitation. And let's start the second session about the rising of a new age in the artificial intelligence use in the imaging for oncology. And it's a pleasure for me to introduce the first speaker, James Dolezel. I hope to pronounce it correctly. I have the opportunity to collaborate with him in the People Project. James is a biologist who moved towards bioinformatician field 8 years ago, and is in charge of the University of Chicago. And today we will talk us about the use of AI in digital pathology.
Great, thank you for the introduction. It's really an honor to be here amongst such a wonderful panel of speakers. I really, it's just an honor to be speaking alongside all of you. So today I'm going to be introducing in more detail the topics of artificial intelligence as applied specifically to digital pathology. By the end of this talk, I hope to have expanded your appreciation of the incredible volume of data that's generated from digital pathology and some of the tools and methods we use to leverage artificial intelligence systems to augment clinical workflows. I have no disclosures. We're going to start with a quick introduction to digital pathology and what it means. We'll talk about some AI methods for digital pathology, understanding that many of you are clinicians, so I'm going to keep it high level. And then one of the takeaways that I want you to have as well from this talk is the need for open source software development to foster collaborations among groups so that we can work together to build these tools and advance research forward. Microscopy is one of the cornerstones of modern medicine. We use microscopy in the initial stages for cancer diagnosis for many of our patients. It informs the overall diagnosis. It can give estimates of risk and lots of other clinically actionable information. But there are many limitations with traditional light microscopy. First, you need a physical slide in hand when you're actually looking at it under the microscope. You need a human pathologist as well to look at the image and provide an interpretation. And as we all know, humans are subjective, and you may get different answers if you have different humans interpreting the same case. This is particularly relevant for rare tumors or cases where pathologists may only see 1 or 2 cases their entire life. High-resolution slide scanners have transformed the way that we acquire data from pathologic image samples. They can provide us with very large images that capture all of the information from a digital pathology slide as up to 80x magnification. Now, there is an enormous amount of information in this thumbnail of a slide that you're seeing, and I hope to expand your appreciation for just how much data is here. It turns out that digital pathology images actually have more in common with satellite images than other sorts of medical imaging modalities, such as radiology. So if the largest digital pathology slides were instead a satellite image with high enough resolution to clearly see the Madonnina perched on the Duomo, digital pathology slides would not only have enough spatial information to cover the entire city of Milan, the largest slides would have enough spatial information to span 10,000 square kilometers. And if you laid that slide on its side, it would span all the way from Milan to Geneva. This is one patient's pathology slide. It's an enormous amount of data that we're able to capture. And we can leverage this data for building robust artificial intelligence systems that augment but do not replace clinician workflows. We can build artificial intelligence systems to do diagnostics, to predict gene expression, predict mutations, and provide estimates of risk and even treatment response predictions. Ultimately, our goal is to take a pathologic sample, transform it through an AI model, and provide actionable clinical information. And some of my colleagues later today will be talking more about what some of those examples might be and some of the prospective trials that are underway to bring these to the clinic. In this session, I hope to talk a little bit more about the AI systems underneath the hood and to help you understand at a high level what's actually going on. In all cases, everything that you're seeing here can be implemented using our freely available open source software called SlideFlow. Because of the enormous size of these digital pathology images, you can't analyze them all at once. You have to segment the whole slide into smaller parts. These smaller parts are called image tiles. This segmentation happens at a pre-specified micron size, pre-specified pixels, and magnification. And on these smaller images, we can then do AI analysis. And there's lots of different types of models we might make. Some types of models might include classification, regression, segmentation, and image translation, although there are more. Classification models give us a categorical outcome prediction, such as tumor type, tumor subtype. Regression models give us a number. So if we're predicting hazard ratio, survival, gene expression, it can be one number or many numbers. Segmentation models outline cells, which allow us to do downstream analysis, such as cellular characteristics, cell size, nuclear density, spatial arrangement of the cells. Image translation allows us to take a source input image and transform the image into a related image. Research has shown that we can use this to take unstained slides and virtually stain them fairly accurately. When building AI systems from digital pathology, there are really three key sources of, that must be considered: the data, the model, and the method of evaluation. Once you've acquired these high-resolution digital pathology images, the images need to go through several steps before they're ready for AI analysis. The first step is tissue detection, where we're detecting the areas of cancer and background tissue and removing the white space. There's lots of different algorithms that we could use. For the engineers, Otsu's thresholding, Gaussian blur filtering could be used. There's lots of different potential algorithms. The next step is artifact removal. We want to remove the pen marks, the slide labels, any other potential sources of confounding, highly out of focus areas. This is really relevant for slides like this, where we almost have just as much pen mark as we do have other tumor tissue. Pen marks and artifacts can serve as confounders and can cause your model to perform really well in your training data set, but then when you apply it to the real world, the model fails. The next step is, once we have the areas of the cancer that we're interested in performing analysis on, we need to segment those areas up into those image tiles that I mentioned before. You do this at a specified magnification level and image size. The amount of tiles you get from a slide depends on that magnification level you're analyzing. So you might get as many as 40 or 50,000 tiles. You might get as little as 100. Next, stain normalization is popularly used to try to harmonize the different colors that you might get from different staining practices at different institutions. So maybe University of Chicago is very heavy-handed on the staining and INT is a little lighter on the staining. So samples taken from the two institutions might have different color. Stain normalization can help harmonize the different colors that we see in the samples and reduce batch effects. Finally, we need to compress this absolutely enormous amount of data into a form that's suitable for AI analysis. So when you're performing analysis on tens of thousands of slides from multi-institution repositories, that could be tens of terabytes of data. And so we need to compress it and store it in a format that's going to be suitable and digestible by these AI systems. Once we have data that's ready for AI analysis, we can build our AI models. So there's two primary considerations when we're building AI models. The first is the architecture, and the second is the training method. Most of these AI systems under the hood are neural networks, which I think we've mentioned a little bit previously. Neural networks have many different forms or architectures, and there's probably hundreds of architectures available. Different architectures are better suited to different tasks, and well-written software would allow you to swap out the architecture as needed. Here are a couple that you might have seen before previously. Once you have an architecture chosen, you need to train the model to be able to predict whatever your outcome is from your input images. Two considerations for training is the type of model that you're making, and then values that influence the training process called hyperparameters. And I'm going to give you an example of that in just a minute. I'm going to take a moment to take a closer look at classification models, as classification is a very popular use for AI and digital pathology. There are two commonly used approaches that I want to spend a little bit more time talking about. The first is tile-based models, and the second is multiple instance learning, or MIL models. Tile-based models were among the first to develop and are the easiest to understand. In tile-based models, we take all image tiles separately, and each image tile is seen by the AI model as an entirely separate entity. Each tile gets the label from the slide that it came from. So if a slide gave you 10,000 tiles, every tile would get the same label based on whatever the slide label was. So in this case, 0 is squamous cell carcinoma, 1 is an adenocarcinoma. We train the model on these images and these labels using values known as hyperparameters to guide the training process. Hyperparameters might be things like learning rate, weight decay, batch size. These are values that influence how the model learns and will affect how accurate the model is in the end and how fast the training goes. You don't know ahead of time what the best values are going to be. You just have to optimize, try out different values and see what works best. Once the model is trained, if you feed it new image tiles, you're going to get a separate prediction for each image tile. So this isn't really clinically actionable yet, because if I have 40,000 image tiles, I'm going to have 40,000 predictions. What do I do with that? So if you have a digital pathology slide, you take out all the image tiles, each image tile gets a separate prediction, and then tile-based models just average everything together. Now, the astute among you are probably thinking, wait, that doesn't seem like it would be good all the time. What if I have a heterogeneous tumor, or there's only a tiny focus of tumor and everything else is irrelevant? Enter multiple instance learning models. So multiple instance learning models, or MIL models, have advantages over tile-based models in that they can focus on areas that are important and ignore the areas that aren't. MIL models have two parts. They have an encoder part, or knowledge extraction, and a classifier that from that knowledge gives you a final prediction. The encoder takes information from the image tiles and transforms it into a distilled set of information. There's lots of different words we could use for this: knowledge, features, information. I'm visually showing it here as barcodes. For the mathematicians, this is just a vector. And for the clinicians, you can think of this as a distilled set of information like architecture characteristics, nuclear characteristics, staining characteristics, things like that. Every image tile gets converted into these knowledge features. And then when it's time to train the second part, the classifier sees all knowledge from a slide all at once and makes a single final prediction from everything from the slide all at once. When it makes that prediction, it can focus on areas that are important and ignore the areas that are unimportant. It learns what's important during training. You don't have to tell it what's important. It just learns it on its own. This provides it advantages when tumors are heterogeneous or when the outcomes are very small in the slide. Once we have our AI model trained, we need the last step that's critical is robust evaluation. And there's a couple of different steps that we need to take to evaluate this AI model before we can trust it. The first is we need to test our model on a held out test set. So models will always do well on your training data. That is a guarantee. You're going to get close to 100% accuracy. It's not meaningful. You have to test how the model does on data that it's never seen before once the training is finished. The type of metrics that you might use depend on the type of model that you're building. For categorical models, you might use metrics like these: area under receiver operator curve, or AUROC, average precision, accuracy, sensitivity, specificity, etc. If you're building a regression model, you might use R-squared. If you're building a Cox proportional hazard model, you might use concordance index. The next step is heat maps. So what do I mean by heat maps? We need to take some of the slides from the held out test set and generate predictions on every area of the slide and look at the areas of predictions. Sit down with a pathologist expert right next to you and navigate these slides. And we want to make sure that the areas that are being predicted according to our classes are consistent with our biological expectations, because we might find that it's predicting those pen marks to be associated with our class. And if that's the case, we need to say, hey, stop, I think there might be a confounder and our model's not trustworthy. The software that you're seeing here is our open source software that's available. The final step is explainability. So I don't have time to talk about all the different explainability methods that might be used, but explainability, as was introduced very nicely previously, is the process by which we improve our trust in the model. A common explainability use for digital pathology are called saliency maps. So these highlight the area of the image that are important to the diagnosis. We saw these applied for the mammography example earlier. And a new example that our lab has just published, well, is in the process of being accepted currently, is synthetic histology. So I'm going to give an example of this in just the next slide. Synthetic histology is a technique where we can have the model draw for us what it thinks a negative case looks like and what it thinks a positive case looks like. And we can look at those illustrations, and if those are consistent with our biological expectation, that reinforces that the model is learning something real and not learning something fake. It also provides a method for scientific discovery. If we're training models to predict gene expression or predict mutation analysis, we can use this teach-back method to have the model show us what does it think a mutated sample looks like. This is an example application in thyroid cancer. So in thyroid cancer, we train models to predict BRAF-like gene expression or RAS-like gene expression, and used this synthetic histology to draw us what a BRAF-like tumor looks like versus what a RAS-like tumor looks like. And you can see all sorts of changes that are happening that are subtle. Changes in the colloid, changes in the nuclei, changes in the arrangement of the follicles and how they become dilated. All of this is within biological expectations, and this same process can be used for scientific discovery. There's many different software tools that you could potentially use for building these AI models. You could use closed source software, which means that you don't actually know what's going on under the hood. You could pay for commercial software, or you can use open source software. What do I mean by open source? Software is open source if it has publicly available source code. That means you can go to some website and see what is the programming code used to make this software. And I'm going to argue that open source software is crucial for advancing AI research. And when you have the opportunity, you should always use open source software. Why? I've grouped the reasons into 5 different categories: complexity, modularity, transparency, reliability, and innovation. So for complexity, our open source software has over 50,000 lines of code and 25,000 lines of documentation. If you were to print that out, single space, 10-point font, Times New Roman, that would be over 1,300 pages. So this is an enormous amount of effort to make this software. And by providing it publicly available, other researchers don't need to reinvent the wheel when they want to do similar types of analyses. Our software is not a silver bullet. It's not going to work for everything. But if you're a researcher that's trying to do the same thing as us, use the software because it's already written. The next is modularity. So well-written open source software will allow you to add things without needing to reinvent the wheel and spend a lot of time on software development effort. Imagine you're reading the latest issue of Nature Biomedical Engineering, and one of the labs at Harvard, let's say, puts out a new stain normalization strategy that really improves and reduces institutional batch effects, and you want to try it out on your own data. Well-written modular software will allow you to add that into your software pipeline easily without requiring a lot of work. Whereas if you're writing your own homegrown software, it might take months of effort to get the APIs to work in a way that you can integrate that reliably into your code base. Next is transparency. So if you can look at the source code yourself, or engineers in your lab looking at the source code, it can help you understand and validate the underlying algorithms and methods that are being used. Sometimes these papers don't include enough information, and you walk away wondering, well, what actually did you do? What was the loss function? How did this actually work? If they have open source software, you can see it yourself and you can replicate it yourself. It fosters ideas for improvement. So maybe you read the source code and you think, I don't agree with the method that you used. Well, now you have an idea for research in the next paper. It also facilitates easier troubleshooting. So if things aren't working well, it allows you to pull up the source code and go through the debugging process and figure out what could be better. Reliability. So every point you see here has been a pain point for us. Bugs, issues, reasons why AI models don't work. Some of them took months to figure out, and some of them were very hard. AI systems are complex. They can be very subtle. AI models will overfit on things that your human eye can't see, and it makes it very challenging to train reliable models. If you use open source software that's been well vetted and used in many publications and other groups are using, it reduces the chance that you're going to fall into one of these potholes and be stuck spinning your wheels for months. And finally, innovation. So free and open source software can be used on low-cost devices. You can really expand your mind and think, how can I use freely available software to create low-cost devices that could be used for the developing world? Open source collaboration fosters novel ideas. If you're working with multiple groups all from the same code base, you might have ideas that together you can think of that you wouldn't be thinking of apart. And having accessible software increases researcher diversity. So if the code is easy to use, you can bring more people in the lab to work on things, and that increases the pool of talent, knowledge, and creativity that we can use to develop new systems. I don't have time to go into detail for all of these, but this is just a high-level, one-sentence snapshot of how we've used the same software in for 8 different research objectives. So we used this software in thyroid cancer to predict gene expression, which was clinically actionable information. We used this in non-small cell lung cancer to build a risk stratification tool for early stage lung cancer and predicting likelihood of relapse. We've used this in breast cancer to predict Oncotype DX, which is a risk stratification tool for guiding chemotherapy use in hormone-positive, HER2-negative breast cancer. We've used this in collaboration with Argonne National Laboratory to predict drug response in PDX models. We use this to develop a new uncertainty quantification technique, which I really wish we had more time to talk about today, to give deep learning models the ability to tell us how confident they are in their answers, in addition to giving us the answer itself. We use this to describe batch effects in large public repositories. We use this for the synthetic histology, which I showed you earlier, a new explainability technique to improve the understanding of AI models in digital pathology. And finally, we've used this to deploy on low-cost devices, building open source AI, fully AI, all-in-one devices that can predict HPV status in head and neck cancer and subtype lung cancer diagnosis using a $35 computer and fully 3D printed microscope parts. So in summary, digital pathology is data rich, provides excellent opportunities for artificial intelligence, but AI pathology pipelines are complex. But open source software development can increase accessibility of these complex methods and can accelerate AI research. So this is our source code. If you are interested, I encourage you, if you're doing this type of research in digital pathology, utilize the resource, join the community, and help us move forward. These are the software developers on our team. We have a collaboration between engineers, medical oncologists, and other researchers. Would not be possible without our really amazing team at University of Chicago. As we look to the future, it's imperative that we continue to support open source software development, because together we can do better than if we were working alone. Thank you.
Thank you very much, James, for your very interesting presentation. And let's keep the question for the discussion later.
Yeah, let's move on to the next speaker of the second session. It's a pleasure for me to introduce Raquel Perez Lopez from VHIO in Barcelona. Raquel is a radiologist and an expert in the field of quantitative imaging analysis and radiomics. And she's also a leader of the radiomics group in our institute. And now she's going to present us some radiomics application of AI for cancer research. Please, Raquel.
Thank you. Good morning, everyone, and thank you for the kind introduction. And I would like to also thank Arcela and the rest of the scientific committee for the invitation. It's a great pleasure for me to be here in front of this audience and the excellent panel of speakers that you managed to put together. So in the next few minutes, I'm going to try to explain a little bit about we and others have been working on regarding the application of AI towards developing new imaging biomarkers in cancer, ideally for improving the way we treat our cancer patients and improve cancer patients' outcome. So as you have seen this morning, AI is impacting every single aspect of our daily life and actually also research and medicine. But I must say that not all the scientific communities have embraced AI in the same way. And sometimes radiologists are a bit reluctant to accept the applications of these new tools. So these are my disclosures. So I think that in order to understand what are going to be the next steps in our field, it's a good idea to look back in time and have this broad overview of the story of radiology, since it was born in 1895 with the first plain film or X-ray performed by a physicist, a German physicist. And then a bunch of several revolutions have occurred in the history of radiology, mostly regarding software, but also, hardware, but also software advances, being able to acquire thousands of those X-rays in just a few seconds, or exploiting the spins of water molecules and acquiring nice MRI images, and also acquiring nice information about the metabolism of tissue with PET imaging. And the next big revolution came around 2000 when in the radiology department we stopped using analogical detectors and we digitalized all the images, and that, as you can imagine, opened a huge window of opportunity to store our data, to share our data, to integrate our data with other sources of information, and why not to apply new computational methods to the analysis of medical images. And as you can see here, we switch the paradigm and start using machine learning models, the classical ones that have been mentioned, and more recently, deep learning models. And why did it happen? So basically, our colleagues working in the computer vision field had been developing for a long time new methods, algorithms to identify objects in typical images. So the accuracy of those models reached kind of a plateau until 2010, 2012, when it was more common to start applying GPUs and new neural architectures, the famous CNNs. And suddenly the accuracy for identifying different objects increased significantly. And they thought, okay, so what we've been doing in standard images and with normal objects is actually what radiologists try to do in their daily life in the department, identifying different patterns that are maybe abnormal and try to characterize those abnormalities. So this is when we start applying those methods to medical images. And actually, the applications could be exponentially increasing as medical images are performed in every single step of the cancer journey, from diagnosis to staging, but also for identifying different prognosis, prediction of response, why not, and obviously also for evaluating response in cancer patients. And that's how we managed to develop new tools, as we have heard this morning, for aiding medical decisions, for supporting physicians in their decisions. And we have two main branches of these clinical decision support systems, one for diagnosis, computer-aided diagnosis systems, that I think the next talk it's gonna dig a bit deeper into this field, and also for therapeutic decision support. So the advances, as I was mentioning, in the medical imaging field goes hand to hand in both of two different flavors, let's say. One is improving the way we acquire those images with higher resolution, with less noise, with in shorter time. So that's better accepted than by the patients, and that means also that they are cheaper. And we also apply AI methods to advance in this sense and improve the quality of the images. And obviously, after the acquisition, how we process and compute that valuable information. We've heard about these more classical machine learning methods in which we have to extract what we call the predefined or handcrafted or engineered radiomic features. I'm not gonna go into much detail because I have a lot of things to explain, but basically this is the type of information that we can extract from every single voxel of the images. And more recently, also deep learning models in which we feed those neural networks, potentially even with the entire image. I must say that saves a lot of time because we don't need to label or segment every single tumor of the body. And yeah, this brings a lot of new opportunities, moving from what we are still doing in clinical practice, which is a two-dimensional anatomical assessment of the images, because radiologists look at the images in the axial plane, no matter what, and it's still very dependent on the observer, on the experience of the radiologist, to a 4D functional imaging and computation analysis, much more robust and in a quantitative way, so we can ideally develop all these new biomarkers that allow us to achieve early diagnosis, optimizing patient selection, and as you can see, all these different objectives. And in the next slides, I'm going to show you just a few examples, focus on what we are doing in our lab. So by the application of these models, we can develop new and more accurate diagnostic tools. And probably in this audience, some of you have been facing this problem. We have a patient that comes to the clinic with neurological symptoms. We do a CT scan and then an MRI scan. And we find out that the patient have a lump, an enhancing tumor in the brain, and we don't know if it's a GBM, a glioblastoma multiforme, which is actually the most common and aggressive brain tumor, or it may be a metastasis, or why not, it could be a lymphoma, which is more rare, but could be the case. And as you know, these three different entities require completely different clinical approaches. And what we end up many times doing is a biopsy, open biopsy, which have obviously may have some complications. So what we try to do is use standard medical images that these patients were having as a standard of care. And in this case, we were focused on the evaluation of the vascularization of the tumors. And this is a common sequence. Perfusion MRI is done in every single hospital nowadays. So the first thing that we had to do is to normalize the signals. We have heard about the standardization of the data. This is important to be able to compare different patients and even the same patient at different time points. And once we normalize those signals, so here we are seeing how the contrast is entering into the tumor and is washed out. We could pull together those curves and see that actually they were behaving differently for a GBM, a MET, or a lymphoma. What's the next challenge or drawback that we face when we try to apply AI for different clinical outcomes? We don't have enough data, as it has been also mentioned. So we try to tackle this issue and actually transform what the information of one single patient by extracting the information of every single voxel in that image. So instead of having one single source of information, we could have a few thousand sources of information per patient. And now, yes, we were able to feed our neural network, which actually is quite a standard architecture, CNN, for differentiating these three tumor types. And as you can see, the tool works pretty well. It's been validated in several external test cohorts, and this paper is under review. And we've heard also about the explainability. So we know that we need high accuracies, but also we need the physician to trust the tool, because at the end of the day, he's gonna, or they are gonna make the decision, and the responsibility is gonna be theirs. So what we did is also plot these maps in which it gives you the probability of all different tumor types per voxel. So you can see if it has randomly assigned diagnostic to each voxel. Probably in that particular case, I won't trust this tool and I will use my common sense and other sources of information. But if it classifies in a very high percentage as a specific tumor type, probably I will use this to make my final decision. And we can also develop predictive biomarkers, which are very, very useful in clinical practice, trying to stratify patients and select the best patient for every single treatment. And in this case, we have been focused our work on immunotherapy. We know that immunotherapy, it's an amazing treatment for some patients, but not all of them respond, and some of them have also secondary effects or toxicities. So the group of Gustave Rossi published already a few years ago this very nice work in which they try to identify a pattern, a phenotype in the CT images of cancer patients that could be associated to the amount of CD8 infiltrating the tumor, which we know that it's relatively good predictive biomarker of response in immunotherapy. They developed the signature in their own cohort and validated in the open cohort of the TCGA, and also try to clinically validate that signature by comparing the different scores and the different outcomes of patients being treated with immunotherapy. And actually they saw that the patients with a high CT score of that signature responded better to immunotherapy, probably related to this higher cytotoxic immune infiltrate in the tumor. But as you can imagine, when we develop a model that it's going to predict a biomarker, that model is not going to work better than the biomarker itself. So we try to follow a different approach and go straight to the clinical outcome. Try to see if actually in those images there was valuable information predictive of clinical benefit, yes or no, to immune checkpoint inhibitors. We developed that signature in a bunch of patients with different tumor types, and we validated it in 2 different cohorts, one with bladder cancer and the other one with lung cancer. And also we tried to understand what was behind that signature, what is the thing that we were capturing with it. In a subset of patients with RNA sequencing, we saw that actually patients with a high score for our signature were enriched for an immune cytotoxic phenotype in their tumors. And the next step is response biomarkers. Once we have decided if a patient is going to receive one treatment or not, the ideal scenario will be to know as soon as possible and as accurate as possible if the patient is responding or not. And in this case, again, we are focusing on immunotherapy, but in this case, we move from the CT images to a more functional imaging technique, MRI, in which we model those signals of the movement of water molecules within the tissue, and we compute the amount of cells and the cell size within the tissue. We have validated these models in mouse models in which we have the histology, and we see that our measurements mirror exactly what we see in the histology. And why not? We also want to study the vascularization of the tumors, which we know that play a key role in immunotherapy response. And we are now applying these models in a clinical trial in which we are recruiting patients prospectively with different solid tumor types treated with immune checkpoint inhibitors, in which we acquire the CT, the MRI, and also we are doing a blood test and tumor biopsies at baseline and at the time of progression. And this is preliminary data, work in progress, so please do not circulate or tweet this slide. But basically what we have started identifying is some signals in the changes of the tumor vasculature, and particularly in the leakage of those vessels, in this case with this particular marker, which is called the catrans. And actually that also goes in line with some previous publications by our colleagues in Cambridge. Sorry, I'll go back. But all the results that I've shown you are very promising, but the reality is that AI in the medical imaging field stays still very much in the research field. Just a few tools, and probably in the next talk, they will show you one is reaching the clinic, and most of the tools that have been approved by the FDA and by the European Commission are for tasks that are not so much clinically relevant in the sense of organ segmentation, sometimes improving the image quality as well, and just a few response and predictive biomarkers. And Jeffrey Hinton has been mentioned this morning, so I have a video that, sorry if there are radiologists in the audience, but it sounds a bit spooky, but I think that it's good that we also hear his prediction. This was made in 2016, as you can see.
Jeff, perhaps a similar question, if you may. What do you think is some of this exciting work to come?
Okay, so, sorry. Let me start by just saying a few things that seem obvious. I think if you work as a radiologist, you're like the coyote that's already over the edge of the cliff, but hasn't yet looked down, so doesn't realize there's no ground underneath him. People should stop training radiologists now. It's just completely obvious that within 5 years, deep learning is going to do better than radiologists because it's going to be able to get a lot more experience. It might be 10 years, but we've got plenty of radiologists already. I said this at a hospital and it didn't go down too well, but there you go.
Yeah, so he was wrong in his prediction. We will see in 10 years' time. I must say that probably he was not aware that in 2016, and it's still a reality nowadays in Europe and probably in the States as well, we are behind. The number of radiologists is far from what it's needed in the clinic. And to be honest, I think that AI tools will do much better than we do for some tasks, but I'm more than happy to be substitute for those tedious tasks like mammogram screening and many others that we have to do in our daily life. So I think that it's a combination of both fields which will improve our future. And why, there are many reasons why these new tools haven't reached the clinic yet. I just mentioned a few here. So for a biomarker to be implemented in the clinic, we need, that's mandatory, to go through all these steps. So we need technical validation of the technique. The technique needs to be shown to be robust and stable. We need clinical validation, which means that we need high accuracies and obviously outperforming the benchmark. And we've heard a very nice presentation about the trustability of and interpretability of those techniques, and obviously as well biological validation. And regarding the accuracy, and something that it's a hot topic, and I think that Saurabh is going to talk about it later on, so I will leave the expert on the field. Just to mention that obviously what we try to do is these tools to mirror what we do in clinical practice, and a physician, when they visit a patient, don't look only at the blood tests or the images, but we try to integrate all this information. So this is exactly what we are trying to do now with AI, integrating data that ideally will be complementary and will provide better accuracies. And we have a few nice examples of how we are going to do that and how the accuracies seems to improve. But obviously this is a tough task. This requires multidisciplinary team effort, data integration, which is lacking nowadays, to have well annotated data sets with all the layers of information available. And with that, I would just like to thank my team, which is truly multidisciplinary, and all our collaborators, and of course the funders that allow us to keep working on this field. And thank you for listening.
Thank you again, Raquel.
It is an honor and a pleasure to introduce you the last speaker of this session. He is a mentor to me, the Chief of Thoracic Surgery Unit in our institution, alive for screening, Dr. Ugo Pastorino.
Thank you. Particular thank to Arcela Prelai for having put together such a great group of experts and also audience. I have no conflict of interest to disclose. In the field of lung cancer screening, AI is already a reality. Is not only experimental, and I wouldn't say, as in the title, that is a second reading. Is very often the first reading, and it's very difficult to separate the contribution of AI and the expertise of the clinical radiologist. We use AI to have a good identification of the small nodule, segmentation of the nodule, volumetric measurement, precise calculation of volume doubling time, which is the main criterion to separate tumors from benign. And more recently, automatic quantification of coronary artery calcification, emphysema, and body mass composition are adding a lot to the pure diagnostic component of the chest CT. This has helped us to develop better performing screening strategies. So raising the threshold of nodules, the prolongating the intervals for low-risk individuals, implementing surveillance instead of active immediate treatment for low-risk subsolid lesions. But most interesting now is also the identification of the other smoking-related chronic disease, cardiovascular and COPD. Here we have run a series of prospective trials from 2000 on. Each of these trials has provided evidence of a clinical value. So the first pilot introduced, identified the benefit of a PET scanning screening and a higher threshold. The second, the MILD trial, showed not only the benefit of screening on the longer term, but also the equivalence of annual versus biennial CT, and has implemented a very long-term surveillance for subsolid lesion. The BioMILD studies combined CT with the blood microRNA, showing that the intervals could be extended selectively, not randomly. So giving a longer interval of 3 years to low-risk individuals. In the SMILE trial, we added prevention, pharmacological prevention. In this time, CT has changed. As you see, we have moved from a single slide to 16 slides in the MILD to 128 slides for the BioMILD, and we are now using dual source 388 CT. So completely different machines. But what is more important, we have decreased the toxicity, the radiation exposure from 2 millisievert to 1.5, and now with the ultra low dose CT of the chest, we are running on 0.4 millisievert. 2 millisievert, the low dose, was already 1/10 of the regular contrast CT of the chest. So we could run 10 annual screens with the exposure of 1 CT. And now with the 0.4, you have, cutting further. But what is the AI in this? It was known at the beginning. Then the lung care with the volume of solid nodules. And then the volume was calculated also for non-solid or subsolid nodules. And that made an enormous change in the practice. To give you an idea, we have picked the 3,000 CTs per year in 2015. We have tested more than 10,000 high-risk individuals, giving them more than 30,000 CTs. We started working on CAD. This is a paper of 2017 with the group of Matthias Kropov and Bram van Ginningen, a group of Nijmegen, which was really a top at that time in the development of artificial intelligence. And we have implemented this software together with this native software in the machine. And we demonstrated that it was possible to categorize automatically the nodule in 4 categories. I don't want to bother you with this, but let's make an example. The BioMILD trial enrolled more than 4,000 individuals, okay? And if you look at the number of nodules at baseline, is more than 3,000. But if you take all the 6-7 years of screening, it's 16,000 nodules. Most solid, but also non-solid, quite a lot. Can you imagine what that means? That you have to compare annual CT for each of these nodules, comparing each nodule with the previous nodules, is unbearable. So the first thing we did is to separate those nodules that have relevance from those that don't have relevance. And we applied the higher cutoff in 2013 ever used worldwide. And so we said everything up to 113 square millimeter is negative, is nonsense. And by doing so, we removed more than 80% of the suspicious lesions. Now it looks quite obvious, but at that time, 10 years ago, it was not obvious at all, because the NLST was using a threshold for nodule that was much lower than that. But this is why, because we relied in the volumetric assessment of the automatic AI system. We demonstrated it was reliable, and we used that. And by doing so, we cut enormously the work. In the biomedical trial, we sent to 3 years repeat those with the negative CT that were 88% of baseline. So the vast majority, and as you see, at 6 years, you have, instead of 29,000 CT, we did less than half. And this was the proof of concept that you can use volumetric assessment to reduce unnecessary repeats, unnecessary examination, unnecessary false positive. You have to consider that in the United States, volumetric measurement is not part of the clinical practice. It's only in Europe. So we are the only, Europeans are the only center that implemented, Canadian as well, but in the States, it's still diameter. Why? Not only volumetric, but a very high threshold. And as you see, the threshold 113/260 that we implemented in 2013 was accepted and by the long-run international system as the appropriate cutoff in 2019, so 6 years later. What is this, the meaning of annual, biannual, or triennial repeats that you can use to screen 10,000 individuals for 10 years? You can have much less expenses, much less efforts. This is not only economic; it has implication in terms of precision management. And we have put forward the concept of long intervals that enabled us to prolong screening up to 10 years, because it is nonsense to conceive a screening that only lasts 2 years. But you can only afford it long term if you separate the risk and you give a different management. Is the risk-based long interval risky? No. We've demonstrated that the percent of resection, the resection rate was higher, the stage 1% was higher in risk-based, and also, of course, the proportion of VATS resections was higher. So a risk-based strategy that was implemented by AI improved the performance. We have worked with the group of Politecnico, with Professor Castiglioni, to develop this a really diagnostic instrument. And this publication was published in 2021, showing that by the use of an algorithm that was generated by 3D slicer. I agree with the fact that it's better to use open source. We use 3D slicers because it's a standard. And we use the data acquired by 3D slicer to prove that you can improve the selection of those individuals that are going to develop cancer from a nodule, and adding something to the simple volume cutoff and volume doubling time. Unfortunately, up to now, we have not been able to transform this in a clinical instrument. So something like we can use during the screening to say, okay, you come in 3 months, you come at a year, and you come 5 years later. We cannot, but we are working on that. There is a project actually funded by the Ricerca Corrente, together with a group of Politecnico. We have clearly shown that volumetric management cuts in a completely different assess the characteristic of pulmonary features. This was published last year and showed that by the diameter does not represent the real size, for this very simple reason that tumors are not spheres. So the assumption that you can transform the diameter in a volume, and this is what we did here. We estimated the volume based on the diameter, completely overestimates the size of the tumor. And by doing so, you would do a lot of unnecessary repeats. We also used at the best the performance of the new CT. This is the dual source Force, which is probably the best scanning machine existing now. We use to set up a randomized trial to define the best ultra-low dose algorithm. We randomized 400, almost 400 individuals on screening into 4 different ultra-low dose CT. We use the one way to do the conventional and the other way of the scansion to do the experimental. And by doing this, we confirmed that it was possible to do it for solid and non-solid, and we confirmed that spectral shaping is reliable and effective, and we picked up the best of these 4 algorithms to use in all the other screening tests done after that experiment. Blood biomarkers are too difficult issue to be addressed today, but the only thing I can tell you, we are involved heavily on microRNA, and we've done more than 10,000 microRNA assessments during the screening, but this is still in a phase of research, and I think that AI is the instrument to integrate radiomic and blood circulating biomarker data. What I want to show you in the last few slides is the value of automatic measurement of emphysema and coronary artery calcification. For many years, it has been told and assumed that you could only measure calcifications if you have ECG-gated CTs, which is obviously impossible in clinical practice. But with the new AI instruments, this is not true anymore. And we've been working with this group of a Korean group that developed the Coreline software, and we tested the Coreline software not only in the BioMILD trial, which is a recent, relatively modern machine, and as you see, the coronary calcification at baseline predict all-cause mortality at 6 years in a very, very precise manner. But what is more interesting is that we duplicated this in the much older MILD trial, where we have 12 years of observation. And as you see, at 12 years, the mortality is totally different based on the calcification quantified automatically by this simple AI instrument. And as you have 1 to 2 years of interval from baseline to the beginning of deaths, you have a very interesting window for prevention. We have a window to intervene in several ways and to try to intercept all-cause mortality in the screening. We have also added, this is not AI, of course, we have added the treatment with the cytosine, a natural antagonism of nicotine receptor, and proved that in the context of screening with a randomized study, we proved that cytosine improved the quit rate. Now, how this fits with AI in a different scenario, that we also, in the SMILE, we also applied anti-inflammatory and dietary restriction modification to change the pattern. And so now we think that AI can help us to define body composition, not only to define upfront what is the metabolic feature of that person, but also to assess the changes. And the changes that usually are done with the abdominal CT, we have demonstrated can be achieved also with the chest CT. So with the same chest scan, we can have a very reliable definition of the body fat, not only the subcutaneous, but also the perivisceral fat. And this is a useful, we hope, a useful biomarker for the assessment of the changes in the metabolic feature during intervention. So you can do this. You can do the simple chest that we can do it now in 1 second with a new machine to get enormous number of information. AI requires big numbers, and we have also made an enormous effort to collect thousands of images in a database, collect thousands of blood samples, to have all the frozen section of the CT resected cases, which are now part of a project with NIH and to get TCGH data on screen-detected lung cancer. We are now coordinating a national study which involves 18 centers in Italy. The study, the Rete Italiana Screening Pulmonare, is doing very well, and we hope that all these AI instruments will be implemented in the RISP study in the Italian network, and these are obviously part of our European connection. We are participating in 2 European studies, the Foreign Lung Run and the Solace trial, and the population and our repository of data, both blood and CT data, will be available for this international contribution. So the take-home message is AI is essential for screening, is not experimental, is essential, but we can improve it. So we can give our contribution to make it better and to generate new ideas. Just to show you that artificial intelligence is not going to replace natural intelligence. This is our group, and as you can see, there is a lot of brains here, and we think that this is essential to put, to go ahead with this sort of clinical research, to have a dedicated, large, multidisciplinary group of experts and contributors. So thank you very much for your attention.
Oh, no, please, Dr. Pastorino, you can stay here and have a seat because we can start the discussion. We also invite the 2 former speakers here with us. And we also would like to remember to the people at home or in their lab that they can do questions using the online tools. So let's start. Any questions from the audience? We actually have a couple of questions. Yeah. Okay, you can start.
I will start with a question for the 3 speakers. In the previous session, the message was the higher number of data, the higher advantages. Is this also true for artificial intelligence in imaging? Better to have much more data, also metadata, or better to work on the image itself to obtain the result?
I can start perhaps. Can you hear me? Yeah. So I guess the quick answer will be yes. I'm staring at you because probably what applies to medical imaging is similar to digital pathology. But that being said, I mean, it has to be clean data correctly labeled with, we were mentioning also about the clinical outcomes, how we label clinical outcomes in a continuous way. If we dichotomize the outcomes, we have to be careful what makes sense technically to achieve good accuracies and what may have an impact in the clinic. And the reality is that we have to deal with what we have nowadays in the clinic. So I think that we don't have to be scared about the scarce data that each of us have in our hands, but try to start working with that, exploit it, get the most of it, and by all means, leverage these consortiums and collaborations with other groups.
Please open.
Sorry, could you actually rephrase the question? I missed just the first part of it.
Okay. Before we talk about the opportunity to add metadata to improve the outcome from artificial intelligence applied to imaging, to transcriptomic or other kind of data. For imaging, does it work the same? Better to have much more data, or better to work on the image itself and outline?
Yeah, so it's a good question. It depends on what the type of metadata is. So if the metadata that you're referring to is clinical information, then we're moving more towards a multimodal model, and multimodal models do improve for most outcomes when we're building biomarkers, do improve accuracy and reliability. And when possible, we should always strive to be building multimodal models and not working on imaging alone. If there's other types of metadata, so other types of metadata might include things like the site of origin, and site specifically is a very important metadata piece that we should strive to include when we have multi-institution repositories, as the site can cause confounders when we're building these models. And we often want to know that information ahead of time so that when we're building the model, we're not introducing confounding into our data set and making our model unreliable. So metadata like the site, the scanner that was used, how the tissue was prepared, things like that can be useful for building the AI model. And then metadata that is more clinical can be used for building multimodal models that can improve accuracy.
Thank you.
Okay, a question for the three of you. So, but we are also working now with the technology. You showed the good tools implemented with artificial intelligence, but also the technology is improving. We have seen something in radiology, but we know also in digital pathology, all the transcriptomic tools for digital spatial pathology. So are these systems open to the advent of the new data generated by the new technologies?
Yeah, so if I'm understanding the question right, are the tools that we have available flexible enough to improve as our technology advances? Yeah, it's a really good question. So in general, not all tools are built to be that way, and tools need to be maintained. So you can't make a tool and release it and expect it to be relevant 5 years later. It won't be unless it's being actively maintained, actively updated. And as research advances and as our methods advance, we need to work on continuously updating our tools. There's really two different approaches that you could take. You could try to have one tool that's continually developed. You have to maintain an active collaboration of software developers, medical oncologists, engineers to make it an active project to help it stay relevant over time so that it doesn't lose its relevance. Alternatively, you can do individual tools and just do one tool at a time for each advance as you go along. I think there's advantages and disadvantages to both. The former is preferred, but it takes effort and it takes work and time and reimbursement and funding.
If I may add, well, we know that the AI field is blooming, and we see new tools, new architectures almost every day. And we've learned that, I think you mentioned that each of them are better designed for specific data. So that's something that we have to bear in mind as well.
Okay, I have another question for Raquel. In your presentation, you have shown two important aspects, because I would say that especially in radiomics, we have started a long process of standardization of the data, and when we have different patients, different machines, and so on. And now is the time probably for doing better in what you have shown. So the first, the interpretability of the model of the classification, and second one, you shown also some example of let's say preclinical study where we can understand better what we got from the images. What, in your opinion, what is more important right now? I mean, what we should more focus to convince the clinicians to use this instrument, the part of the interpretability or the one of the mechanistic approach, let's say?
Very good question, and controversial as well. So I don't know why the idea of lack of standardization has spread so much in the radiology field. And I have the feeling, and I attend general oncology meetings, that in pathology, that's not the case. I mean, we assume that images need to be standardized, but in radiology, it came up to a point that we claim things like we are not going to be able to develop any imaging biomarker because images, the acquisition is not standardized, and that's not the point. So if I may tackle that particular point, I think that we do somehow standard protocols, particularly with CT scans in terms of contrast and the type of images, slice thickness, and so on. Also in MRI, but obviously we want to dig deeper into a particular biomarker. We need to define those protocols ahead and do prospective trials. But I think that that's something that it's been addressed, and there are some pipelines that are publicly available, and we just need to apply them. Trustability, that's the next key point here. I think that it applies not only to imaging biomarkers, but any type of biomarker. As a physician, and I've seen it in my colleagues, and I guess that I will do so, if I'm going to use a new tool, I need to understand it somehow. Probably for clinicians, they don't need to understand the architecture itself, or the maths behind that tool, but at least understand which type of information that's taken into account, and some things like if the tool is truly sure about the label that it's giving you, or not.
I would ask your opinion about a question that concerns data privacy. You talk about the great amount of terabyte required to store data locally. You talk about the large amount of image that can collected in the consortium, the ImageNet consortium. You talk about the large number of cases that are needed in a screening program to obtain data. Which is your opinion about the sharing of all these data that, of course, have a question of primary concerns over the world, or retain your data and use them to provide the...
Yeah, I can take this one. So this is a huge problem and a very important question, and there's a lot of work being developed to build AI systems that allow us to circumvent the need to share data if possible when building models. And so one of these technologies is called swarm learning, and the idea with swarm learning is rather than having all of the data from contributing sites going to one location, which puts a lot of stress on data transfer and increases the resources needed to carry out the experiment, can we run the experiments locally at each site and have them communicate with each other in a way that preserves patient privacy? And so these are technologies that are commercially available and are being studied for research applications for cancer. And I think that's one of the more promising avenues where we can circumvent the patient privacy concerns when training models.
That's great.
Unfortunately, Europe is an area with the worst restrictions in terms of so-called privacy protection. Is to me, it's this issue has very little reason to be sustained. We hope that we will demonstrate that the benefit related to sharing data at the European level overcomes any possible risk. But still, we see the whole world in the field of screening, making research using the repository of the NLST study that is 25 years old with very poor quality CTs, no volumes, nothing, because it's the only one that is available for researchers to use. And to me is offensive the fact that we have 20 years of experience database data of a very high quality that cannot be shared because of our GDPR. I think this is something that the scientific community has to start fighting against. Even if we have a 20-page consent form for our screening participants, still we are not allowed to share. But we have to break this wall. We must have the courage to say this is nonsense. This is hampering all our effort to save lives and at least at the level of a pure, fully unidentified frozen data. As long as we have a longer follow-up, we can also use frozen data. We must start a European initiative for sharing data, and this is the only way to get reliable AI innovative studies, that we have an international repository at the European level. I hope you can, with this type of initiative, you can build evidence to convince our, governors at the European level that is start to move against all those ties, restrictions in clinical research.
Thank you for this clear statement, Raquel.
I'm not an expert in ethics, but if I may add some, just a brief comment. Also, I still don't understand why is it possible to share so much genetic and transcriptomic data in open access databases and not that much about digital pathology or medical imaging. I don't know if it's only coming about the regulation or the researchers themselves, but I leave the comment.
I can't speak to the European context. In the United States, I think there's barriers on both. When you spend a lot of effort collecting your data on your patient population at your hospital, you want to continue to publish from that data and not release it so that people can scoop you. That's a barrier that needs to be overcome and a change of thinking.
Okay, any question from the audience? Or from the net? Otherwise, we can conclude this morning session and invite you to come back at Arcela.
1:30.
1:30.
Yeah, with the hot topic of multiomics data integration.
Thank you very much to the speaker for the great intervention.
Tanti anni fa, un supercomputer progettò lo snack dalla forma perfetta. Le Pringles.
Taking just be. Don't take it. Taking just so deep and live my life. Don't take it personal, but I ain't lying. I ain't hiding. I've been grinding, multiplying. I've been trying to get my weight up, staying prayed up, meditating and take time away. You always posting up pictures, trying to look like you winning. I'm writing rhymes in the kitchen, soaking in moments we live in. Yeah, you got the nerve to be on me, faking your life for the IG. If you got my number, don't add me, cause baby, I'm on hiatus. I'm on hiatus. I'm on hiatus. I'm on hiatus. Oh, baby, don't check for me. Taking time out to be and live my life off screen. Taking time out to be and live my life. Hey. Taking just so deep and live my life. Don't take it personal. We just building. It's my season, lay foundation. Come sing it to me. Oh, come sing it to me. Oh, and I'll sing it to you too. Yeah, I'll sing it to you. Somebody said let go, let go, let go. I think it might be overthinking it. My heart is still stuck, it shows, it shows, it shows. Yeah. Somebody help me get over it. I keep my eyes on the sun. And when the moon shines brighter, I will give it all. Yeah, I know it is time. 'Cause I've seen it all before. It'll pass me, it'll pass me, it'll pass me. I can look back on times that we've been bold. But they don't matter, 'cause I'm moving on. Yeah. But sometimes it shows, it shows, it shows that I need you here to carry on. I keep my eyes on the sun. When the moon shines brighter, I will give it all. Yeah, I know it is time. 'Cause I've seen it all before. It'll pass me, it'll pass me, it'll pass me. Now I know I will get through it. Yeah, I know 'cause I've been through it. Yeah, and I've seen it all. It'll pass me, it'll pass me, it'll pass me. Remember the time I was stood at your doorstep trying to figure out a way to get at you. Oh, I didn't know what to say. And I remember how my hands were shaking, sweat was breaking. Oh, but I knew you were the one. I always knew it was you. Oh, I knew that you were the one. Yeah, you were the one for me, the only one that could ever make me feel this way.
I know. I know that you are the one. Oh, I always knew it was you. I know that you are the one. Yeah, you are the one for me, the only one that could ever make me feel this way. I always knew it was you. I know that you are the one. That you are the one for me, the only one that could ever make me feel this way.
Lord only knows what it took to making you like a blossom of a tree or the color of a jewel. So divine is the feeling that I find, like a sweet mountain breeze in a fragment of my mind. I said, darling, you are all I want for sure. Darling, you give me everything and more. I said, darling, ooh, 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 yeah, girl, you know I miss you. Slide talking, girl, you're walking circles through my mind. And it seems like every day just gets better when you're mine. Then you love now and forever. For my hurt, you are the cure. Like a spring, you keep me healthy with a substance that is pure. And I said, darling, darling, I'm feeling rich although I'm poor. I said, darling, in your arms I feel secure. Darling, darling, ooh, 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 yeah, girl, you know I miss you, baby. You know I miss you. Oh yeah, you know I miss you, baby. You know I miss you. You know I miss you. And I said, darling, oh darling, you are all I want for sure. All I want for sure. Darling, in your arms I feel secure. I feel secure. Darling, darling, feeling rich although I'm poor. I said, darling, darling, give me everything and more. I said, darling, darling, yeah, girl, you know I miss you. Oh, baby. Oh, you know I miss you, darling. You know I miss you, baby. You know I miss you, baby.
just say it wasn't so. Just say you love me and let me fall back into sleep. But when I wake up, you say I had a real bad dream. Whoa, real bad dream. And then tell me, baby, about the time when we first met. Yeah, we were young back then, but I will never forget. You wore a blue dress shoulder. Don't ever look back. No use for second opinions. Don't wanna stay in the past. Just keep on going, 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 going over the top. And keep on rolling, rolling, rolling. Don't ever stop.
If you feel like it's real when I make your body shiver like an autumn leaf, I try to stay on my feet when you move a little closer to me. I can't breathe it. Your love is all I ever need. Take me going. It's time to let you know how I feel. 'Cause you're the one I dream about. When I fall asleep, when I wake up in the morning, you're the first thing on my mind. There is no one else. Oh, baby, it's you. If you're there when I'm here, I don't know what I could do to feel you. It's unreal to be a part in my heart. There's a place where everything's about you. I don't know who could ever make me feel like you do. Oh, keep it coming. It's time to show you my love is true. 'Cause you're the one I dream about. When I fall asleep, when I wake up in the morning, you're the first thing on my mind. There is no one else. Oh, baby, it's you. Yeah. And if I had another way to show you what my dreams are made of, I could somehow reach out to you, finally open the door. 'Cause you're the one I dream about. When I fall asleep, when I wake up in the morning, you're the first thing on my mind. There is no one else. Oh, baby, you're the one I dream about. When I fall asleep, when I wake up in the morning, you're the first thing on my mind. There is no one else. Ooh, you're the one I dream about. When I fall asleep, when I wake up in the morning, you're the first thing on my mind. There is no one else. Oh, baby, you're the one I dream about. When I fall asleep, when I wake up in the morning, you're the first thing on my mind. There is no one else. Oh, baby.
Still wonder how, yeah, you always make it right. Maybe it's all chance, but either way, you showed me how to reach for the best of myself. It's all good when you show the way, yeah. 'Cause even if I fall, ooh, I trust you'll stay, yeah. might be over my troubles. Yeah, they've been there for so long now. Ooh, 'cause suddenly I think of tomorrow. Yeah, since you came around. Ooh, I feel like the only one who found out the reason why. Oh, I was just lonely, but since you came around, all I see is tomorrow. When you hear me calling, oh, it's you and me. Ooh, yeah, 'cause I cannot fake it. No matter how I feel, yeah, 'cause you heal my aching heart. When you come around, I saw a million signs. I must be over it by now. There's a reason why. Oh, I think I might be over my troubles. They've been there for so long now. It's over. Suddenly I think of tomorrow. Yeah, since you came around. Yeah. Ooh, I feel like the only one who found out the reason why. Oh, I was just lonely, but since you came around, all I see is tomorrow.
Darling, I would die for you. Tell 1,000 lies for you. Love you like the ocean, love you in slow motion. Anything it takes to make you stay. But I can't rely on you. Doesn't matter what I do. You say you need a timeout, think you mean a buyout. 'Cause it's pretty clear you're on your way out. And though I understand it's hard sometimes to make up your mind in these trying times, yeah, I just can't accept you leaving me when I'm overseas with a heart so heavy. Think that I deserve the truth for once, not a guilty tone, 'cause you're not alone, yeah. You said you wanna come home, but I know you don't. So this time I won't hear it on the phone. If you got something to say to me, then say it to my face. What it's all about, why you're bailing out. Think you owe me an apology. Just say it to my face. You're sorry. You're so sorry. You're so sorry. You're so sorry. You're so sorry. Say it to my face. You're sorry. I did my job for you. Even quit some friends for you. 'Cause you couldn't stand it, me all independent. So you had to have me for yourself.
Possiamo iniziare? So, I think we can start. So this session will be about multiomics data integration and discovery. So it has called the hottest session of this Congress with the hottest speakers and the hottest moderators, all from Napoli. We won the champions yesterday, so we are very happy. And so please, Carmina, can you introduce the first speaker of the session?
Thank you. So it's a great pleasure to be here. Thanks to Arcela, and it's a great honor to meet and to introduce Professor Shah. I hope the pronunciation is good. So he is the Chief of Computational Oncology at the Department of Epidemiology and Biostatistics at MSK. So he is a great expert, and he is presenting today something really new. So how we can implement the potential predictive value of AI in the field and in the era of cancer immunotherapy. Please.
Okay, thank you so much for the introduction, and Arcela, thanks for the invitation and the organization to this wonderful, wonderful meeting, and congratulations to Napoli. That's many years in the making, right? Yeah, that's right.
33.
Okay.
33.
33 years.
Yeah.
Since the days of Maradona, right?
Yeah.
Okay. Very good. So here are my disclosures. Very good. So I thought I would start to frame the field in general. And so I lead a program in computational oncology. And I think what we're talking about, we talk about AI in oncology, AI for oncology. In our space, we also include computational as an umbrella term that encompasses also non-AI computation to build predictive models as well. So the frontiers of computational oncology research, as I see them, have two branches. The first is discovery from real-world data, and I think what we're starting to learn from the studies that we're executing and broader in the field is that combining orthogonal information has advantages for prediction of clinical endpoints that we care about. So this is a theme that will be iterated throughout my talk. And I think this has a great promise for improving personalized medicine. We tend to think about personalized medicine as being very genomic centric. We look for mutations in a tumor and accordingly prescribe a therapeutic management scheme according to that mutation. And I think what we're trying to learn now is how can we go beyond genomics and use the other data that's in the real world, that's provisioned in the standard of care. And of course, what we have the opportunity to do is take that data that's used to make a clinical management decision for the patient, aggregate it together, and then deploy machine learning technologies and AI systems on those data sets to generalize patterns in the large patient subgroups. So this is an opportunity also to discover new patient subgroups, stratify patients into groups that could be managed similarly and different from each other. So this was written about in a review paper that was co-authored by Kevin Boehm, who's here in the audience, where we would describe this in broad terms and mostly in theoretical terms, where the concept is that we can encapsulate clinical, radiologic, pathologic, genomic data into a unified model for making a prediction about a patient. And so this was the theoretical idea, and really invokes this idea of measuring and modeling the whole patient. So thinking about a comprehensive view that's not siloed, but rather integrated. And so there are a couple of papers that are listed there that are both the principles and also the proof of principle, one of which I'll talk about in detail. On the other half of the frontiers is discovering aspects of new tumor biology. And here we have an incredible advance in measurement technology, where we can start to measure, for example, whole transcriptomes of single cells in situ, using spatial transcriptomics and other innovations like this. And here the key questions involve understanding tumor microenvironments as a whole, as a holistic ecosystem that comprises the overall biology of the tumor. Tumor immune interactions, which ultimately are determinants of whether a patient will respond to immunotherapy or not, and actually pattern, of course, really incredible breakthroughs in vaccine development. mRNA vaccine development is all about understanding and modeling how immune cells may recognize tumor cells. And of course, this has a major impact in the idea of tumor evolution and the acquisition of drug resistance as well. So taking these measurements over time in space and at great detail invokes all of these concepts: tumor phylogenetics, cellular phenotyping, in situ spatial profiling, and immune recognition. And this really, I think, can be summarized by saying we want to measure and model the whole tumor. Okay, so on the left is measuring and modeling the whole patient through real-world data. On the right is really trying to understand the tumor biology through encapsulating multiple measurements, orthogonal measurements that cover the whole space of biology. And in order to make sense of all this, don't have to convince this audience, this is where all of our techniques in the quantitative sciences, computer science, machine learning, artificial intelligence, mathematical modeling, data science, etc., will play a pivotal and central role. The only way to actually do this is through these techniques, okay? Okay, so example number one is a proof of principle in improving the prediction of response to immune checkpoint blockade in non-small cell lung cancer. So a few years ago, we set out to construct a cohort of patients for which we could acquire thoracic CT images, PD-L1 immunohistochemistry, digitized histology slides, and MSK impact clinical sequencing, which is a 500 gene panel that we routinely apply to patients in a tumor normal setting. So we have sequence information, mutation information from 500 genes in the genome, and then some other clinical variables that are routinely collected in the standard of care. So all of this none of this is research data. This is all provisioned in the care of the patient. And so we thought, can we assemble this data to improve the ability to identify patients that might respond to immune checkpoint blockade? Because of course we know that none of the biomarkers work particularly well. So that's the main question that we set out to address. So this is a relatively small scale study, and I'll come back to this, why the size of the study is important. But this is the cohort, 247 patients with advanced non-small cell lung cancer. And so to do this, we set out to work with radiologists and pathologists to annotate these data sources. So we had the radiologists segment the CT scans, the pathologists identify tumor regions in the immunohistochemistry, and then we did feature extraction. So this is not deep learning, this is not CNNs, this is actually a kind of informed feature extraction from these data that we worked very closely with the experts, and then developed an integrative approach using this attention-weighted model to output and model the predictions. And so we separated the groups into responders and non-responders, and then integrated this data together to develop the model. And so I listed the principal contributors here, and you can see that there are pathologists, there are radiologists, and there are computational scientists all working together. That's really the only way to make this work. And I want to stress that this is a team effort, and in order to succeed, it requires multidisciplinary integration and cooperation and collaboration. So one of the efforts, a huge effort, was to actually implement tumor segmentation masks on these PD-L1 immunohistochemistry slides. And then once we did that, within the tumor regions, we extracted features, as I won't go over them all. This is all published work, and you can read the paper, but also download all the code and the features in great detail. And so what we did is first train and try to identify features that were discriminating the responders from non-responders from the PD-L1 stained immunohistochemistry slides. And then when we did that and integrated that with the similar approach to radiologic features and compared this to the standard of care, this is a PD-L1 staining score that's in the pathological record, and we tried to stratify the patient population. You can see here that the curves are not that well separated. Then we used tumor mutation burden as another on-label indication from the genomic sequencing, which is just counting up the number of mutations per megabyte, and that's an indication for that's clinically approved. And that creates a slightly better separation between the risk strata. Then we used a logistic regression model, which was equally weighting all the features together. And then finally, this attention-weighted model called DIAM, which then you can see really separates the low-risk group from the high-risk group quite effectively. And so this is really a really nice proof of principle that as we layer on information, we gain strength and actually can outperform the standard of care biomarkers for risk stratification. And you can see here that this is in a Cox model. You can see that the hazard ratio for the DIAM model score at the very top has really quite a significant hazard ratio and is highly predictive of response. So that gives you a proof of principle of the power of taking these complementary orthogonal measurements of histopathology, radiology, genomics, integrating them together to make a prediction about response in immunotherapy. So I think this is quite a powerful concept, and it has its limitations, which is essentially that this required significant manual annotation from experts. So this is not an end-to-end machine learning or AI model where we can just have the digitized image, execute deep learning, and expect to get some results. What we wrote about in Kevin's review paper is that we're still in a small data regime here with 247 patients. And it's probably not appropriate for deep learning. So we have to understand what are the limitations of these approaches and then strategize appropriately. And I think the other quite important point to make, and Bob and I were just talking about this earlier, is that this is quite difficult to reproduce in other institutions and to actually gather this data. It's only 247 patients, but to have genomic sequencing, digitized PD-L1 staining immunohistochemistry, and the thoracic CTs that are segmented, the reviewers asked us to find another cohort to validate the model, but we couldn't find one, basically, is the point. So I think what we'd like to do is lead by example here. We've released all of the data here, all the annotated data for everyone to use as part of the paper. We released all the source code that's part of the paper as well. And so hopefully other people can then take down what we've learned and apply it to their own data to make progress in the field. Okay, so now moving on, I wanted to illustrate another example on the right-hand side of discovery of new tumor biology. And so I wanted to give a bit of background here. This is a study on high-grade serous ovarian cancers. These are the most lethal gynecologic malignancies where it comprise about 70% of ovarian cancers. Nearly 80% will recur after initial response to therapy. And so there's a real clinical need to better understand and stratify these patients. What this heat map here shows is features extracted from whole genome sequencing, here of 170 patients, but we've reproduced this now in about 350 patients, whereby we studied the pattern of mutations, both in the point mutation signature space and also in genomic rearrangements. So rearrangements are translocations, inversions, tandem duplications, et cetera. And so when we classify the rearrangements that occur in these genomes, and it's really quite profound, this is the archetype tumor of genomic instability that accrue massive amounts of genomic rearrangement in their genomes. So we thought that we could extract the patterns of alteration in both point mutation and structural variation space, so we might be able to better stratify the disease. And so what's shown here is a stratification that encompasses on the left the homologous recombination deficient subgroup, just typically identified by BRCA1 or BRCA2 mutation, and or clinical testing by companies like Myriad, for example, which use a slightly broader genomic assay to identify. And why this is clinically important is, of course, the homologous recombination deficient tumors are candidates for PARP inhibitors, which is mostly given in the maintenance setting, but is now actually being considered in the frontline setting as well. And that's shifted the needle. I think 90% of patients will still relapse, but I think it's actually moved the progression-free survival quite significantly. So the point here is that by integrating point mutations and structural variation signatures, we could substratify homologous recombination into two different groups. So on the left, you see These are tumors that accumulate small and medium tandem duplications in their genomes. They have this HRD point mutation signature that is often called SBS3 in the COSMIC database. And they're enriched for BRCA1 mutations. But the key point is that not all of these tumors have a detectable BRCA1 mutation. So the genome provides evidence for what we call biological mimics of BRCA1 mutant tumors, just because they accrue mutations in the same way as the BRCA1 mutation-bearing tumors. In the second column is about 20% of patients. These are what we call HRD del. They accumulate, instead of tandem duplications, they accumulate small interstitial deletions. And so these are enriched in the BRCA2 patients and essentially kind of mutually exclusive with the BRCA1. So there's really a very definitive split in the HRD cases between the HRD dupes and the HRD dels. And then on the right, we have the non-HRD tumors, 10% or 12% of which are characterized by these tandem duplicators. So these accrue very large tandem duplications in their genomes. They're enriched for CDK12 loss of function mutations. They lack the HRD signature, and yes, they accrue these tandem duplications. On the right is about a quarter of the population is classified as fold-back inversion. And here's a picture of what these genomes look like. They have these characteristic stepwise high-level amplifications in their genomes. And at the breakpoints of these high-level amplifications are what we call fold-back inversions. And so these are short inverted tandem duplications shown by these green arcs that are responsible for creating these high-level amplifications in oncogenes, such as cyclin E1 in this case. Cyclin E1 is mutually exclusive with BRCA1 and BRCA2 loss, and is shown to have a really poor prognosis in these tumors. So these represent, I think, a very difficult to treat. These patients over here, they tend to do better. These patients over here are essentially refractory to treatment. And so these genome stratification tools are quite important because they really stratify the patients into different prognoses. Okay, so that's a long introduction to how we then stratify these tumors. But once we do that, then we can ask all kinds of questions. And so in this particular study, which was published about 5 years ago now, we just asked the basic question using bulk gene expression data. What is the immune activity in these tumors, and do they have different immunologic profiles? So just looking at the expression of cytotoxicity, cytokines, antigen processing, you can see that these fold-back inversion-bearing tumors, they're much more immunologically cold than the HRDs. So the HRDs do elicit an immune response, whereas the FBIs are essentially immunologically inert. And so we started asking the question, why is that the case? And so when I arrived at MSK about 5 years ago now, we set out to create a prospective project called MSK Spectrum on the left, whereby we worked with surgeons to collect tissues in the OR that are suitable for, so we're in a single day workflow. We could take these tumor specimens, create single cell suspensions, and then prepare the single cell suspensions for single cell RNA sequencing on a same day workflow. And so the power of single cell RNA sequencing is that we can not only identify the cellular composition of a tumor, but we can start to identify the phenotypes that the cells acquire, the phenotypic states. And so we can tell the difference between, for example, a naive CD8 T cell and an exhausted CD8 T cell, which always has major implications for response to immunotherapy. So what we did is then execute single cell RNA sequencing using sorted populations on CD45. So we had the malignant cell population and the immune fraction. And then we kept a piece of tissue embedded in formalin, and so that allowed us to do both digital pathology from standard H&E, but also multiplexed immunofluorescence using the Akoya Vectra platform. And here what we did is we stained for pan-CK, PD-L1, PD-1, tox as a marker of T cell exhaustion, and CD8 and CD68. So then we could start to learn a little bit more in situ about the phenotypes of the immune cells as they related to these mutational signatures, which we extracted from whole genome sequencing. So here's a really good example of multimodal data or multi-omic integration that involves whole genome sequencing on the bottom, in situ or spatial profiling in the middle, and single-cell RNA sequencing on the top. And this was a major collaboration with the clinical groups, and I want to acknowledge the clinical leadership that of the GYN disease management team that really got behind this, Nadim and Carol, and especially the surgeons who helped us collect all the data as well, and then a medical oncologist, Dimitri Zamarin, who is essentially the co-author of this paper. So the punchline is really that we could integrate then these signatures that are now shown in a UMAP formation with this really extensive data set of single-cell transcriptomes. And so it really shows that there are about 1 million cells in this study. And here, what we have done is project these into a UMAP, which is essentially a two-dimensional representation of the transcriptome of each of these cells. So each dot here represents a single cell, and there's space on the UMAP is some representation of its transcriptional profile. And so what's gratifying about this, and the way to read this, is that the T cells, for example, they all cluster together from all the patients. The myeloid cells cluster together and separate from the T cells. The fibroblasts are here, and the cancer cells are here. And so one thing to note right off the bat is that the cancer cells tend to cluster by patient, and that's because of the bespoke structural variations that occur in each tumor. They drive the expression of those malignant cells in very specific ways, right? So that's why the tumor cells are patient-specific. So just to quickly run through the results then, so we first asked, what are the malignant cell phenotypic states that associate with these different mutational patterns? Once we stratify the patients by whole genome, then we ask what is the enrichment of the signaling. What you can see is that the HRD dupes here, they have upregulated JAK-STAT signaling, whereas the full-back inversion-bearing tumors, they are upregulated in TGF-beta. And so this was really something that we couldn't have identified through traditional gene expression, because essentially with a bulk multicellular measurement, this signal was obscured. So by doing the single-cell work, we were able to isolate these signals. And so this tells us that there is essentially an immunosuppressive signaling going on in the full-back inversions that's very distinct from the immunoreactive HRD dupe tumors. Similarly, in MHC class 1 and MHC class 2 tumors, you can see really dramatic differences in expression, whereas where the HRD dupe tumors are expressing HLA and B2M and the MHC class 2 proteins at a much higher level than the full-back inversions. And that has consequences also on the immune cells. So this is now a UMAP of just the T cells, and this shows you basically all the phenotypes that we identify. And the punchline here is that the full-back inversion-bearing tumors tended to have T cells that stayed in a naive, undifferentiated state, whereas the HRD dupe tumors had highly differentiated and dysfunctional exhausted T cells that were consistent with chronic exposure to neoantigens. And again, these T cells also express the JAK-STAT pathway. So there's very strong differences in phenotypic signaling between these 3 or 4 different mutational processes. Okay, and lastly is that in situ, we also noticed that there were many more proximal interactions between CD8 positive T cells and cancer cells in the HRD dupe tumors as shown on the top versus the full-back inversion-bearing tumors on the bottom. And so to summarize this is a density of proximal interactions between these different subgroups, and you can see that the distance between the closest T cell and cancer cell in the HRD dupes is much lower and peaked at a much lower distance than, for example, the full-back conversions, which are spread out. So this is a nice validation of the phenotypes that we observed. And so to summarize, we really have this dichotomous pattern of phenotypic properties in the immune cell states of the full-back inversions and the HRD tumors. The full-back inversions are essentially immunologically cold, and the HRDs are immunologically hot, but end up being exhausted. And so that's just summarized here, and you can read the rest in the paper. And I just want to conclude by saying a few things. We come back to this slide about the frontiers of computational oncology research. What we now want to do is in the real world data is scale. So I mentioned this small study of 247 patients. It's quite effective, but hard to reproduce and is a relatively small scale. So what we're now doing at Memorial is creating a platform where we can actually integrate data from 100,000 patients in clinical genome sequencing and digital histology and clinical data. We need to prospectively encode the clinical data in EHR so that the data is ready and we don't have to rely on clinicians to then go back and clean it. Those are, I think, the main points I want to make there. On the other side, there's a whole list of really powerful directions to take. And I think I'm out of time, so I think I'll just stop and summarize to say that multimodal data integration is a powerful approach to both real-world data and also experimental data interpretation. Requires multidisciplinary collaboration, as I've already mentioned, clinical expertise working alongside computational scientists to add the rigor. Data engineering efforts are absolutely required for the scale, durability, and future systematic work in this field. I don't think we can do this work without investment in data engineering. And so don't let anybody convince you otherwise. This is really required to succeed. The single cell technologies, I think, are going to be really important in research and how to leverage appropriately the AI tools for insight on evolution selection is going to be important. And then lastly, I think the point I want to make is that open code and open data provide a pathway to advance this field. And we've talked a little bit about that this morning. And I just wanted to pick up on that theme that we need to share data sets. I think that's key. It's hard to do. We need to figure out a way to do it. It may be through swarm learning, it may be through federated, but we need to do it. We need to share code. And I think that was something that James picked up as well. There's no need to write software anymore, really. You don't need to do it. So don't do it. And so I think that's something that we should all espouse. So this is an acknowledgement of a huge number of people that illustrates the team science. These are the funders, and I'm out of time. So thank you very much for your attention. I want to thank the patients and families for contributing to research as well. Thank you.
Thank you.
Thanks, Dr. Shah, for your presentation. I'm very glad to be here now introducing the second speaker of this session, Professor Alexander Pearson from University of Chicago, Chief of Pearson Lab, a research group involving both computational and clinical expertise. He will give us a presentation about opportunity from AI, about drug and biomarker discovery.
Great, thanks. So I'm both a medical oncologist and a statistician. So I'm going to wear my medical oncologist hat during this talk today. And so these are my disclosures. They're pertinent only to my leadership in terms of the head and neck medical oncology group. But I wanted to start with a quiz since we're in our insulin glut after lunch. So this is, can I see a raise of hands? Who are the clinicians in the audience? Okay, great. All right, enough to make it interesting. So in this quiz, I want to offer to the audience that you can choose either A or B. And the goal here is you need to come up with a treatment plan for this conceptual patient. But you only get the information from A or from B to make your decision. So do you want to know A, that the patient is a 54-year-old man with a 30-pack-year smoking history and diagnosed with stage 3 head and neck squamous cell carcinoma of the hypopharynx? Or would you prefer to have this high-resolution digital pathology image? So show of hands, who would want the information from A? Good, okay. And how about from B? This is usually a test of who's a pathologist in the audience. Yeah. And indeed, I'd choose A as well. So, but let's switch the concept a little bit. And as we're talking about biomarkers and precision oncology, let's instead, you have to make a decision just with the information from the two categories. So it's the information from A, but now in this frontline stage 3 patient, you would also know that the patient was a P53 mutant, was a likely immunotherapy responder, but you have to pay. The cost of making that decision is a 4-week delay in initiating treatment and $6,500 US. So who would prefer the information from A? Okay. Me, yeah. And how about from B? I've told you the answer. So, okay, great. So in the US, the reason why I put this is a little provocative, because we don't make treatment decisions in the frontline setting with any of that supplemental information. And so from my perspective, that's a cost, both in terms of delay of initiation and, a cost to the already bloated US healthcare system with the cost of that putative, test. So I continue to choose the information from A. But now, having set this up, I'll change it again. And that is that we now, with the same information, I've reduced the cost barrier. And now you know that the patient is indeed an HPV negative, as you suspected, cancer, an HPV negative cancer, human papillomavirus, and also has a high recurrence risk. And now, who would choose A? Anyone still? Okay, how about B? Yes, I think now we have helpful additive information with no cost. And the argument that I'll make is that with artificial intelligence, we have the potential to combine this clinical information and other factors and then derive some of these precision targets on behalf of our patients in order to make clinically useful and non-cost additive decisions. So I'll frame, having introduced the topic, I'll frame the way we kind of think about the broad concept in terms of the complexity of cancer. So a patient's tumor might reflect abnormalities at multiple different scales, and I think you've heard this from Professor Shah's talk, and you'll hear this from Jakob's talk, Dr. Cather's talk. And so, a variety of different alterations from the environment the patient lives to the microscopic tumor microenvironment or even molecular changes might alter the way their cancer behaves and the characteristics of their cancer. And so we think of this global, representation and some number of axes, which might include things like whether the immune cells can infiltrate the cancer and how fast the cancer grows and whether it has certain alterations which would respond to different therapeutics. Each of these, or many of the scales, and this is not an exhaustive list, can be inferred, that the states of those scales can be inferred with different technologies. And you've heard about many of these technologies today. That comes from demographics, that comes from next generation sequencing, that comes from that standard diagnostic pathology. And so these are the way that we can capture in a digital format the states that represent the complexities of cancer. The goal here, or the promise, I should say, is that some amount of information in terms of the complexity of cancer can be used to choose existing treatments or to find new treatments. But each of these, different methodologies has a different cost basis, and I argue that there's a wide range, many orders of magnitude in terms of the cost that exist. And so, one of the concepts that drives the work in my lab is whether we can leverage the least costly of these mechanisms to make those, to accomplish those same tasks, to choose existing treatments or to find new treatments, as well as to simultaneously reduce costs by choosing components of these measures of tumor complexity, which have the least cost implications to the patient and to the system. So the broad hypothesis that I'm going to cover in a couple of subtopics are that AI tools can provide us with biologically relevant, cost-effective, and trustworthy biomarkers for cancer care, and we can better understand cancer biology as a result. So, in the first of those domains, the biologically relevant biomarkers, I'll just touch on this, but this is to say that AI tools, deep convolutional neural networks, can predict molecular alterations in a lot of different cancer subtypes for a lot of different targets. And there's a lot of work done on this, and there are some of these, including microsatellite instability and FGFR2 and 3, are moving through the regulatory pipeline now, and I think will be approved biomarkers. This is a screen grab of work I did with Dr. Cather some years ago where we tried to find every genetic mutation in every cancer from TCGA. So that's thousands of patients. And we quantified the ability to detect any of these alterations using digital pathology alone. And we conceptualized this as kind of a digital next generation sequencing directly from histopathology. So I'll point out just that the rate, the speed that you can accomplish some of these tasks is really fantastic. You know, we came up with this idea. I know the exact date. It's March 21st, and then within a year we had posted the preprint to bioRxiv after doing this comprehensive analysis. So the biomarkers that we can derive are also cost effective. So this is leveraging work. I won't go into all the details to spoil Dr. Cather's talk, but microsatellite detection, microsatellite instability detection can be done with high accuracy from a digital pathology slide, and has direct implications on treatment decision making. So in the US, microsatellite instability tells you that you can treat with immunotherapy instead of chemotherapy, and improves frontline progression-free survival in colorectal cancers. And so we did we did a thought experiment effectively to say, okay, so we have a biomarker, it works well. What would be the implication to the system of implementing this in its current state? So that's what are the costs for making the correct and incorrect decisions? What's the burden to the patient? And indeed, what we discovered in our economic analysis was that we could dramatically reduce the cost of the testing. We could dramatically reduce the cost to the system, in terms of the overall cost of the treatment plan. We could reduce significantly the time to treatment initiation using a fully AI-driven biomarker compared to an NGS-based biomarker or an immunohistochemistry-based biomarker, and we could maintain excellent correspondence with the standard of care. So, the question that I think has been asked is, are AI biomarkers ready for prime time? And we wanted, I think we argue with this that yeah, we have tools in hand already where we can start making decisions that are really accurate and have some direct benefits to the patient's perspective. Like, for example, by decreasing the amount of time taken before initiating treatment. One other thing that I think you've heard referenced is our exploration on democratizing using both open source software, but also open source hardware. So James, Dr. Dolezal talked about this. One of the experiments we've done is to prototype a 3D printed open source microscope. And it includes, these are the contents. So all of these, we have this table with the cost. OpenFlexure was not our published domain, but we've adapted it for oncology prediction with digital pathology slides. And so all of these contents are included under open source licenses and have very low costs compared to, for example, an institutional slide scanner, which might cost hundreds of thousands of dollars. So the all-in cost of this digital pathology 3D printable open sourced workstation is around $300, and it maintains an incredibly consistent correspondence with the models. So the data capture is done on this microscope. The models are run on a $35 computer, and the correspondence is super high with the models that were run on institutional slide scanners. So this is, you could imagine in low and middle income countries or low resource settings, that this is a way to get around having to have a $300,000 slide scanner. All right, so the next topic I want to cover was trustworthiness of biomarkers. So for those of you who are clinicians, there's this, and not computer scientists, there's this kind of seminal cautionary tale in computer science where in the early days, teams trained algorithms to recognize pictures of wolves compared to pictures of husky dogs captured from the internet. And then they evaluated the explanation for what the algorithm was doing, was recognizing in this picture. You know, did the animal have different ears or a snout length or long tail or something like that? Indeed, it was none of these things. It was whether or not the animal was standing in the snow or in the woods or was in your living room, because these were internet pictures, right? So this is a terrifying cautionary tale, right? Because the animal is correctly assigned based on where it's standing, and not whether it's truly a wolf or truly a husky dog. So as clinicians, you know, the analogy is, depending on the data, we might be making horrible decisions on behalf of the patient based on which door they walked in the cancer center or what neighborhood they lived in, right? These are really threats to us. So we want to understand and trust the biomarkers we're using, especially if there's a black box component. So one of the things that we've done is use a generative adversarial network. So these are, you might have heard these as synthetic histology or hallucinations. And fundamentally, we're running a neural network in reverse. We're asking a neural network to draw pictures of what it sees or what it conceptualizes as a given state. And so we can feed a network some degree of noise and then have a component that evaluates the results. And so as an example here, this is data from our lab where we trained a neural network to recognize every different subtype of cancer from large publicly available repositories. And then we asked the neural network to draw us a representation of each of the different subtypes of cancer. And so you'll see that it retains, you know, retains kind of the same image format, but that we can see all of the differences within those slides, within the tiles, I should say, of what the core concept of that image actually is. And now here's a close-up just to show that it's really accurate. You know, it's a really accurate image, and there's a lot you can learn by looking at the patterns within one of these images. So we've deployed this in some unique ways. And so one of the things we did based on a model we trained for understanding thyroid cancer subtypes or thyroid tumor subtypes on an axis that was BRAF-like versus RAS-like. And you can see some of the synthetic images along this transition. We ran an experiment to see if we could use this digital neural network to train an organic neural network, which is a pathologist, based on this data. So we had a reader study where we gave pathologists in training a standard lecture on pathology of thyroid lesion subtypes. We tested their knowledge of being able to predict the molecular states, BRAF or RAS-like. We gave them a curriculum entirely based on synthetic images, and then we tested them again. And these are the performances. And this is not recognizing molecular states directly from histopathology is not a standard training exercise. So we saw an increase in the performance of a human pathologist on a new set of real images based entirely on training from synthetic images, which we thought was really interesting and provocative. So that these trustworthy data sets actually provide us some useful information. The other way we can trust a black box algorithm is if we know when to distrust it. So there's a recent paper just come out in the last week that pathologists radiologists suffer from a strong anchoring bias if given false information from an AI algorithm. So if they're faced with, say an algorithm says it's state A, their likelihood, their accuracy actually decreases when the true state is B. And so one of the things we did was try to create a biomarker that acknowledges its own uncertainty. And so we can do this with a process called MC dropout, where we're altering the actual active connections within a neural network. And then from that alteration, we can get a distribution of the performance of that network, and then infer the degree of confidence And so when we can infer the degree of confidence on any given prediction, we can say, oh, those low confidence predictions are ones that we should ignore. We shouldn't include them, or we should let the user know that this is, we think that this is cancer, but we're not that confident, right? That allows us as trained physicians to supersede the prediction of the model. And indeed, we showed that the performance of that model, of the models, can improve even across a wide range of available training data, so that this was a strategy that could be used in sparse data settings as well. Finally, I've shown some of the extensions of what biomarkers can do, but one of the other things that we're really invested in is this using the tools we've developed to understand the biology that we don't know yet. So I commented on one of my first slides about what latent structure looks like, and indeed, this is what we want to do with transcriptomic analysis as well, or multimodal analysis. So we can, in this experiment, we took a large amount of pan-squamous cell carcinoma data, so data that comes from head and neck, cervical, and lung, and we used a method called COGAPS to develop, instead of discrete states for each, we developed axes of variation. So in other words, an individual might not exist only in one class. They might exist in classes where you could have high levels of multiple. So you might have high immune cell infiltration and a high rate of cell growth, of tumor growth, for example. And so we used transcriptomic data, developed a series of axes which cross-define each sample. And then we evaluated this on both the publicly available TCGA data and CPTAC data. We could develop a series of 12 factors in our experiment, and we gave these putative labels based on looking at other characteristics, clinical demographics, mutation, and so forth, and thought that there was a significant amount of anchoring in reality from these unsupervised machine learning derived transcriptomic features. And then we went back and tested our ability to anchor these concepts in reality. And so we again used one of those generative adversarial networks to create representative tiles for each of the factors. And then we showed those and had those annotated by human pathologists again. And so you can check this out in the preprint, but each of the factors has characteristics where a higher level of this factor 1 might have less stroma, smaller nuclei, increased lymphocytes, etc. So and this was we were able to accurately predict the transcriptomic features directly from the histopathology across these 12 latent represented axes. So I'll conclude by saying AI biomarkers are here. There was a question before about prospective trials. Here's a list of the prospective trials that we found for AI in oncology from a paper that Arcela wrote and I got to participate in. And so it's here, it's coming. We just have to figure out how to maximize impact over minimizing costs. So with that, I'll conclude and thank the teams I get to work with and my funders.
Thank you so much, Professor Pearson. And now it's my pleasure to introduce Professor Jacob Nicolas Kater. He's Professor of Clinical Artificial Intelligence at the University of Dresden in Germany. And he has his own research group on artificial intelligence. And he recently published on Nature Medicine and Nature Cancer about machine learning and artificial intelligence. Please, Jacob.
Hi everybody. Thank you so much. Thank you so much for inviting me and for organizing this great conference, Arcela. It's really a great forum and it's an honor for me to be here. So I'm Jakob. I'm a GI medical oncologist, and I also have a background in image analysis. I'm based at Technical University Dresden in Germany. This is my website, my Twitter. You can feel free to follow us there. And in the next 15-20 minutes, I'm going to speak about AI-based multimodal data integration in oncology. These are my disclosures. So in the morning, we already heard a definition of different AI approaches. What is AI? What is deep learning? Basically, the takeaway is the boundaries are fuzzy, right? It's not perfectly well defined. But when I am confronted with this question, I'm very pragmatic and thinking about the data that we actually want to analyze with a given approach. So anything, and these are the types of data that collaborators want us to analyze, usually tabular data, image data, and free text data. Tabular data is basically anything that you can put in an Excel table, right? And for these things, you don't need AI. For these things, what you need is statistics, classical machine learning methods, but this is not really what most people understand when they talk about contemporaneous AI methods. But then there's image data and free text data. And these are types of data where the classical statistical methods and machine learning stuff that we had like in the 1990s and 2000s, they don't work at all. They really fail miserably. And so we need to use deep learning based methods. And this is what most people think about when they say AI nowadays. The types of techniques that we use for these data are artificial neural networks, convolutional neural networks for images, or transformers nowadays for images, and for text data, it's also transformers. So basically, it's pretty easy. It's always the same type of architecture that you use to analyze these data. I will speak now a bit. And in oncology, we care a lot about image data. So traditionally, like if you look at the landscape of clinically approved AI-based devices in medicine in general, 95% of that is based on image data. And so if you're speaking about AI in medicine, in many cases, it's about image data, and now also nowadays, because the techniques have become better, about free text data. So what I'm going to speak about today is first about AI for image-based biomarkers, and then a little bit of multimodal and text-based analysis. I included some illustrations that I generated with the Midjourney AI model. So these are like big AI models that you can prompt with a certain text, and then they will generate an image for you. For example, here I asked it to generate an image of a pathologist at work, and this is what you get there. Quite fascinating, not immediately useful, but fun. Let's speak about image data. In oncology, we deal with image data a lot. These are different types of image data, all shown at the same scale. 1 pixel in one image is 1 pixel in the other image, and we all love radiology images. For example, we cannot do oncology without radiology, right? We need that to diagnose tumors, to stage tumors, to follow up during treatment. But so we love radiology, but when it comes to pixel size, number of pixels in these images, it's actually not so large. You don't have so much information in these images if you compare it to histopathology images. And this is just one single histopathology slide of a cancer, and typically we have for every patient like 20 or so slides, right, or more. And so there's just a lot of pixels in these images, and so this allows us to extract a lot of information with AI methods. This is not just all of this is not just an academic exercise, but there's right now clinically approved devices in different types that analyze different types of image data in oncology. So these are just some random examples that I pulled from the internet for clinically approved AI solutions for radiology or pathology image analysis. Some of them are very basic, so they let you, for example, just segment nodules on a lung, on chest CT. Others are, or segment cells in histopathology images. Others are more advanced, so they let you predict risk of death or relapse directly from histopathology slides. So these things are making it into the clinical routine. The fact that they're approved in the US or in Europe does not mean that anybody is actually using them, right? So it's another step from having an approved product to making people use that actually in clinical routine. But I think we have seen in the last couple of years that the field is moving fast, and these things are moving into clinical routine deployment. So what are some of the things that, so these were some products that are essentially on the market, and these things are not so interesting anymore for academic research, because these things are out, they work, they just have to be improved maybe a bit. What we focus on in our academic research is to find new use cases, find new applications where we can use AI in image analysis. And one of the things that we are very interested in is to find correlates between the genotype and the phenotype of tumors. So in any organism, the genotype ultimately determines the phenotype, right? And that's also true for tumors. So any genetic alteration that you have changes the way the tumor looks like. And so what we hypothesized, we started to think about this a couple of years ago together with Alex Pearson and many others, is that just by looking at the histology image, you can basically guess the genotype from these images. And we've seen many beautiful talks here that have shown applications of this technique. This was one of our own work where we showed that that we can predict microsatellite instability in colorectal cancer, gastric cancer, and endometrial cancer from H&E pathology slides. And microsatellite instability is kind of an easy case because we know how this changes the actual phenotype, but for us it was a proof of principle to show that we can predict genetic alterations from H&E slides. And this was published in 2019, and now it's a clinically approved diagnostic device in Europe, so you can buy that and use it to diagnose colorectal cancer patients for MSI. The way this is marketed is as a pre-screening tool, because the performance is not perfect, but you can adjust these things such that they have a pretty high sensitivity, so you don't miss any patient, while being able to exclude maybe half of the patients from subsequent testing. Microsatellite instability is just one example where we can look at the phenotype and guess the underlying genotype, and there's many other examples. We did some work together with Alex in 2020, and now just this year followed up on this in larger cohorts with better methods. And what we found was that in many types of tumors, there are some genetic alterations that we care about, that we can predict from just by looking at the H&E pathology slides. Some of these are old friends that are relevant in clinical routine, such as BRAF mutations in colorectal cancer, CDH1 mutations in breast cancer, which are associated with lobular phenotype, but then also something like BRCA mutations, HRD, IDH1 mutations in brain cancers, etc. So we think that this will, of course, not replace sequencing tests, but it could. It's just scientifically interesting to see that you can basically see the genotype in the images, and also I think there's a role for these things in clinical decision workflows, ultimately for pre-screening or for offering simpler tests, or maybe ultimately for multimodal tests. One of the best things about these methods, I think, is the fact that they let us visualize intratumor heterogeneity. So this was a beautiful work done by Chiara Löffler, who's a PhD student in my lab, who's here in the audience, and she showed that you can predict FGFR3 mutations in bladder cancer just from H&E pathology slides, and this is a druggable mutation, so we really care about this. And Chiara found one tumor in her data set that had a very striking pattern. So the tumor was predicted to be mutated in the top part, but it was predicted to be wild type in the bottom part. And this is what you can see here in this heat map, and we actually confirmed that by sequencing. And so this means that these methods can really inexpensively visualize the intratumor heterogeneity, which would not be possible by bulk sequencing methods. And one of the biggest bottlenecks that we encounter is always data availability. We need hundreds or thousands of slides to be able to train these things. One potential way to mitigate this is decentralized learning, for example, swarm learning, which means you can collaborate with multiple hospitals that don't have to share their data between each other, but you basically train an AI model at each hospital, and during training, these AI models synchronize and then in the end you get one big model that's as good as a model that has been trained on all the data in just a single location. We showed that this is feasible in a publication last year, and now this is the basis for a EU-funded consortium that we have together with Raquel, who's also here, on the topic of breast cancer detection in MRI, screening MRI scans. What we found is that this is maybe not the ultimate solution for all of our problems, because setting up this swarm learning infrastructure is quite challenging. So it can be the right tool in some situations, but in most situations, you probably want to share the actual data for centralized analysis. So to sum up this part of my talk, why are we doing AI-based analysis of histopathology slides? Well, we are aiming for two things. We are aiming for clinical biomarkers, but also we are aiming for scientific discovery. And I think this makes these methods very attractive for use in many contexts. So let me speak in the last couple of minutes about multimodal biomarkers, because that's the topic of this session. And also I'm very hyped about this, and very excited. From a clinical perspective, it makes sense to not just look at images, but to incorporate different types of data. I mean, that's what we always do when we treat patients. And so it really makes no sense to have an AI system that only looks at the pathology slides and expect that to come up with like universal solution for your clinical problems, right? So it makes sense to look at different types of data because they're obviously complementary, but we somehow have to approach this topic with a bit of caution, because already 11 years ago there were big hopes for such multimodal AI approaches in the IBM Watson program, which was very hyped in 2012, so a long time ago, and promised to solve many problems in oncology by just AIing every type of data that's available, right? But this program failed after a lot of money was spent on it. So so people are a bit cautious in this field, and rightly so. But in the last maybe 2-3 years, we have seen what I think is some solid scientific evidence that shows us that these multimodal methods can really work and can really extract clinically actionable knowledge from different types of data. And some of the most important papers in this field were published by Saurabh Shah's group at Memorial Sloan, for example, this here on the multimodal data integration in ovarian cancer, where they showed you do get a synergy if you combine CT radiology images. First author is also here. So very prominent people here today. That was one of the landmark papers in this field. And also kudos to you that you shared the actual data and the actual images, which is great. And we've been reusing them, and it's this is how everybody should do it. So really important publication and piece of evidence. Now, we have seen some other similar publications, for example, by Faisal Mahmoud's team at Harvard, and our own group was involved in this study where we combined different types of histopathology images, immunohistochemistry plus H&E, putting it together into one giant deep learning model that was able to predict treatment response, relapse, and survival in colorectal cancer. So there is some evidence out there. And nowadays the methods are becoming much more fancy. Even this is a recent preprint by the Harvard group, which I was which I think is great, combining genetic data and morphology. Of course, now we have in many parts of our society, we have tremendous progress. We are observing tremendous progress in AI, and one of these parts is, of course, ChatGPT, GPT-4. It was mentioned today also. So we are seeing that these models, that multimodal AI models, are becoming more mainstream, And this is just an example of the Microsoft Bing Assistant, which runs on GPT 3.5, I think in this case, that you can basically converse with that in a chatbot-like way. You can ask it which are histopathological features of MSI colorectal cancer. It will give you a list, and then you can ask it to create a histopathology image that shows these features. These images are pretty bad, so this is not really helpful here. But I think we see where the field is going, and now with ChatGPT 4, we are seeing really tremendous progress in the capabilities of logical reasoning, but also factual knowledge that these models have. And this is just an example of where I put in like a clinical question with a lot of expert jargon into ChatGPT 4. So this is, I put here a question. I have a liver cancer patient in a certain disease stage. Should I give them immunotherapy or tyrosine kinase inhibitors? Is there clinical evidence? What are the pros and cons? And this is the response which I got. So the model ChatGPT 4 gave me a really nuanced answer here, citing the appropriate clinical evidence and telling me that I should use immunotherapy because that's where the current medical evidence is, but also which are the pros and cons of both types of treatment. So these things are really starting to work really, really well. And why am I talking about this? Because GPT-4 is a multimodal AI model that can integrate text and images. Well, not the public version, we still cannot access that, but they have this, OpenAI has described this internally. So you can give the model images and text and ask it to interpret the images in the light of additional information which you provide by text. And this is really just completely mind-blowing because this was completely unimaginable like 2-3 years ago. And so here we are seeing a big technical advancement in terms of multimodal models. In this case, this means text plus images. That's just totally mind-blowing. And of course, this is obviously relevant for medicine, and many people have picked up on that. There was this recent Nature paper published by some Twitter gurus and key opinion leaders from Harvard, where they, which is great, and I love this paper for the concept and for the visuals, because they conceptualize how we can use these multimodal models in the future for medical decision support. And this is so this will, what they argue is that this will enable us for the first time to really integrate diverse types of data into one prediction. But we can do this not just in a single specialized field, so let's say in orthopedics or in lung cancer, but in anything. Like this can order a pizza for you, but it can also interpret the chest CT scans of your lung cancer patients and prescribe the appropriate treatment and alert you of some imminent complications. Or so this is really and just 2-3 years ago, again, this would have been completely science fiction, right? But now this is still not reality. We don't have these models yet. This is just a concept. But I think these advancements which we have seen in GPT-4 show us that this is probably going to happen in the next in the near future, like in the next 1 or 2 years. And for my own academic research, I'm questioning myself, we can probably not proceed to publish niche models on lung cancer, on ovarian cancer, on histopathology, on radiology for the next 5 or 10 years. We have to go to some more generalist models and apply them. But this is really an exciting time to be alive. My very last slide is that sometimes we have to be careful with these models, so they can go completely crazy. Sometimes they have emergent behavior that you cannot foresee. So in one of these early versions of ChatGPT, they didn't do the censoring and the domestication basically correctly. They just shipped the early stage of the model to Microsoft, and Microsoft included that in its Bing search engine. And then it turned out that this model that they had, this chatbot, had a really weird personality and was like going completely crazy on an emotional level, hallucinating a lot of stuff. So these models, without the appropriate safeguards, can do really funny funny stuff. Of course, we don't want that in a medical AI happening in a medical AI model, right? So we have to be a bit mindful here. But yeah, the bottom line is the future is going to be very exciting, and let's try to keep up with this and use these tools for our research. And I'm very grateful to my team in Dresden in Germany. This is an old photo of the team. We have grown a bit since then. We are quite interdisciplinary. We have medical doctors, physicists, computer scientists in our team who collaborate. We always have open positions. If you want, if someone wants to come for an internship or do a PhD with us or whatever, please reach out. And yeah, also thanks to the organizers of this conference and all the fantastic faculty here who we collaborate with a lot. And now I'm looking forward to the questions. Thank you.
Thanks so much. I invite all the speakers here in order to discuss and to answer the question. And please, if there are questions from the floor, don't be shy. Yeah.
Thank you very much. You showed that you can go from a phenotype to a genotype easily, but if you integrate more data and very complex data like the single cell RNA-seq, can you still do the same? Because in general, what you want is to have easy data to produce, to have the information you need, because you cannot realize the single cell RNA-seq for all the patients in real life.
So if I can briefly answer this, in my group, we only work with routinely available data like CTs, MRIs, H&E slides, immunohistochemistry slides, bulk sequencing, and we really need hundreds or thousands of cases to train the model. So I'm not using single cell data, but I think Saurabh can comment on it.
Yeah, I think for now we view single cell as a tool for research and to make biological discovery. This is why it's on the right-hand side of my my slides there. And so I think projecting the phenotypic state information that's inferred from 25,000 genes measured in a single cell into an H&E is going to be probably an impossible task. I don't think we will get to diverse phenotypic states that can be inferred from histopathology data. I think that's probably just it's a cross-purpose type of activity there. So I would say that at least today, the current state of the art is that single-cell RNA-seq is a research discovery tool, and I think where we can probably train useful clinical models is firmly in the H&E space, where we have hundreds of thousands of examples. Yeah.
Any other question from the floor? I have one question for Jacob. You said that MSI test with the artificial intelligence and machine learning was at a high sensitivity, but not so high specificity. So the false positive rate was still high. So do you think that in the future this can be improved? And also, how do you think that machine learning technique can replace or must integrate the normal testing for MSI or for other pathological biomarker?
Yeah, thank you. Excellent question. I think the performance we are seeing that the performance is going up. So every month we are using a new model, a new transformer model, and we can see we can squeeze out maybe 0.01 ROC points by using better models. But of course, there's a limit, right? And we will never, for example, for MSI, we will never be able to perfectly predict the ground truth. Also because the ground truth is not perfect, but these are difficult discussions. I don't think we will be able to replace all of these tests, but there are some tests where I think the phenotype could even be better than the ground truth tests. For example, HRD, homologous repair deficiency. There's like a bunch of different tests out there that people are using. None of them is perfect. None of them is ubiquitously available. Most people just use BRCA1, BRCA2 mutations, which is a very poor surrogate for HRD-ness. But what we are seeing is that there's a strong phenotype associated with HRD. So maybe in these cases, the phenotype would be even more predictive of the ultimate drug response, and more predictive than these diverse genetic tests. So this would be an example where maybe the phenotype based information could be more useful clinically. What do you think, Alex?
Yeah, I was gonna add that, you know, digital biomarkers are just biomarkers, right? So just like anything, any test you develop, you can determine where you want the sensitivity or specificity trade-off to be. You know, there's always a threshold you can set. And so for some decisions clinically, we want a highly sensitive, and other decisions we want a highly specific biomarker to accomplish our task on behalf of our patients. So we you know, I think that we have those same the same ability to do that with even as the performance overall improves, we can also tune it to a specific task. And so, so I think that it's just to keep in mind, I think all of the good practice principles for biomarker development exist for a digital biomarker, just like they exist for a standard chemical biomarker.
Thank you.
So I had a question for Professor Shah. In particular, I mean, we are all hoping that AI can answer a lot of questions, especially regarding the feature of immune-responsive tumors. So from a clinical point of view, we all know that tumors can be binary, classified into hot and cold, but we do not really have biomarkers. And I mean, after your presentation, I was still thinking about the difficulty in translating all these in the general clinical practice, as you were also saying, because we don't have the same data from all patients in all institutions. So one question was if you have an idea on how do you foresee the developing of these techniques, looking more closely to the general clinical practice? So I don't know, how can we move? And second, if you think that there is something that we can also use from liquid biopsy, because we have a lot of tumor types. I was just thinking about this, for example, lung cancer, small cell lung cancer, in which we do not have a lot of pathological material, and now we know that from pathology we can have a lot of information. So there is maybe something that we can also learn from circulating tumor cells and immune cells from periphery.
Yeah, okay, that's a lot.
Too many questions.
So on the first point, I think that what we need to be doing is prospectively collecting the data in digital form, so that 5 years from now, we actually do have the scaled information to use the latest and greatest techniques, which are going to be far better than today's, which is kind of scary, right? But I think that's probably the approach. And so all of the work that we've done, and probably Jakob and Alex have done, is like retrospective look backs. We take data that has been collected in the provision of care, and we have to annotate it and clean it and look for data sets that we have complete information, and then execute a study. And there's an attrition rate with that. Every time we sort of layer on a new type of information, and then we lose patients because we don't have the information in others. So I think if we make concerted efforts to encourage the systems to collect the data as a part of provision of care. Of course, the systems are worried about caring for the patient. They don't care about 5 years from now whether we have a good data set to do research on. But if we can convince the systems to do that, that's probably a logistical solution to what you're asking about. And because I think logistics actually are critical to success to get the scale. In these models, large language models are successful because they trained on the entire internet plus other information, right? So that's all information that we know about in human history. That's what these models are trained on, and that's how they can be successful. So We're never going to succeed with 247 patients, as you point out, but can we succeed with 10,000 patients? Maybe 100,000 patients, probably, and million patients, and that's probably where we need to get to. So, so I think that's probably, and to get to 1 million patients, multiple institutions around the world need to systematically collect and encode this data. So, yeah.
Thank you. Thank you.
We have time for 2 more questions. There is a question from Leonardo Provenzano.
Hi, I'm Leonardo Provenzano from Oncology Fellow in Milan. A question from all of you. We talked a lot about multimodal integration to create a model, but there are some effort on intermodal integration. I mean, between radiomics and pathomics, for example, or to reach a phenotype, a radiomics phenotype from RNA-seq, for example. Thank you.
I think the question is how to integrate multimodal like radiomic and pathomics.
I mean, there are any studies comparing radiomics with pathomics. So found some features we can find in on an image that are correlated with some feature finding on the slides, for example. I don't know if there are any efforts in this.
I think I'll take a stab at that. I think what we've been interested in is looking for correlations, but also looking for anti-correlations of features. So where we have complementary information, where in some contexts, let's say radiologic features are predictive. In other contexts, it's actually histopathology features. So learning those contexts where to apply and reweight the features is, I think, an important area of study that I think is just beginning now, where we're starting to learn the context. It could be that in HRD tumors, in ovarian cancer or other tumors, then histopathology information may very well be helpful. But in the non-HRD tumors, what do we do there? And if the signal is not encoded in the histopathology data, perhaps it's encoded in the radiology data or visible in other molecular information, for example. Kevin's work, I think, starts to get at that question. And then I think the other maybe relevant comment to make is that even within major cancer types, like in breast cancer, clinical designations by hormone receptor subtypes, we see that the models, even though we have histopathology, radiology, genomics information on all tumors, within or between the hormone receptor subtypes, the models behave differently. And so what is driving that? And that, I think that's an open question, and I think is really interesting. I hope that gets at yeah, okay, all right.
Last very quick question. Giuseppe, you had one. Sorry.
I have just a comment. Maybe I'm going to bore you, all of you, but I thought a bit about the example that Dr. Persson showed of the classification of the ASCII, and so that what was wrong in the black box. Actually, I believe that that image is even more didactic that of what you've shown, because actually in that case, the problem is actually the heterogeneity of the data that we are given to the system, because we are always given ASCII in the snow, and that's a problem. We don't get any information if we give some kind of data from clinics, while it represents, the snow can actually represent something more interesting, because in some way represent the progressive knowledge that we have, and it's something that we have to defend and we have to include when we use this kind of sophisticated model. We need to include literature information, clinical practice, and the snow is something that can help in detect, but it's not just that. And yes, so just to say something about
I guess I'd argue that the analogy fits, because all of the data, unless we do a full census of all individuals in every country, all of the data will always be wrong. They will always be incomplete, and there will always be biases. So if you can at this moment train an AI model to predict a patient's racial ancestry directly from their path slides, and you will be 95+% correct from TCGA data, because all of the African American patients came from Chicago and all of the Asian patients came from the Bay Area, and that there are signifiers in those slides, just like the snow in the example, that are pervasive and that a lazy algorithm will find. And so, I think the point has not been made strongly enough that the quality of the data and the quality of the annotation is absolutely imperative. Just like so Sydney doesn't get angry at us because of the training of ChatGPT from all of the angry rantings on the internet. I think the same curation concept is even more, well, maybe not more, but it's appropriate for clinical models as well. Thank you.
Okay, thanks so much. We are 7 minutes late, so we close this session. And thanks to all the speakers for the excellent presentation. Thanks so much.
Hi everyone, I'm Sokol Costa. I'm associate professor in computer science from University of Aalborg in Denmark. I'm going to introduce this session 4, which is about adapting data storage models and regulatory frameworks to the AI paradigm. And it is a pleasure for me to start this session with Professor Robert Grossman from University of Chicago. He has a past as mathematician, from what I read, and then he's a data scientist. And lately, since 2010, he's a data science within the topic of biology, health, and environmental. He's also director of the Center of Data Science in the University of Chicago. Thank you.
Thank you. It's an absolute pleasure to be here. It's a wonderfully organized conference. There are wonderful researchers and others here to talk to, and I'm just very happy to be here. I'm going to talk, what we heard, what I heard so far today is if you have good data, you could build good models and impact patients. We talk a lot about data, but we don't have very much high quality data, or as much as we would like. So I took a little detour and spent about a decade building data platforms to make it easier to collect high quality data and to curate them. They're called data commons. I'm going to talk a little bit today about what a data commons is, how you can build one, what make them. Just because you could build one doesn't mean you're going to build a good one. So what makes some good and some bad, and then importantly from the last few talks, how you could use them as a basis for federated and swarm machine learning so that you can get more data. I have no relevant disclosures. So I'm going to talk briefly about a data commons that has a lot of cancer genomics data. Then I'll talk about how you might build one. So we stood up about in 2016 something called the Genomic Data Commons. It had a very simple premise. The premise of it was that if the NIH, National Cancer Institute in the US funded your work and you produced cancer genomics data, you would have to share your data with the Genomic Data Commons. So it was an interesting unit. It was the first time they had done something like this. If they fund you, they can tell you what to do with the data, and they told you to share the data, and they needed a platform and I'm going to describe the platform that was built. So the unit here is all the data funded by the National Cancer Institute that produces cancer genomics data. It has about 5 petabytes today. In a couple months, we're going to add another 3 petabytes, so it's about 8 petabytes. It will be about, I guess we're going to add 4, so it'll be about 9 petabytes of cancer genomics data. It's widely used. It's used by over 60,000 researchers each month. Over 2 petabytes of data are pulled out. All the work is in curating and harmonizing the data. Harmonizing here means running a common set of bioinformatic pipelines on them. So we run about 25,000 pipelines each month so that we can uniformly process all the data. And it's all open source, so if you want to build one, you could build one. I'll echo what others people say. You know, studies, not well-constructed studies, but studies show you'll live longer if you use open source software. So I want you to consider that. So this is what it looks like. You can sort of explore the data. You could build survival curves. You could do all sorts of things with it. You know, people look at it and they forget that, you know, we have a data model. We curate everything with respect to the data model. We call the projects, and if they don't give us enough information to align it with respect to the data model, we bug them. And, you know, people, you know, if people ask you in Chicago, we're so polite, they always tell us how they did the data so we could curate it. Then we run a uniform set of pipelines on it. Here is a you know, classical Venn diagram of the overlap of the mutation calls. And again, our unit is all the data, so we harmonize all of it and then we make it available. And then we encourage other people to build applications over this. They're the so-called APIs. They are what are called FAIR. They make the data findable, accessible, interoperable, and reusable. And everything we do to visualize and share the data is over the APIs. And then we make the APIs, the same APIs available to anyone in the world. So anyone in the world can build the same kind of applications, do the same data analysis, do swarm, do all sorts of federated learning over the data. So I didn't know what I was going to talk about, so I looked at the title of the session. The title of the session told me to talk about platforms, so I'm going to talk a little bit about software platforms. So here are 5 things about the Genomic Data Commons, which are relevant for the next piece of the talk. So it has a data model and it holds structured data. That's very easy to do. Genomic data can be large. You know, all the non-genomic data is measured in terabytes. The genomic data is measured in petabytes. So we have a so-called data lake model I won't go into, but in a data lake model, you take an object like a BAM file or images or other things, and you store them in a cloud computing infrastructure, and you do it in such a way that it's easy to move and retrieve. There's no standard name for this kind of architecture. It's been used for a while. I call them data hybrids. A database, you know what it is. It's for the structured data. A data lake is what I just described. When you integrate in a fair way databases and data and cloud data lakes, I call them data hybrids. So it's sort of well known. It came out of Europe, sort of this passion for fair APIs. And then harmonization, I've already described. Harmonizing at scale can be very expensive. Again, luckily the National Cancer Institute committed to this, but we run hundreds of millions of core hours each year to harmonize the data, and then it has a scalable interface to make it pleasant to use. I'll come back to these. So I'm going to talk a little bit about the idea behind the data commons. I think of it as a unit for sharing data and for supporting well-curated, harmonized data and contributing to a federated infrastructure. it was hard to build the Genomic Data Commons, so we created some open source software called Gen3. We now have over 25 of these. They include other large cancer sets, the cancer data from the US Veterans Association, a liquid biopsy commons that came from the moonshot in the US, and others. And the goal is to, people are building these around the world, and we're trying to get 200 of these over the next couple years. If you can interoperate multiple structures like this that you and other people built, so built by different organizations, and in many places, any organization is always right, and all the other organizations are always wrong. And they don't like to share, even though they say they like to share. So how do you federate data in a situation in which everyone in a separate organization builds their own infrastructure? That's called, at least when we do it, it's called a data ecosystem. And these all form a data ecosystem, and they have a particular type of governance I'll describe. So that's what I want to talk about. This particular data ecosystem here has 1.6 million subjects, over 100 million objects in its lake, and over 17 petabytes of data, but they could all interoperate. But each organization decides how they play with the others, what they share, whether computations are only done inside or data could be shared, and you have knobs to choose. So I'm going to look at a data commons from three perspectives. The first perspective is from a data management perspective. And in most disciplines, as you get older, you get grumpier, and you think there are fewer and fewer ideas, and people are just using older and older ideas with better marketing. So if you look at data management from that perspective, there haven't been that many new ideas. One were databases, and databases like the Protein Data Bank and GenBank are extremely good ways to organize data for a project. When you have data for an organization versus a single project, a large organization, it's much harder, but data warehouses sort of gave us that perspective. A data commons takes the viewpoint, if you have a research discipline and you want to share the data while respecting privacy and security, what would that software as a software platform look like? So what's the software platform for a research discipline to share data? And an ecosystem is when you have multiple of those. And so from a data management perspective, that's what a commons is. And then from a public good perspective, there's a whole nother view, and this is around governance. And Elinor Ostrom, she was the first woman to win the Nobel Prize in Economics. She won it in 2009, and she spent a good portion of her career looking at how do you govern a commons and what's the economic value of data and how do you respect that. So a commons comes from this old idea that if you have a village, say, and you have grazing land, how do you make sure that that grazing land is fairly used as a resource? It's something collectively owned by a collective for the benefit of a group or of society. And how do you make sure that bad behavior, the so-called tragedy of the commons, doesn't impact the ability to do that? And so fisheries and cows and grazing land are examples of commons. Her book, Governing the Commons, is a way to think of this from an economic perspective, and a data commons is a way to sort of share this data. And finally, social media platforms, Uber and Lyft and platforms like this are an example of something called a software platform, which is something very, very specific. It was described in an article a few years ago in Harvard Business Review. It has 4 essential features. It has people, say, contributing data, people using data, say, researchers. It has an operator, people like us who build it, and it has a platform owner. And in research, we don't talk about owners, we talk about sponsors of research, but it's essentially the same thing. And so that's a platform is a very, very important way of thinking of how to build scalable systems for working with AI data. So I wrote a paper of, I think this year, that looked back over a decade of what made Commons successful and what made them not so successful. And one of the most important things is the curation harmonization of data, so the data is actually usable. There's a number of important differences between data commons and repositories and what in Europe are often called or were called virtual research environments. They share some characteristics. They overlap in ways, but I've highlighted the FAIR APIs, I've highlighted the cloud computing, and I've highlighted the importance of curation and harmonization of data. And until you curate the data, you don't understand it. Until you analyze it, you don't understand how you curated it. Until you build a model, an AI model, you don't understand what you don't understand when you analyzed it and curated it. So it's easy to talk about curating and harmonizing data, but until you do a new analysis, you don't understand what you didn't understand. Think of Alex Pearson's example of data from Chicago, TCA images from Chicago versus San Francisco. For your notes, I've summarized some of the differences between commons, ecosystems, which are multiple commons, virtual research environments and repositories. You don't have to read this. I just wanted you to have, I didn't want to be accosted later saying I didn't define these. So I'm going to take the last 5 minutes and I'm going to talk about how you can sort of do federated machine learning. And I'm taking a very, very general view of federated, which is when data is in separate locations under separate organizations who have a governance structure that allows some types of interoperability. So that would include swarm and all sorts of examples. In software, again, I'm talking about software because I read the session title. In software, we have stacks. So the stack I'm going to talk about is a data platform, which I've given an example. And then there's contributed data. These are from projects that collect collect oncology data. Then you do AI, and then you get something out. So that's the stack. Now, if you're a researcher, you're sort of done with that stack. If you lead an organization, you ignore that stack because you trust your researcher understands that stack. And what you're going to think about is what is the data governance? What is the platform governance? What is the organizational governance? What is the regulatory framework? What's the privacy framework? What's the security? What's the business model? And what's the sustainability model? And you can't federate data. And indeed, you can't keep a software platform unless you know the answer to each of those questions, unless you have standard agreements, and unless the agreements are compatible. So what I've sort of done for the last decade is think about the left-hand side, try to stay away from the right-hand side, but get sucked into the right-hand side. And then if you do that right, you can federate. So this is the same picture. This is a federated view, but I have 3 organizations. And there are not that many, if you think about why the internet works, well, I'm assuming the internet works. Whether it works or not is another lecture. But if you assume the internet works, anytime we get a new type of data, whether it was images or images or video or streaming data, if you noticed it, we never changed the routers and switches and all the underlying platforms in the internet. What we did was we have a design so that we can add new data, add new applications, and nothing changes. There's a technical approach to that. The goal is to build your application over a very small number of services, in this case, HTTP and TCP, so that you can live with this for 20, 30, 50 years. So the way data ecosystems work, the way we use them, is to have a very small number of services. They haven't changed for us in a decade, even though everything has changed since then, from Jupyter notebooks to large language models. Nothing of that. And those are the blue arrows. Those are called mesh services. There are a number of standards out there. So our software, which is open source, other people's software can interoperate. And so there is what's called a hybrid governance model, in which the organizations do almost 90% on their own in terms of their governance, but there's a consortium governance for federated learning where you agree on the mesh services, you agree on a small number of things of sharing data, and you can interoperate. So this is a busy slide, but it says if you take this approach, you have a lot of knobs. One knob is whether you ship the data, that's on the left. The other knob is whether you shipped a request for a computation, ship a container, ship a query, and return results, return counts. I won't go into details, but each of the contributing organizations can have their own data model. Then there could be a transfer model. So you don't have to agree on a model, because there's not enough time in the world for everyone to agree on a common data model in oncology. And so this is the same thing, but it just says, what are the knobs? Do you ship queries, counts, workflows, containers? What's returned? Yes, no. Say for the BRCA discovery mechanism, the beacon mechanism, counts for cohort discovery, the output of a model, or the model itself. And then I'm not going to go into this, but how do you scale this for a single organization, a single player like Apple or Alpha Health Kit or Google? I think we're going to hear a talk about this, where you have to take consumer level information. Here it's not federated, it's a single entity like Apple. And then how do you feed that up into something? And you could do data mining on something like this. And those are the references. I'm right on time, so I'm not going to feel guilty. So thank you.
Thank you, Dr. Grandi.
Thank you.
Very nice and interesting talk. So now it's a pleasure for me to present and introduce the second speaker, Emilia Ambrosini. Emilia Ambrosini is a bioengineer, is assistant professor at the Politecnico in Milan. Since 2011, he has been working at NEAR Lab, the neuroengineering robotic system labs at Politecnico. Thank you, Emilia.
Thank you very much, and thanks, Arcela, for inviting me to be here today. So just let me get familiar with, okay. So I'm a little bit an outsider here, but you have all well explained how artificial intelligence can really reshape the landscapes and the horizon of oncology. But what we need is a roadmap for a responsible machine learning system in healthcare. So in a recent paper published in Nature Medicine, they tried to outline a roadmap, a responsible roadmap, which actually starts from choosing the right problem, which doesn't mean selecting just good data, but also really thinking if, so good labeled data, which is often the starting point for a researcher, but really finding relevant clinical questions. Then developing a useful solution, considering the ethical implications, and then this is something that will be covered next. And then how to evaluate and reporting our results, how to deploy these results responsible, and then how can we reach the market. And actually, I tried to give some hints on this last point. So, which are the already approved devices? That was already mentioned before, but there are some devices, some AI devices which are already approved. And this was a systematic review recently published, which actually focus on FDA approved devices that already enter the clinical practice in oncology. And what we can see is actually the majority, I would say more than 80% are for diagnostics and mainly for radiology and pathology, as we have heard. And the majority, of course, targets general cancer and breast cancer, which are for the highest incidence of this type of tumors. That was actually just based on FDA, so devices which are approved in US. This is try to summarize a little bit the situation and compare the situation between US and Europe. In the US, you have a centralized organization, which is the FDA, which is responsible for the regulatory framework. So there is a centralized agency, while the situation in Europe is much different because each member state has its own accredited private notified bodies under the same umbrella, so the same regulatory framework. But this makes things a little bit more complicated in Europe. In the US, there are 3 types of pathway that needs to be followed. So there is the pre-market approval that is needed for the highest risk class, so the class 3 devices. And these are more stringent, and clinical studies are needed for demonstrating the safety and the effectiveness of the device. Then there is the de novo pre-market review, which is for lower risk devices. And then you have the 510K pathway, in which basically you don't really need a pre-market approval, but you just need to compare that your device is similar to previously approved device. The situation in Europe is a little bit different, but I will explain this more into the detail. What I want to highlight just here now is that currently in the US you have public access to the document, and there is a unified database in which you can find the list of all approved devices, while this is not available so far in Europe. So in this review, they made a comparison between numbers of approved devices in Europe and the US, focusing between 2015 and 2020, which is already very, very old, but just to give an idea. And so there was more devices approved in Europe than in US, but the number were very similar. And most of it, so this is not just speaking about oncology, this is more generic about AI-based medical devices for many other, for different applications. And the majority anyway was for radiological use. About this, about more than 100 were both approved by US and in Europe, and these of course are the one from more, let's say, not like small company, but bigger company. And 80 were firstly approved in Europe. So this somehow, so the end of this review more or less indicates that in Europe there is a less rigorous approach, and that the decentralized evaluation makes things easier to reach the market. But this was the story up to 2020, because Europe is now in a transitory period between 2 regulations. So the new regulation came actually already some years ago. It was published in May 2017. But become applicable just in May 2021, and actually new rules, so new devices need to be completely fully compliant with the new regulation just in May 2024. The new regulation introduced an increased clinical investigation requirements. So they put a lot of emphasis on this. So clinical data are really needed in order to get the market, and an increased importance of the risk management. Also, they increase the surveillance and management on the entire medical device life cycle. So we need to care not just up to reach the market, but also what happened afterwards. They also put the emphasis of improving the traceability and transparency. This is something related to what I mentioned before about the absence of a database which summarizes, that lists all the available devices. And also they improved the classification and definition, because what happened up to the previous, so with the previous regulation is that there was a little bit of ambiguity, and then it was easy to put on the market devices with a lower class risk, which was also the reason why there was easier procedure in Europe. So this is a definition of medical device. While I'm speaking about medical devices, while now here we are speaking about software and AI-powered devices, is because actually, according to the Article 1 of the regulation, software is considered as a medical device, even if it's alone. So just a standalone software is a medical device if it's used for human beings for more or one of the following medical purposes, which means diagnosis, prevention, monitoring, prediction, prognosis, treatment, or alleviation of a disease. And these are all the wonderful AI-powered tools that you explained so far are actually following within this definition. Focusing on software, which is something more related to this, to the topic of this conference, a medical device software can be used, as I said, alone or in combination with a medical device. And it is classified as a medical device regardless of the location. So it could be an app, it could be running on the cloud, it could be running on a computer, on a web service, but anyway, it has to be considered as a medical device. And also, medical device software may be intended to be used by healthcare professionals, but also by laypersons. So also if we are developing, so just to make it, so an app fitness to be used for a layperson for improving their cardiovascular activity, this has to be intended as a medical device. So this is the regulatory roadmap for reaching the market for product release. So the manufacturer needs to start from early stages, so considerations. Then he needs to design and development the device. And then he needs to apply for the regulatory framework. Then he can release the product, but then the job is not finished yet because he needs to still look at the market and perform post-market surveillance. So just start from few definitions. I just try not to bore you too much. So the first thing that is very important is to define the intended use, which is the scope, the reason why we want to use our product. And basically it defines both the disease that we want to treat, the person, so the target users, the operators, the environment in which we want to use our device. And the intended purpose provides a confirmation of the regulatory what they need to apply and the basis for the classification and the starting point for the development activities. Based on the intended use, as I said, there is the manufacturer needs to classify the device. And there are 4 classes from class 1, which is the low risk class for which the manufacturer is basically self-responsible for the product. While the other 3 classes, 2A, 2B, and 3, they need all the documentation need to be revised by an external organization, which is called notified body. And the classification, of course, is based on the duration of use, on the invasiveness, and on the source energy. This is like a schema for the classification just for medical software. This is mentioned in the rule 11 of the annex. And so starting from the top here, so first of all, when we have defined that our medical device is actually a medical software, our software is a medical device, we need to ask if it's used for a diagnostic or therapeutic decisions. If yes, we are going to higher class risks. And so if then the decision can cause the death of a permanent disability, then it's a class 3 device, so highest risk. If we say no, then we need to decide if the decision can result in a serious deterioration of a person's state of health. And then if you say yes, it's a class 2B, otherwise 2A. And instead, if it's not intended for diagnostic or therapeutic decision, but is intended to monitor physiological processes, then, of course, the risk class depends how vital are our parameters. But as I mentioned before, even if we are not monitoring physiological process, so again, the example of the fitness app, then we are still working with medical devices of class 1, so lowest risk class. Once we have defined the intended use and the class of our device, we can start the development. All the development is guided by the general safety and performance requirements, which is a list of requirements that our device needs to apply. These are a list of standards that needs to be followed during the design and the development phases. But what I want just to highlight here is that all these requirements are high level, but needs to be proven by data. So we need to provide evidence that we have tested these requirements and that we have data to support that. Very important step is the risk management part that is intended to limit any potential harm for the patient, the care provider, and the treatment environment. So, of course, the regulatory cares the patients, but also care provider and the environment. And the risk is basically the product between the probability of occurrence of an harm and the severity of that harm that we may cause. And manufacturers may take the risk under control and should try to implement any type of measures to reduce the risk and to balance the risk-benefit analysis. Regardless of the class of the device, what is very important is that all device needs a clinical evaluation. So this means that the clinical evaluation is the process to demonstrate safety and performance and positive risk-benefit ratio through a clinical evaluation of clinical data. So first of all, we need to define, as a manufacturer, we need to define a clinical evaluation plan. Then we need to identify pertinent data. So this data should be found through clinical investigations or through literature, state-of-the-art, for equivalent devices. Actually, the equivalence route was the one which was followed before a lot, but this equivalence route is very, very difficult to follow within the current regulatory framework, because to demonstrate the equivalence of our device with respect to another, we really need to have access to the technical file of the other manufacturer, and this is very, very difficult. So in the majority of the case, we need to collect data with our device before reaching the market. And this, of course, can take a lot of time. In our case, means that we should run randomized control trial using the high-powered tool that we developed in order to demonstrate the efficacy of this tool. Once the data has been identified, this data need to be appraised. We need to evaluate if we have enough statistically significant data. We need to analyze the data, and then if we do not have enough clinical evidence, we should go back and find pertinent data. Actually, who decides which is the clinical evidence? This has to be decided by the manufacturer again. So this is something that manufacturer choose if it has enough data, which is the clinical evidence, and so on. But of course, this should be strictly linked with the intended use of the device. At the end of the process, the manufacturer needs to provide a clinical evaluation report. Next step, we have the device, and then we need to submit the document in order to achieve the declaration of conformity. And so the manufacturer needs to produce the technical file, which is a list of technical documents with detailed description of the device, evidence used by the device to demonstrate the safety and clinical efficacy. And this file is evaluated by the notified body, by the competent authority, by the European Commission, specially appointed expert in case of very high risk class. So this is a picture just to give an idea of the complexity of the system, of the entity involved. So, the manufacturer is actually here, at the center of this. He needs to produce the technical file, which is a list of several documents, including the clinical evaluation, the risk management, the requirements I mentioned, and the results of the test in order to demonstrate the safety of our device. This is sent to the notified body, which evaluates it, and then evaluate if it compliance or not. If it compliant, then it can, at the end, release the CE marked, and then the device can reach the market. So when the product is released, the manufacturer still needs to perform the post-market surveillance. So he needs to evaluate what happened afterwards. And this post-market surveillance needs to be proactive. So the manufacturer needs to seek for eventual problem. It's not something that should be reported by others. The manufacturer should demonstrate that he's actually checking that what is tested on small numbers is actually proven also on real data. It has to be planned. So the plan of the post-market surveillance is something that should be delivered before reaching the market and should be based on the risk class of the device. Before I mentioned that there wasn't in Europe, there is not in Europe so far a database reporting all medical devices. Actually, this is something that was introduced by the new regulation. So the EUDOMED, so the European database on medical devices, was introduced by the MDR 745. And this will provide a living picture of the life cycle of our medical device. And this will touch several domains, from registration of manufacturer, of devices, of certificates and notified body. It will have a module about vigilance, so reporting serious incidents, corrective action, about market surveillance, so which measures should maybe are taken by member states or devices that were not compliant, that are not on market, and also about clinical investigation ongoing. The timeline, so this is not ready yet. Actually, it was planned to be ready, but this timeline was already shifted in time. And these 6 modules should be developed by the end of this year, but will be fully functionally by mid of 2026. Just to conclude, to sum up, what I wanted to with this presentation is actually that US has a centralized regulatory agency, which makes things a little bit easier for manufacturer to get the market, to reach the market, while in Europe there is this unified regulatory framework, but then each member state has its own authorities. EU is in a transition period which is actually very, very, very slow. It has been made even slower by the pandemic. And so if you see the timeline that I mentioned before, if the law was published in 2017 and it will be, and devices needs to be fully compliant to that 7 years later, this is a very, very long time. Technology is much, much faster than law. So this is actually the take-home message. And so probably this framework will be old, is already old for the devices that you are developing right now. And also, so far, there are no specific regulatory pathway for AI-based medical devices, neither in Europe nor in US. There are some, let's say, guidelines, some action plan, both in the US and in Europe, but this is still under discussion, so there is still not a regulatory framework specific to this. And probably, I mean, we are very, very late in that from a regulatory point of view. Thank you.
Thank you, Dr. Emilia Ambrosini, for your talk. Okay, thank you, Emilia, for your presentation. And it's a very pleasure for me to introduce the next speaker, Elisabetta Biasin. She is a researcher in law at the Q Leuven Center for IT and IP Law, where she researches on privacy and data protection, cybersecurity, and health law. She's also an expert on data protection of big data and real-world data at the European Medicine Agency, EMA.
Thank you very much, and good afternoon all. It's really a pleasure to be here, and thanks Arcela and all the organizing committee today. So I'm happy that you already introduced myself, so I don't have to introduce what we do at at our research center. At the research center, we are dealing with ethical and legal aspects of AI, and especially in healthcare. So my research is also related to AI in healthcare. Today, my presentation will concern cybersecurity of AI-based medical devices. I will give a brief introduction of why is cybersecurity really relevant for AI-based medical devices, what is the regulatory domain at the moment so far, the EU legal framework and the MDR, the other pieces of cybersecurity legislation, and some ethical aspects to consider in cybersecurity. And I'm really glad that there was a firmer intervention about the medical devices, and also I couldn't agree more with what was said before about the regulatory pathways for AI and medical devices. But the focus of my presentation will be really specific to cybersecurity. So why cybersecurity is really important? So we have seen in last years, especially during the COVID-19 pandemic, how important is to preserve security of networks in hospitals. We saw ransomware in hospitals, and especially we saw, for example, cyber attack at EMA. The ENISA, the European Union Agency for Cybersecurity, highlighted as well the urgency to tackle cybersecurity in healthcare. And before 2017, this wasn't perceived as much as important as it is now. And also what started to be more and more discussed was the possibility that certain medical devices, such as pacemakers, could have some vulnerabilities that needed to be communicated in order to tackle those vulnerabilities, so that no malicious actors could take these vulnerabilities and take advantage of these to undergo to malicious actions. And this is no less true for cybersecurity of AI-based medical devices. When I'm speaking about AI-based medical devices, and I'm really reconnected with the former presentation, I'm talking about software as a medical devices or medical device software. There is a difference in the terminology because medical device software is the terminology that is being used in the EU. So just to give a couple of examples, what are the common threats for AI-based medical devices, so applications in healthcare that use AI. In a recent paper that I wrote with my colleagues for a research that we are doing, and we are comparing EU and US AI cybersecurity, we found three main common threats for cybersecurity of medical devices. One is data poisoning. So for example, you poison the data set and the data that are being used for inferences are being corrupted. And for example, in clinical decision making, it means that there could be inaccuracies that could be also leading to inaccurate predictions or inaccurate diagnosis, depending on the field of application. So it's really important that a lack of security doesn't imply a data poisoning. But also social engineering is something that is increasingly being used through AI, and social engineering is also capable of bringing threats to healthcare IT networks, including medical devices. Another common threat is the extraction of data or source code of medical devices, with which a malicious actor could use to, for example, steal intellectual property if they are not using open source software, or to take advantage of certain data and to reverse engineer the software. But this is a little bit the common threats, but what about the current regulatory framework so far? So it's a very recent matter, internationally wise, at the IMDRF, which is the International Medical Device Regulatory Forum, which is composed by a different composition of states, which have different roles in the decision making of the body. But it is an example that is making a authoritative guidance through, on a worldwide basis. And the first document, it includes the principles for medical device cybersecurity, and it was issued only in 2020. But we are not having medical devices that are connected since 2020. I think it's a bit more. But I think this says a lot about how little was the attention to cybersecurity before. And after this, this guidance was followed by a principle of practices of legacy medical devices, which means in this guidance, these are meant as those medical devices that are a bit old, and those, let's say, old features could imply vulnerability. So this is a guidance to tackle those devices and say, okay, what can we do if they are vulnerable? What can the manufacturer or the hospital do? And then the third guidance is under consultation at the moment. There are national guidances that were issued in the last 5 years on medical device cybersecurity. So in Japan, in China, Germany, Canada, Australia, Brazil, there is an initiative in Saudi Arabia, but also in France, etc. But the first one was issued in 2005, whereas in the former you could see that it was very later. It's 2017, the first one, and it was in the US with the FDA, where the FDA, Food and Drug Administration, issued a general principle of networked medical devices containing off-the-shelf software, and then further guidance followed. Okay, so that was the global situation to ensure cybersecurity of medical devices. But what about Europe? What about the EU legal framework? So in a recent piece of research that I carried out with my colleague Kamenjasevic, we found the first piece of legislation that contains cybersecurity requirement is the medical device regulation. And here I'm focusing only on the medical device regulation, but there is also the in vitro medical device regulation. But that's not all. We have a lot of other pieces of legislation that contain cybersecurity requirement, and that they are likely to cause an headache soon to security officers in hospitals and medical devices manufacturers soon. So there is the NIS directive, which concerns the network and information system security, which is applicable currently for healthcare hospitals, simply put, the Cybersecurity Act and the GDPR, which you might be familiar with as well. And then there are other proposals that are going to introduce cybersecurity requirements. So the AI Act, which was mentioned before, the Data Act proposal, indeed, it's a quite hidden requirement, but it's there. And also the European Health Data Space proposal. In a former session, we discussed about secondary use of data, which is gonna be tackled by the European Health Data Space, but this regulation also includes security requirements for specific devices. So just a little bit an overview of medical device regulation. So this regulation does not mention explicitly cybersecurity. So the thing is that at the same time, cybersecurity could be inferred from the safety and performance requirement, which were excellently outlined in the former presentation. And it's about cybersecurity is about also safety and effectiveness, and it could concern software. And cybersecurity should happen across the whole life cycle of the device. In last year, the Medical Device Coordination Group issued a guidance on medical device cybersecurity, which was the first in EU-wide, which took the MDR and IVDR requirements and said, okay, let's see which is the cybersecurity relevance. And it makes a very nice overview of the provisions that deal with cybersecurity requirement, which I decided to draw in this purple table. So as you can see, the cybersecurity requirements, which are contained as safety and performance requirement in the annex of the medical device regulation, concern IT security, information security, and safety, security, and effectiveness. And also, most importantly, cybersecurity needs to be considered in the secure design and manufacture of the device. So it's about risk management. It's about the protection of risks against vulnerabilities. You have to identify threats, hazards, and risks, and implement risk control measures. The annex of the MDR also talks about IT security requirements. Cybersecurity needs to be throughout the life cycle, so it's also about verification and validation, and it is also shall be included references in the documentation and instructions and labeling. But it would be too easy that only the medical device would be relevant in healthcare. So we have the NIS directive, which stands for Network and Information System. And here it applies to healthcare providers, which means hospitals, which are identified on specific requirements. And it includes cybersecurity risk management measures and reporting obligation. This directive is going to be replaced soon by an NIS2 directive, which adds even further cybersecurity requirements and wants also medical device manufacturers to be included. And for example, if there is a security incident, manufacturers or hospitals have to notify the cyber incident to the competent authority. Then we have also the GDPR, which has a very important principle, which is integrity and confidentiality. And according to it, data should be processed in a manner to ensure appropriate security. So you might have been hearing about appropriate technical organizational measures in the GDPR. And when it comes to security, it means carrying out the DPIAs, nominating a DPO, but especially when there is a data breach and you lose data, or the data are they're not available because of a data breach, you need to carry out a personal data breach, meaning that you have to notify to the data protection authority and sometimes also to the data subject. Now there is also the AI Act proposal that will include specific requirements, one of which is cybersecurity for AI high-risk application. Here I won't stop too much about the relevance of AI Act with the medical device regulation, but this is another headache potentially for those who will deal with medical devices. Because it might be uncertain to understand which medical devices fall within the proposal scope. And there is also a minor aspect. There is a serious incident notification in the case there is a breach to a fundamental right, and fundamental right is also health. So if you have a cyber incident that implies specific threats to patients, in my opinion, it means that you will have to undergo to serious incident notification. So this is another requirement. So you will see that there is a GDPR personal data breach notification, NIS notification, MDR serious incident notification, and AI Act proposal serious incident notification. And finally, the European Health Data Space proposal, which is mostly known for primary and secondary use of health data, but it also includes cybersecurity requirements. Currently, I'm analyzing it in order to understand to what extent it applies to medical devices system. In my opinion, it's not clear, but I think it will apply. And it includes cybersecurity requirements for electronic health record systems, which could also consist in medical devices and eye-based medical devices. And it has also rules on the secure processing environment, which is another part that will be very important to be discussed in the future, because it's where the data will be shared. So there will have to be security requirements to ensure that health data are shared in a secure environment. And also, I won't talk too much about the Data Act, but there are also requirements in the Data Act, which is basically a new proposal that also concerns data sharing. It's less specific from the European Health Data Space, because it's not just about healthcare, it's a general one, and it foresees business to business, business to government, and business consumer data sharing rules. Finally, and I think for the regulatory aspect, it's really whole. I thought also to add some ethical aspects concerning cybersecurity, because cybersecurity per se in law, it's quite a matter that is not really discussed very much, maybe because some don't find it as much as attracting. But there are also ethical aspects that I think are really relevant when it comes to cybersecurity. And I think it's nice to analyze, this is an approach that we undertake usually in our research center. We consider ethical issues in healthcare technology by analyzing it from the principles of biomedical ethics. So you might be familiar, for instance, to the non-maleficence principles, which is harm, the Hippocratic Oath, but also these principles consist in respecting the autonomy of patients, beneficence, and justice, which consists, for example, in health equity. And some authors mapped these biomedical ethics principles to some technical aims of cybersecurity. So, for example, the autonomy is connected to privacy and confidentiality, and, for example, beneficence is connected with efficiency and quality of services. And this is an example that happened a long time ago, but still it was quite problematic, the WannaCry example. And this is an example just to bring an idea of the ethical stakes that could be brought by cyber attacks, because once you have a certain attacks to medical devices and healthcare provider, data are unavailable. And when you need to make some decisions and you don't have available data, it means that privacy and patient's autonomy somehow is diminished. There are also other kinds of threats that could be stem for that. So if a medical devices act and data are diffused, that could mean, for example, also that data concerning a certain disease or pathology could be used against them to manipulate them, to discriminate them. So this is an idea of how it's important to consider the ethics aspects. Another example is non-maleficence principle. So a security incident could also have an impact of the principle of maleficence. So if you manipulate a medical device, for example, a brain-computer interface, it could also really impact spatial mobility or control of given devices. These are examples taken in the literature to just underline a little bit what could be, from an ethical perspective, the relevance of cybersecurity. So in conclusion, the take-home message from AI and cybersecurity for medical devices, what I think it's important to note is that cybersecurity in the last years has been an increasing concern for regulatory authorities worldwide, and which resulted in a production of guidance for cybersecurity in the recent years. Cybersecurity is also a matter of ethical relevance. For example, safety harms could be read in the principle of doing no harm, and requires thorough consideration by healthcare stakeholders, being them patient, being them healthcare professional, doctors, device manufacturers, or others. In the EU, the MDR contains already safety and performance requirement with cybersecurity relevance. And I underline again the former finding of the presentation, where there is not yet a ad hoc regulatory pathway for AI-based medical devices. And when it comes to AI and cybersecurity together for medical devices, there is even less attention on AI-specific cyber threat and what should be done by manufacturers, but also all the players in the healthcare domain. So I really thank you for your attention, for being here. It's been a great day today, and I'm looking forward to the discussion. Thanks.
So we would invite Professor Grossman and Elisabetta, please. And we look forward to some questions from the audience or from people connected online. There's a question over there. Maybe the mic. Yeah.
Yeah, so this is a question for Dr. Grossman on the topic of building data commons. So I was wondering if you could talk a little bit about, sorry, over here, the cost of building a data commons, and with the cost in mind, is this what sort of project threshold would you need to consider building a data commons versus just putting the data up unstructured on some of these public repository websites?
That's a great question. I think you need a certain longevity for the project and a certain scale for the project. So that's the first thing to keep in mind. The second thing to keep in mind, in the US, these have been very, very large and have been done by the NIH institutes and centers. And I think there are additional models. What's going to happen over the next few months is there's going to be an AWS, a data commons as a service coming out, so that mid-sized projects, smaller projects can bring up a data commons via Gen 3, run it for 5 years, and then because of the data lake model, there'll be automatic migration of all the data when you're done with the project that can send it to one of the large-scale repositories. That's going to change the dynamics. But let me make one more comment. As always, the cost is in the curation and harmonization on one side, and then the front end on the other. If I think it is more work to put it publicly, but if you put it publicly through a commons or otherwise, it really puts the burden on you to make sure the data is what it is. And unfortunately, a lot of data out there isn't. On the other hand, these commons will come up with a generic front end, but in general, people want to put more front ends. One of the things I didn't have time to say, I mean, is that coming out within 6 months for the genomic data commons, and within probably a few months after that for Gen 3, there'll be a front end framework so you can put your own tools over the data. And so I think and then there'll be a competition for the community to create the best tools that can go over data at these huge scales. So I think that's going to be a game changer.
Questions from the audience? I had a question actually, which relates to probably both the three of you, and it has to do with data poisoning. It was brought in the last discussion, and because of the sensitivity of this data in the medical field, the swarm computing or federated learning is the best approach apparently. But how does this tool then deal with the complying of the centers using the tools appropriately and not maliciously, either intentionally or not?
So,
I'll go after her.
Okay, thanks. Thanks for the question and about data poisoning. And well, my answer would be quite legally oriented because my background is rather legally rather than technical. So for what I've learned, I think it constitutes a measure to mitigate privacy risk and cybersecurity risk. And in my opinion, adopting security measures to avoid the risks such as data poisoning are tools which I don't know if they are effective, because technically speaking is more complicated for me to assess because I'm a legal expert. But for sure they will constitute a measure to comply with from a GDPR perspective when it comes to ensuring technical and organizational measures for ensuring security of data, but also in light of NIS2 directive, which will be coming soon and which requires the adoption of cybersecurity risk management measures. And today I was not mentioning also the Data Governance Act, which is another regulation that concerns the data sharing and it's specific to healthcare. And one of the key concepts is data altruism. And among the many aspects, it introduces the notion of secure processing environment for data sharing, and it then lists the fact that that could be privacy enhancing technology. So also in this case, I think it could help mitigating risks. But yeah.
I'll respond briefly. Yeah, I mean, for organizations taking large data sets they don't understand, building models that are fragile in the sense that they're likely to be susceptible to attack by data poisoning and other attacks, the burden is on you not to put those out for general use. One advantage is of taking your own data, understanding it extremely well, building extremely robust models, and then robust in the technical sense is that they don't have a lot of the susceptibility to data poisoning, is they're less susceptible. Doesn't mean they're not completely susceptible. You can, I'll go back to Alex Pearson's example. I spent years cleaning up for the community the TCGA data but it has this bias that's inherent from it came from a few sites. So choosing the models and choosing how you expose the models is the first. The second is when you think of federated learning and think of swarm and other things, the easiest way to do this at the beginning is through, if you think about this, what I was calling consortium management, for having a small consortium of groups that you trust, that you know their data, that their data is curated, you'll be much less likely to be susceptible. That's at one end. And, you know, if you think about it, if you know, I came here because I'm excited about interoperating with, complying to GDPR with this sort of the large US infrastructure with European. If we were to do 100 sites, that could cover a good portion of the world and you could have a trust relation. At the other extreme is the, you know, consumer health that come up through phones and wearables and go up to an organization. You know, that's a whole different area, but that is at such scale that it's a little easier to understand these kinds of attacks.
Thank you. There is a question over there.
Yeah, I have a question. We've talked in a number of different sessions about open source, both hardware and software, and I wonder about, do you think as the framework moves forward, is there sufficient regulatory and legal infrastructure where we could actually move an open source hardware or hardware software hybrid into practice and have that be deployable for patient care?
I guess the question is for me. I go first. Okay, thanks. So actually, this is a question I really enjoy thinking about it because it also open source software and hardware is a matter that I've been researching before in a previous European project, which was about European open source hardware and the legal framework that in healthcare and share with open collaborative platforms. So for me, that was something that was really interesting to study as a legal and ethical researcher. And while I was researching that and the legal framework, I was dealing with this question. Of course, the former project was more household related, and here it's clearly another kind of application. But still, I think there should be more, and it's a bit a funny answer to bring, but I think there should be more research in law to understand the implication of cybersecurity and transparency and cybersecurity when it comes to open source software and hardware. In the European Union scholarship in law, I don't think there is enough research. I couldn't find much. From a really initial research, I thought, yeah, it looks like there are some tensions between ensuring cybersecurity, but at the same time, as I am, let's say, a proponent of open source software and hardware, I have the impression that this could be just a narrative to somehow diminish the value and the role of open source software and hardware. So my wish is that someone could research more on that. And at the moment, I think to reply again to the question is that there is not enough relevant references, although I see in proposals that it's popping up a little bit more open source software and hardware and European Commission's level as well.
I just want to add just briefly that actually the IACT and also there is like a direction of making making a must to make, I mean, data has been already done, but also the source and the code. So probably it will become something that it's a requirement to make the code as open access and the model as open access after having the open access data, which is already now a must, I would say. So this will probably become, at least in Europe, like something like stated in the regulatory framework as something that you have to do if you want to reach the market with your device.
And let me just make a quick perspective from the US perspective. I know nothing about Europe, but it's useful when asking questions like that to have a distinction between the open source as software and the organization. You know this better than anyone else, Dr. Pearson, and the organization that does the submission to the FDA for a software as a medical device or as a medical device, because there's nothing to preclude the organization from using open source software as long as it puts all the required processes around that open source software. And that's today. Over time, in terms of transparency and other things, it would merge to that. But the simplest example I think about this is, the Moat paper that a number of people were talking about yesterday, where, things are shifting back from these large proprietary AI systems to smaller more understandable ones that can have a really big impact. So I think that's a great question. I think this is a good time to be thinking about these kinds of things.
Thank you. We have not a question, but maybe a comment from the online people. It's Pierre Albino Colombo, and it touches on data poisoning, very important point. This is one of the key points with chatbots trained by private entities. So I guess what he means is that that's why we should train chatbots ourselves within private entities rather than trusting what the chatbot is saying when somebody else has trained it, because the user does not know on which data the model has and is trained. About the data commons experience, which is an important point, should be extended to also to chatbots training. It's not that easy. Data curation and harmonization is challenging, but I think this aspect should be seriously considered. So that's a comment, I guess. And because we are running out of time, I'm afraid maybe we need to close this session.
Yeah, let me just please have, because I would like to make just a final question, or a comment, maybe more to Elisabetta. Yeah, very quickly, because I think that this is a very real important section, especially because I think that there is now today a really high gap, and also I think that we need a more great balance between innovation and legal and ethical framework, because we are running, we as technology are running in a logarithmic way. Why we have a really, I can say as a medical oncologist also, a bit as a technician, that it's really hard. You are one, I'm very proud that you are one of our ethical group and partner within our European project. And you are doing such a great work. But I want an advice from you, us as medical oncologists, as clinicians, what we can do. And also as a patient representative, I'm very happy you will know him from the lung cancer Italian group, and he will be present here because they are helping us a lot as an engagement with the patients, also related to all these problems. Sometimes most of patients don't see all these, GDPR things. So I'm talking now about a EU perspective, not US perspective, but just to say that what we can do more, we need to run and innovate also in this way.
Yes, I agree. This is
Sorry.
another question.
I think we all agree with something mentioned that we all mention. If you think that is something that if you think that from the MDR, which is actually the regulatory framework now that for medical devices and also for software, that was published in 2017. And now on the market, there are still devices that are not compliant to that, and this can remain into the market up to 2024. And I'm pretty sure that this date will be shifted in time, because everything has been shifted in time. So it's 7 years, and it's like, everything is very, very old at the end of the story already. So it's crazy.
And also at the data sharing, I don't know, I'm thinking about how to create or how we can better impact these and accelerate this step, which I think we have to accelerate some way. So how we can participate better and to, try to guarantee somehow or explain to GDPRs and everything, all the this governance that we need their help also, I mean, in this step. This is very important. Otherwise, will be a lot of innovation and research and less impact, not only from the data, not only for the models that we are not, I mean, so robust, but also because everything that, for example, we need more, at least 1 year to, I mean, activate a study, and especially for the technology that is going fast.
Yes, I agree. I think also it's really important to guarantee legal certainty when it comes to further processing of data for research, which is another hot topic, at least in legal studies. And it's really important that I think forthcoming reforms tackles appropriately this issue, which I learn day by day, every day, that it's really pressing for the healthcare community.
So thank you. And
thank you.
Now it's time for a coffee break, 15 minutes, and we return at 4:30.
Yeah, please come back at 4:30 so we can finish in time. Thank you.
Good afternoon, everybody. Please allow me to introduce myself. I'm Giuseppe Lorusso. I'm a medical oncologist here at the Istituto Nazionale dei Tumori in Milan. It is a great pleasure and a great honor to be here with you today and to introduce this very interesting section of the conference. Before starting, I have to remind you that we will proceed first with the presentation and then we will have time for question and discussion. For the virtual audience, I want to remember the possibility to ask questions using the web live chat. We are waiting for the question for the Dr. Colombo. Thank you for the previous question. We hope that we will have also a question in this section. So let me introduce my colleagues that will be with me, the chairs of this section, Dr. Claudia Proto and Dr. Carlo Genova. Claudia?
Thank you, Giuseppe. Good afternoon, everybody. First of all, I would like to thank my colleague and friend Arcela for this kind opportunity. Now we have to start this last session, and it is my great pleasure to introduce the first speaker, my friend and my mentor, Dr. Marina Carassino. She is a professor at Chicago University. Unfortunately, due to a concomitant commitment, she is not here with us and she can't connect. We don't know if she will be able to connect later. We hope for the future. But meanwhile, we can start with her pre-recorded talk. Her presentation, the title of her presentation is AI to Accelerate Clinical Trials Design and Implementation. I think that we can start with the presentation.
So, hello everyone. I'm really sorry not to be in Milano today, but unfortunately I had a previous commitment here at the University of Chicago. But I'm really happy that a lot of people of the University of Chicago are in Milano, and I'm really happy about this alliance that I think that Arcela created, and I'm really grateful to her for this Congress, for the invitation, and I'm really enjoying this collaboration with my previous and my new group. Starting from the aim of my presentation, I have to talk about the clinical trials design and the implementation with the artificial intelligence. And we know very well that there is a funnel of drug development for which it takes a lot of time to develop drugs. And there is a starting from a target validation and arriving to the commercialization of the drugs. And you can see the incredible attrition that we have from the beginning to the end of this process. And clearly, this is translated in a very high economic burden, in a very high failure rate, and in costs of drugs and time for our patients. So potentially, the artificial intelligence can help at multiple levels for this decrease of time and resources. And we are going to see what are the parts where there is more impact of the artificial intelligence. Clearly, there are many fields that are starting from the diagnosis of the patients, from the treatment and prognosis, to the drug discovery and patient management. And all these techniques will help to reduce the timelines of the drug discovery. I'm sure that you heard yesterday the presentation of Alex about drug discovery and drug development, which is a very fascinating field. And there was this paper that was a breakthrough in the last 2 weeks that said that in 30 days, these authors from the University of Toronto were able to create a drug and an efficient discovery of a novel CDK20 small molecule inhibitor. And this is something that we do also at the University of Chicago, where we have a process that is a collaboration with the University of Chicago and the Argonne National Lab that was the idea of the actual president of the Cancer Center, Kunle Odunsi, and we can propose new targets with the quantum technology and the computers. We are able to screen 1 billion of compounds. We are able to modeling drugs in silico. Then there is the human part, which is the drug, the part for which the chemistry has a fundamental role to create the molecules. But I'm sure that you are also aware that the robots are coming also in this field, for which it is possible that we will be able to create an incredible number of compounds in days. And then clearly we have to go in the animal models and in the human part. So, but it's incredible because all this process is really accelerating in a very incredible way all the drug discovery, and then we are going to see how it will have an impact also in the drug development. So when we think about the clinical trial development, we have always to remember that we must follow the rules that were also before. And I just want to tell you that the artificial intelligence will have a great impact in the identification of the right patients and to give to the right patients the right drug. But when we do a protocol design, we must follow the same basically rules. A thing that is really important is that if you look at the trials that are now in the clinicaltrials.gov with the artificial intelligence, and I would like to thank Alex for giving me the list, you can see that the majority of them are observational trials, and the majority of them are including the tumor detection, are including the optimization of design and dosing, and they are basically biomarker discovery. And so we still have to start really trials including the artificial intelligence from the beginning. We are now working on all the pieces, and I'm sure that in a year or 2 years from now, we will be able to run really what I'm going to tell you now. Now we have just a composition of everything that I'm going to give you. When you start a clinical trial, you have to identify a very clear background, to identify the objective, the study population, the intervention, the quality of life, the safety. You must monitor the quality and the reliability of what you are collecting to have a precise statistical plan, and you have to monitor the study conduction. And in all these 10 points, there can be a role of the artificial intelligence. First of all, you can be able to identify what is the unmet need, exploring the literature. There are also techniques with the text mining techniques to explore the possible background. There are also public databases that you can consult to see if a clinical trial is already ongoing and what is the design of that clinical trial. And I think that there can be also use of some chat box like ChatGPT, but you must be also aware that, for example, I did an experiment and ChatGPT, you must be aware that is inventing also a lot of things and is not totally reliable to this aim, in my opinion, at this point. Here you have 2 examples of 2 aggregated structured the clinical trials repositories. One is a project which is called AACT and is promoted by NCI, and basically through the AACT you are able to consult, and also with the clinical healthcare intelligence application dataset you are able to use some keywords, some conditions, and some qualifiers to extract what are the clinical trials that are already ongoing. And I think that this can be really important and really unique. I think that the second step is to identify what are the best objectives and endpoints that are able to maximize the possibility that a clinical trial will become positive. And I think that potentially a big application of the artificial intelligence will be to predict the probability that a clinical trial will become positive, and also the timelines of the clinical trial, and also the eligibility criteria of the clinical trial. This is something that was recently proposed, and as you can see, the two repositories are able to increase a sort of enhanced data set, and the data set is able to create data analytics, model training, model evaluation, and clearly is able also to create what is the probability of an early clinical trial termination based on unstructured data. You can see that the authors identified some study characteristics from objectives and eligibility criteria that are associated with clinical trial failures. Another very important part is to match the inclusion-exclusion criteria with the electronic health records. Here there is a part that is very important for the feasibility of the clinical trials, because potentially you can extract some features from the health records that can give you an estimation of the prevalence, for example, of a target, or potentially that can influence also the recruitment from cancer registries, and can also combine omic data with medical records through the natural language processing or the optical character recognition. I think that is also important to use this data to identify some populations that they have a particular prognostic characteristics, and so you can try to enrich some population of patients that potentially can benefit more than others to the treatment that you want to evaluate. Another, I think another very interesting possibility is to match the machine learning, the deep learning, the reasoning, the human-machine interfaces with clinical trial databases. And there is a sort of clinical trial matching, and you can match the patients with the eligibility criteria and the empowerment and the motivation of the patients. I think that this can really represent an opportunity for the clinicians, because we are all aware that the time that we use for finding the right trial for the right patients. So this can represent an opportunity to match the patients and the clinical trials, and to, again, to accelerate the trial conductions and to finish the clinical trials early, in particular for the rare population. Clearly, we are always all complaining about the fact that sometimes the clinical trials are not representing the reality, and sometimes they are boutique trials, because the patients in the clinical trials represent patients in general in very good conditions, and in general patients in really motivated to come to a clinical trials, and unfortunately sometimes they represent not the overall population but a particular part of the population. So I think that in the future the possibility to use the real world data is a huge opportunity to have a real control arm. And I think that potentially in the future the drug will provide some safety data from the drugs, and then the later phase clinical trials will be in the real world data, and we can potentially use also the control arms from real world data. This is something that is still not new, but FDA recently announced that there is a new advancing real-world evidence program, and I think that this will be also important for the equity and for the access for all the patients to the clinical trials and not just for particular part of the population. I think that another very important part is the presence of open source projects. This is one project, DataSphere is one of them, and clearly if we will have open sources data, potentially we will be able to create our control arms for the clinical trials. Another fascinating part is the creation of digital twins. There is also one part that we call avatars in the I3 lung. So potentially we are able, based on the genomic data, the clinical data, the patient reporting outcome data, and also psychological data, potentially we are able to create a sort of digital twin. And with the digital twin, we are able also to create some simulation of clinical trials based on historical data and based on a sort of clinical trials on digital models. I think that also this part potentially will reduce the attrition of the patients enrolled in the clinical trials, and potentially thinking to the future, potentially we will have maybe in some years from now, we will have our digital avatar and we will be able to treat the patients based on the digital avatar and with all the genomic and the clinical data and all the omics from the patient. So I think that also this can be a fascinating part. Another part that I'm sure that for all the people that are sitting in the room and are doing clinical trials, we know how much is our pain to do the RECIST criteria. We have to go down to the radiology department, beg the radiologist to do the RECIST. Sometimes the RECIST are not matching to the previous RECIST, the RECIST that we collected. Sometimes we evaluate the diameter in we evaluate the diameter in a slice that is not corresponding to the other one. And so there is a huge effort to use automated techniques to assess the treatment performance in a more standardized and blinded way. For this, the FDA, again, is creating some automated RECIST. There is a huge effort to standardize the RECIST criteria. And if we are able also to create automated RECIST criteria, I think that potentially we are much more reliable, and potentially there is clearly less cost, less centralization, and less human work. Another part that, again, I think is really painful for all the people who are doing the clinical trials is the presence of the monitors in our hospitals. The monitoring, the human monitoring is requiring really a lot of time, a lot of human time, a lot of, now maybe is just a bit better after COVID because we do much more remote monitoring than before, but we need a big delegated staff to do the monitoring. And so through some methods like the natural language processing, there is the possibility to check the data collection directly from the electronic health records. And we are also potentially able to collect some data with the wearable devices, for example, through wearable devices or through smartphone web app that can allow a continuous assessment of, for example, the quality of data and also for the drug adherence of the patients. This is an example of wearable devices, but potentially if you think we can control, the saturation of the oxygen, we can control the heartbeat, we can control how many steps a patient is walking, the tone of the voice, the time that the patient is sleeping. So we have the possibility to collect a lot of data that potentially are associated to the quality of the life of the patients, and maybe they are more precise than the quality of life that we are collecting now through just questionnaires. Clearly, the artificial intelligence in the future will assist also to the creation of maybe novel method to create our sample size. First experiments were created. You know that we do the phase 1 trial based on the Fibonacci rules with the 3+3 schedule, and basically collecting the data in a different way. Potentially we are able to move from this typical way to do the phase 1 trial, and we can use more precise data that are not just 3+3, but are continuous data, and maybe they will help also the drug development, in particular in the phase 1 trial. This is a clinical trial simulations that was done not in cancer, but with Alzheimer. And as you can see, there are components that were able to provide the variation of the drug, of the disease state, and of the trial design. And you can see that the number of subjects included in the clinical trials were totally different if they were created with the artificial intelligence or they were created with standard models. We must be very aware that the web is full of scams, and so try to remain only in situations that are done by academic institutions or are validated. And none of them are validated to the clinic, so it's still we are still working on creating correlations and that are not totally related to the clinical trials. So potentially the artificial intelligence tools that are coming will have a big impact in reducing the cost, in higher and faster adaptability than humans, in shorter development times, and potentially we will enrich the patients' populations of patients that are potentially have more chances to benefit to a drug from another. And as I said before, the drug discovery will be much better than what it was in the past. There are big challenges. I think that one of the major challenges is the privacy. We know, for example, that in the United States, there is the HIPAA compliance, while in the Europe, we have the GDPR. And sometimes, unfortunately, the GDPR and the HIPAA don't match. And I think that we have to work also on the anonymization of the data, because this will allow to create public registry. And I think that is very important to create in the hospitals and also in the cancer center artificial intelligence units. And I think that as Arcela is doing now, we have to start talking with the engineers. It will be difficult with the doctors to talk with the engineers, and maybe it will be even worse for the engineers to talk with the doctors. But I think that the future will be the collaboration among multiple stakeholders, because only in that way we can accelerate the research, and we can accelerate the clinical trials, and we can accelerate the drugs for our patients. There are some data, or already some historical example of real-world data sharing. This is the DREAM dataset from cancer. And I think that this kind of experiments are becoming very important for the future, because we can share historical trial data and we can potentially increase the reproducibility of the clinical trials. So clearly, this is just 1% of what we can say about the impact that the artificial intelligence will have in the clinical trials. But I think that there is a great hope that this will help the drug discovery and the drug development, will help the patient-reported outcomes, will reduce the human burden that we have now for the clinical trial conduction. We have to work on the privacy. And I think that, as we did for the translational research about 20 years ago with the basic science, with the basic scientists, we have to start working together with the engineers, with the physics, with the other people working in this field to implement the research and to stay all united to do that. I would like to conclude with this picture that we have done some months ago, saying that I'm really happy about this collaboration with Istituto Nazionale dei Tumori that is and was my house for many years, and with the new people of the University of Chicago, because I'm sure that all together we will be able to increase the chances for our patients, and we will be able to foster the research in the future for our patients. I would like to thank again Arcela, enjoy your work, and again, I'm really sorry not to be there, but my heart is with you. Bye-bye.
Okay, thank you. Can you hear me? Yes. Okay, so for the next presentation, I assume you all know Arcela. So, but we still need to introduce her. So Arcela Prelai is a medical oncologist from the Thoracic Oncology Unit of the National Cancer Institute, and she's also member of the ESMO working group for real-world data in digital health, and she's she's a PhD candidate for bioengineering and artificial intelligence, so she's very competent about this. And she's going to describe about a fine example of applied AI-based project, and she's talking about the iCube Lung Horizon Europe project.
Thank you, Carlo, for your presentation. And I mean, everything you have said, it's correct, except for my huge experience in AI. So yeah, I mean, these last 4 years, I can say that I was very enthusiastic to introduce myself in this new field. And I really like and take this opportunity to thank you for being here. I cannot thank myself for the invitation. But another important point is that in this new path for me, still very new, I'd like to thank also Marina Garassino. I mean, she was and is one of my mentor, and she really put me in this path, because I didn't know anything 4 years ago what was AI. And so I'm very happy here to present also one of use cases. Don't want to bother you because I know that it's a bit late, so all of you are a bit tired, but just to give a practical example of, as you have seen, how we can, I mean, prospectively conduct an AI clinical trial, in this case, focus on biomarker discovery and biomarker validation. So this Horizon Europe project, it's very, I mean, the design or the objective of this project was very simple, because for 10 years, we, us as a medical oncologist, try to answer to one question, how we can predict, as Saurabh said, immunotherapy response to non-small cell lung cancer patients and to other cancers also, but in this case to non-small cell lung cancer. And it's really very hard because today we are all treated patients with immunotherapy, but we know very well that there, I mean, not that most patients benefit, but there are still, for example, a percentage of patients that do not benefit from that, or we still do not know to give, for example, in Italy, we don't give to all comers chemoimmuno, but we give immunotherapy only for high PD-L1 patients while for PD-L1 lower than 50%, we give chemoimmuno. And to do this, we applied in this European grant, but we also, to be inclusive with the US and Israel, and also because one of the scope here, and as I said with Elizabeth and University of Kiel, was to understand all these ethical issues related to AI and data sharing frameworks and legal frameworks, and to understand if we can overcome US, EU, and Israel, and all the other, countries, and also reducing the bias disparities on these models that it's another great problem. And to do that, we aim to have two main goals. So to develop a platform, which is called i3Lung platform, put the data inside, not only real-world data, but as you can see, you will see other type of data, for example, multiomic, and respond and try to develop three main tools. One, the decision-making tool for physicians, so that can help to decide patients who are candidate to immunotherapy, if they can benefit or not, maybe we can candidate them in other clinical trials or things like that. And another co-decision-making tools with it's a very important patient engagement and their participations in patient has to be aware about all the outcomes that we have, so the overall survival, the quality of life. Have to contribute a bit on this. Another tool related to the researcher dedicated to the continuum learning and the possibility to this platform to grow and to put new data from other centers beyond this research, this project. So this is just the panorama of our work packages. And just to mention that our work packages, except from the coordination, which is a must work packages, it starts with the ethical and legal framework and to try to understand and how to overcome and how to build why new guidelines related with AI design. While I will start, the second aim was the data collection, which, as we discussed today, it's not very simple. And what we decided to do is to reuse the available data that we had in all these 10 years, with immunotherapy. So, and what we did is that we decided to include, and we will finish now at the end of the May, hopefully, our first deliverables, 2,000 patients among six cancer centers, lung cancer centers in Europe and beyond, and trying to train and develop a tool based in real-world data. So in clinical data, radiomic data from CT scan and PET scan, and digital pathology data, when available, digital slides on histology, and PD-L1 slides. I'm very happy James will be one of the guys that will lead our pathology, digital pathology task in this case. And the second cohort, which is, I call them a non-omic cohort because our cohort on real-world data will be a prospective one. The goal is to validate what we have learned from retrospective data prospectively to another 2,000 patient of cohort within these cancer centers and try with the same data, so clinical data, radiomics data, CT scan and PET scan, histology data. And we also will at this time the behavioral data, which as Emilia said, and she will lead also this part of the project, also with the app mobile, transparency app mobile, which are very important because we also have to know to understand how we can improve the quality of life and the behavioral data collection with AI. So while we have a final multi-omic data cohort, But the objective of this cohort, when we designed it with Marina, we thought, as Alex said today, not to, put together and integrate all the multiomics available data, because we know very well that it's not feasible in clinical practice, this. So, but we have to try, at least within this opportunity, and understand which of the omic that we can have and is available can fit more for a subgroup of patients, or maybe there are some other omics that can fit better. So try to personalize a bit the diagnostic path of all these omics and try really to move the ghost biomarkers, which are generally the immune, for example, immune circulating profiling and that, to a more clinical practice opportunity. So we'll always here in this cohort collect the clinical data and behavioral data, the medical images, as we will do in the previous cohort, and also on tissue, also with a great collaboration with Germany and with Mario Negri, which is here, Massimo. He will work on metabolomics, genomics and transcriptomics from Val d'Hebron, and also all the multiomic data, almost the most important multiomic data on liquid samples, so liquid biopsy, ctDNA, circulating immune profiling, cytokines, microRNA with Mattia that work here, and also single cell analysis. Related to single cell analysis, we will focus these analyses, as we said today with Sorab, just to discover something within the INT cohort, since we have to do it within fresh blood. And so from guessing information from that 40 patient cohort, we will then validate then further in fax analysis or. And finally, we will also evaluate the microbiome in these patients. As you said, it's impossible that in a real world data, in a real practice, we can integrate all of them. But the idea is that we have to impact clinical practice and at the same time, in the parallel way, discover and continue our research. As Vibert said today, it's very important. There are many, many agnostic cancers and unknown cancers. We need to impact the patient life, so in 360 degree. And so, as I said, one of the aims that we stated is to understand the adding value of this omic within the retrospective tool, and also to personalize probably the diagnostic way of these patients. So it's just a demonstration what we did also related to the retrospective cohort, so we have to go back. We try to understand what we have done in all these 10 years and collect also the translational data that the centers have worked on in order to don't forget with AI, we can learn and reuse the data that we have, and only putting them together and trying to harmonize them. Also, we'll try with the help of Robert that discussed today and Alex within a common data dictionary, mainly related to genomics, but also to other multi-omic common data dictionary to help and understand how we can homogenize it among centers. So this is the platform. I'm not going within depth because I don't have many time, so I am over, I think. So I just had 10 minutes because another colleague would present another case uses, and the infrastructure that Michele Zannitti together with Sokol Costa from Copenhagen have really built. It's very complex, but just to let you know that it's a great opportunity, as said Roberts, with all these data lakes and platforms to understand and multi-usable data within the same interface. And obviously, it is also foreseen the privacy and security, as we discussed, and all these design have been published recently. But the last thing, and let me just take one more minute, was this design of this psychological clinical trial that tried to understand 2 points to put the model within clinical practice, which is the patient awareness related to AI tools and what would be the doctor anchoring bias of these tools. So this is very important, and we will try to understand and hopefully in the next years have some results on it. And as we said with Professor Pedrocchi, in the final part of our project, we'll try to explain the models and give more interpretability and trustability to our models. To don't leave the cost-effective analysis, which is very important, because if we want to go in the market and when we want to have approval for a CE market, we need absolutely our tool to be cost-effective. But I think that, as Alex said, we are in the right way, so we believe this. So I finished with my presentation. I'm very happy again to have you here. I'd like to to thank all my group and our group led by Dr. Lorusso at Istituto Nazionale Tumori and Thoracic Oncology, and also our AI lab, which will be very soon. We have their first space. And thank you to Vanya for her contribution and helping me for these slides, and to all of you for joining this meeting today.
Thank you, Arsela. And now let me introduce Dr. Andrea Vingiani. Professor Andrea Vingiani. He's an assistant professor in pathology and working in the pathology unit of the National Cancer Institute, and he's going to talk about the Apollo 11 study master protocol.
Thank you so much for your kind presentation. And I'll try to briefly introduce the Apollo 11 study that is somehow the little brother of the I3-Lang that Arsela just presented. So, what is the Apollo 11? The Apollo 11 is a study funded by the Scientific Directorate of INTA, led of course by Arsela, and is a study with a particular endpoint, that is the creation of an Italian lung cancer network for the systematic collection of real-world data coming from lung cancer patients, both non-small cell lung cancer and small cell lung cancer patients, treated with innovative therapies through a robust and shared database that we identified in REDCap for a systematic collection, an homogeneous collection of several types of data, and of course also the implementation of a national biobank, a virtual multi-level biobank for the collection of several types of tissue, like FFP tissue or fresh frozen tumor tissue, as well as plasma and blood samples for each patient. And of course, this infrastructure will be absolutely fundamental and crucial for the main objective of the study, that is again the development of an AI-based algorithm to predict the efficacy of immunotherapy in lung cancer patients through a federated approach. And the algorithm will be fed with the real-world data, as Arsela said before, for the I3-Lang study, with radiomics and multiomics data. We plan to gather 48 Italian centers across 19 different Italian regions, planning to collect data from more than 1,200 patients. This is the actual situation at present. There are 5 institutions in which the study protocol has been already submitted and approved by the local ethical committee, and they are INT in Milan, Niguarda in Milan, Cremona, Campus Universitario in Rome, and San Matteo di Pavia, but several other cancer centers are at present in the process of submitting the protocol to the ethical committee and will be soon on board. Again, with our database, with REDCap and other dedicated database, we will be able to collect traditional, let me say, real-world data, including demographics, anamnestic information, clinical findings, but also lab findings, traditional histopathological characteristics, including histotypes, tumor grade, Ki-67 proliferative index, of course, PD-L1 expression status, and also molecular data from NGS characterization of tumor samples. On the other side, we'll collect multiomics data, like, for example, microRNA, lipidomic, liquid biopsy data, and of course also data from the characterization of peripheral immune cells through single-cell RNA-seq and FACS analysis that in turn represent the main focus of the translational part of the Apollo 11 studies, and of course radiomics. Just I want to give you an overview of what is our clinical practice. This is the workflow used for every single lung cancer patient in our institution. As you can see, every single lung cancer patient, after appropriate histopathological diagnosis, every single patient is characterized with comprehensive genomic profiling, both on DNA and RNA, with a comprehensive genomic profiling panels, being able to detect mutation in more than 500 genes, copy number variant alteration, rearrangements, tumor mutational burden, and also microsatellite instability status. Of course, we'll have PD-L1 evaluation by immunohistochemistry, and in a subset of progressing patient, also the characterization of circulating free DNA. Of course, huge efforts will be put also in radiomics with the acquisition of the largest number of CT scan possible from all the patients recruited in the study. We will acquire the images, and as previously mentioned, we will have image segmentation for feature extraction and the implementation of the predictive model. Just a few words of single cell analysis. That is my focus. Well, as you probably know, a lot of researchers focus their effort in characterizing immune cell species by single-cell RNA-seq, and the vast majority of groups, of course, focused their effort on T cells, but only a few examples of studies focused on neutrophils are present in literature. This is true because of surely obvious biological reasons, since the main focus in immunotherapy are T cells, but also for technical reasons, because neutrophils are delicate, fragile, and short-living cells, so they are not easily detected and captured by single-cell sequencing. This here on the right, you can see a recent example of a research project in which authors classified and characterized the transcriptional heterogeneity of tumor-resident neutrophils and developed a predictive algorithm that was subsequently validated in a bulk RNA-seq dataset, being able to predict the clinical outcome in patients treated with atezolizumab. On the other hand, the group of Sabina Sangaletti, working here in Istituto Nazionale Tumori, she's the leader of the translational research task force in the Apollo 11 study, and his group, including Roberto Ferrara, recently published these promising results in which they were able to demonstrate that the relative proportion of peculiar subset of neutrophils is able to predict and to correlate with clinical outcome. For example, you can see that CD-positive mature low-density cells are enriched, for example, in a patient with a partial response. And on the other hand, for example, you can see that CD10 negative immature neutrophils are significantly enriched in patients with the poor response or in hyper-progressive patient. So in this context, we decided to focus our translational research aims on the characterization of circulating immune cells with a twofold approach. A first approach relying on the characterization, extremely deep characterization with the single-cell RNA-seq on 30 patients. with a subsequent validation of 120 patients by fax analysis. And in consideration of the technical issues related to the neutrophil itself, we implemented a dedicated wet lab protocol aimed at guarantee the largest number of neutrophil profiled. And in that cases, we initially started with processing 2 samples from each patient, 1 sample made up of PBNC and 1 sample with a vial of neutrophil enriched by fax sorting. And we were able to demonstrate that transcriptionally these two, the neutrophil found in the PBNC vial and in the enriched vials were not significantly different, so we were on the right way, and we therefore moved the shift of another approach just in order to optimize the cost related to single-cell sequencing, of course, taking care of putting together PBNC and neutrophil within the same vial and process just 1 vial of cells. And up to now, we have profiled 11 patients and we have sequenced 3 patients, and these are the preliminary results. And as you can see, that along with an expected high number of B cell, T cell dividing CD8 plus and CD4 cells, we have a huge, an unexpected high number of neutrophils that are those that cloud in blue, in light blue. And we were also able, thanks to CD10 gene level expression and other gene expression signature, to identify mature and immature neutrophils. So we are at the very beginning. The road is long, but we are quite excited. So I want to thank you, all the medical oncology staff, all the AI team from Politecnico, Monica, but also the Dottoressa Sangaletti group and Roberto, and of course all the pathology department, all the people from the pathology department involved in the study, including surgical pathologists, of course people dedicated to single-cell analysis, including Antonino, Luca Agnelli, Tommaso Torelli, and all the molecular pathology staff. Thank you.
Thank you, Andrea. Let's go with the last presentation of this section. I'm very happy to introduce Dr. Laura Gagliardi. Laura Gagliardi is an Italian theoretical and computational chemistry at the University of Chicago. She is known for her work on the development of electronic structure methods and their use of understanding complex chemical systems. She will talk connected online from Chicago about beyond AI, quantum science. Thank you, Dr. Gagliardi.
Thank you very much. Oops, can you hear me?
Yes, yes, yes.
Yeah, now I have to, well, there is okay, I have to share. So am I sharing anything or not? Let's say if I do share, let's see, share, how do I share my presentation? Do you know? Share. Hello, can you help me? Browse my computer. Okay. Let's see. Okay, I think I'm ready to share. I know I did. Okay, this is the version 2. Great. No, it's all right. So I think I can share it. Let's see if you can see my presentation.
Not yet.
Okay, wait a second. Save it. Oh, apologize for this. Okay, let me just, I think I have to open it first. Okay, or hold on, give me a second. I apologize for this. I usually use computer talk. Okay, I want to open this one. Oh my God, it's getting bad.
Yes, yes, everything is okay. We have a lot of time until 20, 21 in the night.
I want to help. Someone has to help me. Stai bene? Sta benissimo.
La dottoressa si è sconnessa, ha perso la connessione.
Okay.
Okay.
We can start with the question.
I think that is better to wait some minutes.
If you want, we can start with some questions. Okay, for you and for Andrea. I have. Are there any questions from the audience? If you want, you can come here, Andrea. No. I have one question for you. You know we are oncologists, and we hope that AI may be useful in the next future for our patients to choose the better strategy and to improve their outcome. I was thinking, what do you think about the timeline of the implementation of AI in clinical practice, based on what we have largely discussed today? Do you think that it will be easy to introduce all these tools in clinical practice?
So as we discussed today, and I don't remember exactly, but I think James or other speakers give some examples. We have actually already some of them, of these tools that are used mainly in radiomics field, which are more implemented for many years now. But the idea is that, I mean, if we are talking, because it can be different diagnostics tools, so if we are thinking about digital pathology, for example, which with the slide flow, which is an example that can be used and implemented. The idea is that the AI revolution will be very fast as it is, but in different sectors will grow. I don't think will grow in a parallel way in different sectors. But when we are talking about impacting clinical practice, as we discussed and we were chatting with Alex before, we really, I think that I really believe that to implement clinical practice, we have to be also pragmatic and cost-effective. We can continue as I said before, in a parallel way for many years, for example, working on biomarkers. Why I mentioned ghost biomarkers, I mentioned that before because we know that the NGS biomarkers, which are more genomics biomarkers, are more the successful biomarkers, but because they have been used for many years also in clinical trials. And to give an answer, as one of the radiologists said this today in the video that Raquel shows, I think that within the next 5 or 10 years, we can have useful tools using real-world data, including images. This is my maybe practical perspectives, while using these ghost biomarkers, including, I don't know, immune circulating profiling and other related biomarkers, transcriptomics. I think that it would be very difficult to, in a whole way, to include them. But I think that rationalizing them, I don't know, so in the proportion way, in maybe within 20 years, we will be able to personalize more and more, not the histology, but subgroup of patients within very personalized diagnostic paths.
Thank you.
Thank you. Andrea, you can do a comment?
Just for one example. If you multi-cancer early detection, a good proportion of those tools are actually based on, of course, genomic profiling, for example, the evaluation of tumor DNA fragmentation, but also DNA methylation that are actually treated with AI and implemented with AI. So, I mean, I'm not into AI as Arcela and all this stuff, all the panel present here today, but to me, there are several examples with several pieces of activity that are actually covered by AI. There are also tools, for example, in vascular surgery that use, for example, there is a question, okay, it use artificial intelligence for the prediction of the risk of an aneurysmatic rupture and so on. So there are, artificial intelligence is somehow here. Yes.
We can feel it.
Yes, we can feel it.
Okay, there is a question from the audience.
Yeah, we can feel it too. So your study design is very elegant and powerful, Arcela. The 2,000 patients with a prospective validation cohort, and I suppose so. Those patients, I'm just trying to understand. They come from across the multiple institutions. That's going to be like a blended cohort from.
Yeah, sorry, related to the timeline, I didn't specify, but yeah, so there are 6 cancer centers mainly involved, which are all cancer centers focusing on lung cancer with a high, so Istituto Tumori, Val d'Hebron is Martin Reck in Germany and also Greece. And there is also University of Chicago and Israel. These are the 6 cancer centers.
Okay.
Yeah.
So the question is really, given that potential for heterogeneity in terms of acquisition of CT scans, the technology that's used, or statings for histopathology, have you worked out what the expected center specificity of signals might be, and how we're going to deal with that? And is 2,000 patients enough to cover all that? I mean, can you speculate on that?
So this is a very good question and point of discussion in many meetings that we have had. We had recently, yesterday we had a meeting with a platform group related to imaging data, so in specificity for radiomics and digital pathology. So James knows related to digital pathology, he has gathered also the requirements, and he knows very well that there will be a lot of work to homogenize there, absolutely. So, for sure there are some tools, and we know that we can use, James explained today, and related to radiomics, we didn't decide yet which would be, exactly the pipeline for pre-processing and harmonizing. We discussed with, and we are creating actually a working group related to radiomics, which would be lead from Israel. However, simple size is a good question. We never discussed today, but maybe Marina quickly mentioned it. So there is no guidelines on simple size, and the message is, at least for now, the more the better in this case. So this is why we thought, and the Apollo 11 study, which is an Italian network on 48 cancer centers, it's not meant to copy or something, the idea, the scientific idea, but it's absolutely meant, which I am actually coordinating with Dr. Vinjani, which is the co-PI, and in order to also use, for example, more external validated cohorts, for example, also with Gustave Roussy, which we will hopefully, we are collaborating on one of the externally validated cohorts, and also I am working with Manchester, etc. So the idea is the more the better, and we will see. But what we discussed also with Alex, what we need to do, and which was all my energies these 2-3 years dedicated to absolutely try to harmonize the data collection and to put all these regulatory frameworks, which take a lot of time. So hopefully.
Okay, there is a question from the audience for Dr. Prelai, from Irene Azzali. You mentioned that you validate your system on a prospective cohort of patients, including also behavioral data. If we develop a system on a retrospective cohort, aren't we forced to use only the source of data available for the retrospective patients?
Yeah, I mean, we can, when I mention in a general purpose, I just explained that we will try to validate. And when we talk about validation, it's obvious that we need to use the regional data where when the tool have been built. However, we will see how the quality of data will implement, and we will improve also the prospective tool. So yeah, a validation process will be with the existing data, but we also will try to understand, since behavioral data are not a lot costly, obviously the app mobile, transparent app mobile, which as we are utilizing now, it's not so costly. I mean, we just uploaded it in a phone mobile, every patient have, or at the caregiver in case of old patients. So yeah, get more information about it rather than a validation, while we're trying to validate in the existing data from the retrospective cohort.
Okay, I saw Marina. Marina, are you here with us? No. No more.
She left. She left. Okay, she's here. She's here.
Yeah.
Okay, now Marina is back. Ciao, Laura. Ciao, Marina.
Okay. We have also Dr. Gagliardi, I think, no?
Yes. Shall I start?
Yeah.
Okay. We can have the presentation of Dr. Gagliardi.
Okay, can you see my slides?
No.
Not yet.
Hello?
No.
But I'm sharing it. Michele, can you see my slide? Michele, vedi la mia slide? Ok, adesso mi vedete? Do you see me now?
Yes.
Okay,
Okay,
so
it's
great.
okay.
Okay, so, well, good afternoon, everybody. My name is Laura Gagliardi, and I'm really honored to be here. It's not exactly, I'm not a medical doctor, I'm a chemist, but we have something in common. First of all, we all know Marina, who is a really unique humankind. She's amazing. And we all have an interest in computing, artificial intelligence, and beyond artificial intelligence. So today I'm going to talk about going beyond artificial intelligence with quantum computing for healthcare and life sciences. But before doing that, let me start. I mean, I really have to put everything into context and tell you just very briefly what I do. So first of all, I am a so-called theoretical chemist, material scientist. So I don't go in the wet lab. I do everything on the computer. I'm Italian, as you can hear from my accent. I graduated from the University of Bologna. And so we develop computational methods in chemistry, material science. We, as a group, we are more interested in application towards sustainable energies, climate change. But of course, expanding these directions also toward health sciences is very possible. And here you see some of the applications. So we study catalytic reaction in confined environments. We study some of these materials. They're like sponges for example, to capture carbon dioxide from the atmosphere or water. We also want to make superior quantum materials for quantum computers or study photovoltaics materials. And the whole idea is to model all these phenomena on a computer and work in collaboration with people who will make them and bring this technology to the next level. And so here, I want to tell you about the length scale at which we work. And so here you see objects going from like the size of a proton, which is 10 to the minus 15 meters, to galaxies, 10 to the 27 meters. We work with the molecules and atom, 10 to the minus 10 meters. This is the size of an atom. And this is how to compare it with a red blood cell, microscale, which is probably where life science is also involved. And so why do we want to model all this? So why computations? And here you see on the top left, you see a molecule, a DNA basis. On the bottom, this is one of these frameworks, one of these sponges with which we work. And the idea is that when people perform experiments, of course, they get part of the picture, but with the simulation, one can really complement the experiment. One can fill information gaps, offer interpretations, suggest new targets before their synthesis. So this is really our goal, to not just understand, but also be predictive. And so what also, so for example, predict fingerprints, spectroscopic predictions. So to do all this, what physics do we want to include? So of course, if we look really at molecules, materials, so something at the molecular level, the interactions are governed by electron distribution. And so we need quantum mechanics. If we look at more statistical behaviors, classical mechanics is also important. But so you can think about computational chemistry as the field that uses computer simulations to study chemical phenomena of various types. And this is a field which is very hard computational, in the sense that we need a lot of computational resources, because we have to perform a lot of calculations, especially when the systems are complex. And also the methods, the more accurate they are, the more computational power they require. Think, for example, about predicting the structure of a protein. So now here, I want to show you in these computational methods, the physical time scale and the length time scale. And so, as I told you, if we look at molecules, we are really in this very small dimension. Classical physics doesn't work. We need to use quantum mechanics, the Schrödinger equation. If we are more in this middle size, we use molecular dynamics. These are classical simulations. But in both cases, I mean, the goal is to solve very complicated partial differential equations. And so we need these very high performing computers, either in the form of parallel machines or, for example, graphical processing units. And again, if we can, with one of these simulations, for example, predict the structure of a protein and explain through that why a patient has a certain genetic disorder, this is really important, and it can advance the field a lot. So let's now look about the scenario in healthcare and life sciences and the utilization of this high performance computing. And perhaps here I'm repeating things that are obvious, but this is to build the premises to talk about quantum computing. So for healthcare, there is a large use of machine learning algorithms, as we have heard, in image processing, biomarkers, optimization algorithms for radiotherapy planning, clinical trial optimization, or these classical simulations, Monte Carlo simulations that I mentioned before, to understand the mechanism of a disease. In life science, on the other hand, use electronic structures, so these methods that make predictions at the molecular level, but also molecular dynamic simulation for drug discovery, protein structure prediction, and machine learning for omics, therapeutics, as we have heard also in previous talks. So what about artificial intelligence? This is the conference in artificial intelligence. And probably you all know about it, but this is a picture that shows the annual global private investment in artificial intelligence by focus area. It's a couple of years old, but basically you see how much is invested in medical and health care. And certainly artificial intelligence is an incredible tool for this field of research. However, we can also look at this picture, which shows this is about the accuracy of artificial intelligence, so the percent error, as a function of the number of the floating point operations, so the cost of the calculation. And if one extrapolates this trend, basically we see that by 2025, the error level in the best deep learning system designed for recognizing objects should be reduced to like 5%. So this is great, but at the same time, we have to worry about the fact that the computing resources and the energy that are required to train such a future system is enormous. Probably it is comparable to the emission in terms, for example, of emission of CO2, the emission of CO2 that the city of New York City generates in 1 month. So using high performance computing in health care and life sciences is exciting. It offers many opportunities of development, but it will also pose some challenges. And so here is where we are starting to talk about quantum computing versus classical computing. And I will say very, very basic things about this type of architecture. I hope I don't insult anybody because you already know too much, but I didn't know about the level of knowledge in this field of this audience. But let's say that if on a classical computing, the unit of information is the bit, which can have 2 states, 0 and 1. In quantum computing, the basic unit of information is the qubit, which collapses to 0 or 1 when it's measured, but a qubit can also exist as a superposition of both 0 and 1 while in use. And so why is this important? Because the amount of information that one can represent with qubits grows exponentially with the number of qubits. And so here in this table, you see, for example, if we have 1 bit or 1 qubit, we'll have 1 bit of representation in a classical environment, while we'll have 2 qubit representations in a quantum environment. And here you can see this linear combination of the 2 states. Now, if we have 2 qubits, we'll have 2 bit of representations in a classical environment, but we'll have 2 to the power of 2, so 4 qubit representations that are there. And if you have 3, we'll have 3 to the, 2 to the 3, which is 8, 2 to the 50 with 50 qubits, and so on. So really the number in which you can represent a situation grows exponentially with the number of qubits. And so this is what can bring the so-called quantum advantage compared to a classical computer. And especially since this is a conference about AI, machine learning, being able to use quantum machine learning is really appealing, because one can use these quantum algorithms to analyze large data sets in a much more efficient way than with classical computer. And this, has an impact in many fields. We'll talk a little bit about it, but for example, also cryptography, which uses quantum communication to really secure communication is very important. So how do quantum computers work? Again, we have this possibility of having a single qubit in a superposition of 2 states, 0 and 1. And so if we have, for example, n qubits, we'll have 2 to the power of n combinations. So the superposition is very important, but also what is very important is this concept of entanglement, which means that you can have entangled qubits that describe a certain state, and this state cannot be described by the 2 qubits being independently one from the other. And again, the developments in quantum computing hardware have seen progress across a variety of platforms and technology. So what about the types of quantum computers that are available nowadays? We are looking at their function, their number of physical qubits, and eventually the companies that produce them. So if we start from the left in this side, we have the so-called quantum emulators, which is basically a classical computer that performs simulations of what a quantum computer should do. And so it's no faster than existing classical computers, and it has no physical qubits. Then there is this so-called quantum annealers, which are are still focusing on optimization problems. They can either have 0 qubits, so be completely classical, or some qubits, but they don't have logical gates among the qubits. And it is not clear whether such devices will have a speed up over conventional computers using classical algorithms. And then there are noisy intermediate scale quantum, so also called near device terms, that use qubits, but they are noisy. There is this problem of the noise of the qubits, and they don't have a mechanism to really deal with this fault tolerance. But they can demonstrate useful application with the aid of classical computers. And you can think that here you have between 1,000 to 5,000 qubits. And then finally, this universal fault-tolerant quantum computers, that this is the ultimate goal. And the idea is that they achieve this, once they are available, they achieve these exponential speed-ups that can be demonstrated over classical computers. However, one has to, I mean, if you really want to if we want to perform this error correction, this will require a lot of qubits, possibly millions of qubits needed. How about now, when we talk about quantum computers, how can we judge their performance, if they are good or bad? Usually, so there are various criteria. So the scale is an important one, which basically tells us how many qubits do we have. But this is not the only criterion. We also want to know about the quality of the qubits. And this depends on a metric that is called quantum volume, which indicates the ability of the chips to execute circuits. And finally, there is this other criterion, so this circuit layer operations per second, CLOPs, which evaluates the speed of the device or how many circuits we can run in a given time. And so these are all directions which are pushed by various companies. We had the pleasure to collaborate with IBM. They're really trying to make progress, not just in the scale, but also in the quality and the speed. Now, of course, we have this hardware. What we want to do is also to develop some software, so quantum computing software, which is a critical component of this emerging field. And it's essential to be able to develop software for these computers because it allows researchers to develop, to design algorithms and test them. And so here you see an example of this software, which is called a software platform, which is called Qiskit. It's an open source software development kit, SDK, and it's designed to work on IBM computers. And so it allows basically researchers to design and test different circuits, execute quantum programs. And there are other types of software, but this is really something that everybody can use and play with. What about the quantum algorithms? So here, important. So here you see, for example, of course, you need the proper algorithm. Here you see an example of what is called the Shor algorithm. This is one of the most famous one. It was developed mainly to really be able to factor large exponential numbers, and this is important, for example, as I told you, in cryptography. But there are other algorithms that are used in different areas. And the development of quantum algorithm is also an active area of research because different algorithms can take advantages of the capabilities of different hardwares. So with this brief introduction, I want to go back to chemistry and then healthcare and life sciences. So what about in chemistry? And this is maybe where my research fits. What can we do nowadays with quantum computing? So here, if we look at the bottom left of this picture where we have the quantum chemistry, so studying objects with the quantum mechanics at the molecular level, we can say that quantum computing seems to have a great potential for this area because we really, in this domain, we have to solve problems that scale exponentially with the size of the system. And so they seem perfect for a quantum computer. but it's possible nowadays to perform quantum mechanics calculations using these first principle methods on quantum simulator and or quantum devices. I would say that nowadays we can only study small molecules, more sort of toy systems, but one can also utilize error mitigation when performing these calculations. And there is a lot of research in this field to reduce the number of qubits required for large molecules. On the other hand, if you are more in this domain here, classical simulation, molecular dynamics simulation, there is also research going on there, but it's not immediately clear whether there will be or not a quantum advantage here. So what about quantum computing and industry impact? And here you see different possible applications of quantum computing in chemicals and petroleum industry, distribution and logistics, financial services, of course, healthcare, life sciences, and manufacturing. So these are all areas where there could be an advantage utilizing this architecture. So what about healthcare? Why quantum computing is important for healthcare? And here we can see some of the advantages. So there is a power efficiency. So compared to modern classical computing, through the use of a concept called quantum tunneling, the processing is quite powerful, so they can be efficient in solving highly complicated problems compared to what can be done in a classical computer. So they can speed up learning process of AI, reducing thousands of years of learning to seconds. They can efficiently solve multivariable equations that usually one has to do in lengthy simulation. And there is this concept of compute supremacy. I'm not sure, supremacy for sure in the US is a non-politically correct word anymore. Let's talk about compute advantage, but they can surpass the limit of the traditional computing. Now, what about, so this is the why is important. And now let's look at some use cases and quantum computing techniques for healthcare and life sciences. So here you can see some applications. So for example, in image processing, one can utilize this quantum topological data analysis algorithm. It's one of these algorithms. In biomarkers, quantum machine learning, radiotherapy, there are these quantum approximate optimization algorithms, and the same also in clinical trial optimization. And now in life science, we are interested, as I told you, in drug discovery. And so we want to optimize, minimize the energy of molecules and complexes. And so we try to perform a structure simulation on the quantum computer using this variational quantum algorithm solver algorithm. And also, I mean, there is potential for protein structure prediction, omics, and cell-centric therapeutics. So here I want to show you also this the quantum computing has the potential to accelerate the transition from what is called umbrella diagnosis and treatment to some precision health status and intervention. So this framework would allow organizations, for example, to optimize and personalize their services through continuum care. And of course, if there is a patient engagement and adherence, these are key components to be considered when one wants to make a decision about the next best medical action. So these are certainly potential areas where quantum computing will make a difference. So I hope I've given you a super short, super quick, very basic introduction. So where are we now and where would we like to go? So we see that there is a potential for quantum computing to revolutionize healthcare, but of course it depends also on the availability of health relevant data. But health data sets are growing. And so what is important is to grow the number of people who are being instrumented and the data types that are collected. And so having this data available is certainly essential for the advancement of quantum computing in healthcare. So if we can say now or within 5 years, we can achieve a claim, we can address claims, customer relationship management, imaging, lab values. Maybe in 10 years, we can use quantum computing for omics, Internet of Medical Things, social determinants, wearables, and perhaps in 10 plus years, clinical research. So with that, I like to conclude. So I like to thank, first of all, as I said, I work on this topic with the great collaborators at IBM, especially Gavin Jones, IBM Quantum. He has helped me also with the slides. Also other collaborators at Argonne National Lab and HRL. And this is my group at the University of Chicago, a group of talented students and postdocs, and they do research in this field. With that, I'd like to thank you all for your attention. And again, I'm sorry that I'm not there with you, but if you have questions, I'm happy to take them.
Thank you, Dr. Gagliardi, for your interesting overview on these future perspectives. We are 15 minutes late, so we have only the time for 1 or 2 questions. We have one question from the audience.
Hi, this is a question for Dr. Gagliardi, sorry. I'll be quick because of time. So I saw QSkit, I don't know if I'm pronouncing that right, looks amazing. So understanding the limitations with quantum computers now, with the limited number of qubits that we can simulate, I understand that it's probably not practical to simulate neural networks, which can be millions or billions of parameters. But do you know if any of the open source packages for neural networks like PyTorch, TensorFlow, et cetera, are working towards supporting quantum computers for when the computers are available, we'll be ready to actually deploy them, or are we still pretty far away from that?
No, I think, I think at the moment our limitation is the hardware, not just in terms of the number of qubits, but also you have to build these gates among qubits and deal with the error that is associated with that. So I think that all packages for artificial intelligence, machine learning are really looking in this direction and trying to be quantum ready. So I think there is a great potential there. We are not there yet. And so sometimes what I don't like also in chemistry papers, they always open saying, oh, we are going to solve the next protein structure. We are going to solve the next climate change issue with quantum computing. No, we are not now, okay? Now we are really working a lot with toy problems. But, you know, in the 60s, when computers started appearing, nobody knew what we could have done 50 years later. So I think it's fine that we really try to be ready with the software and the theories, the algorithms, because the computers will be there. That's at least my view.
Thank you. I got one question for Marina Garassino. Can you read us? We cannot hear you. Okay.
Can you hear me?
Oh, yes, yes, thank you. So we heard about AI-assisted trials, AI-assisted protocols, and I can easily see the point of artificial intelligence helping us designing clinical trials. But I got one question for you with regards to modelization and to simulations, with specific regards to the regulatory agencies. So you got a great experience because you know EMA and you know FDA, so probably you're the most expert here for both agencies. But what's your opinion about how these agencies should or will maybe behave regarding drug registration after this kind of AI-assisted trials?
So thank you for the question. I think that this is a crucial part. I think that we are very far from the acceptance from the regulatory agencies of this kind of trials. And as you saw in my slides, the majority of the trials that are now ongoing are mainly observational trials. So I think that this is the future. And if I have to predict the future, I think that in 10 years from now we are just creating the trials for all-comer patients without any selection. And it is possible that in the future we will have all the characteristics of a patient from the beginning, and maybe we will be able to shape the treatment according to the characteristics. So I think that in particular in FDA, there is an opening to start to work on the artificial intelligence. I don't know if EMA, how much is far from the concept that we will work with very ultra rare populations for which we will have to develop new drugs. I think that altogether we should shape a new era. I think that we are going very far from the clinical trials in all comers, but we have clearly to start to do some research in that field.
Thank you so much. Unfortunately, we don't have enough time for additional questions right now, so we're leaving in order to give place to the next session. So we're calling Alessandro De Toma and Diego Signorelli for the last session for the roundtable. Thank you. Thank you so much.
Thank you, Marina and Laura, for being here. Bye. Thank you.
Good afternoon, everybody. Still afternoon, no? Not evening, I guess. I'm Diego Signorelli. I'm a medical oncologist at Niguarda Cancer Center in Milan. And first of all, I would like to thank Arsi for the kind invitation, for giving me the opportunity to be here at this very important Congress. So last but not least, let's start with the roundtable session. How to exploit big data and AI innovation in oncology, finding common ground for academic, policy makers, and industry stakeholders. We will discuss this topic with 3 speakers that I invite here, please. I would like that this room is a unique, big roundtable, so please feel free to ask questions, to make comments from both the room and virtually. And I'm very pleased to be co-chair of this session with my colleague and friend, Alessandro De Toma.
Hello, I'm Alessandro De Toma from Varese, and I'm very glad to introduce Luis Castelo Branco. He's a medical oncology. He also has a degree in pharmaceutics and a PhD in public health. And I think it's the perfect person to talk us about how we can find a common background in Europe and worldwide between academy, policy, and industry. So, Luis, please.
Thank you so much for the introduction and for inviting me here. First, I would like to congratulate for this outstanding event and for all the teamwork that you built. And I'm sure this will be the first of a few that will be organized over time. A special word, keeping with the title of and the topics here, a special word for a very intelligent and machine woman, Arcela, for your outstanding work and you bringing all these people together and all the team that you working with you to make this possible. So it's a great step having this event, and I'm learning so much from all of you today. Please let me share that I'm working for ESMO, but I'm sharing here is just my personal views and my individual perspectives, okay? It's a very, very interesting and very important question. So let me try to talk about artificial intelligence without talking about artificial intelligence. The first thing I would say is that let's look back to the classic research framework where you have industry, having new drugs going to centers, research teams, clinical trials development, data generated, publications, then that publication bring to the regulatory agencies for approval. This is our classic framework from research, but things change a lot over the last years in several dimensions. And so let's say that we may be talking a totally different ecosystem specifically for oncology, in how we are doing research, collecting data, and processing data, sharing, and our correlation with regulatory agencies and policymakers. And this is also another important thing, if I may, distinguishing regulatory agencies from policymakers by a few reasons, which I will explain soon. So the first thing is like looking for the modern oncology ecosystem. Yes, we have academics, as you mentioned, the industry, but there's many other stakeholders that we need to take into consideration for this discussion, not only for research, but also for clinical practice, obviously. I mean, we can start by different types of clinicians, and I mentioned it on purpose because we're oncologists. Things change a lot also in our field, and we need to interact more with other groups of colleagues that we were not classically working on. For instance, immunology, we change a lot our practice in immunology. We're still learning how to interact and to cooperate with our colleagues, other health professionals. Here, specifically on this session, I mean, engineers, data experts, of course, pharmacoeconomics, public health experts. So, and I mentioned this one by one because it's not only that we acknowledge that we need to interact with them, but it's also the fact that we need to find new ways to bridge and to integrate these different backgrounds into a common framework where we optimize how we cooperate. I can bring if I may, my small experience in public health and oncology. I mean, if you talk just with a group of public health experts about oncology, there's a lot of things they may not understand. If you are just oncologists trying to bring some evidence for public health experts, we may fail in the way we communicate and you bring evidence for them. So we need to find better ways to cooperate and to optimize how we do our collaborations. And this is somehow two medical fields, somehow closer. Let's talk about engineers and medical doctors. We come from totally different backgrounds. We think differently. We face some obstacles sometimes, even in the communication process. So we need to optimize many steps. That we start first to acknowledging that we are having an obstacle, and how we cooperate, and how we share knowledge, and how we use that knowledge for a common ground, hopefully to optimize and be more efficient. And how you conduct our clinical research, aiming for the benefit of, obviously, of our patients on the future, and also acknowledging that there are different agendas here. I mean, it's industry may have different agendas from several research and academic institutions. So we need to acknowledge all this and try to identify the challenges ahead. Another thing about what all these amazing sessions that we are having here. I mean, there's no doubt AI will play an important role in research and clinical practice, but are we already integrating it in our training for the future doctors, not only postgraduate, but also in medical schools? How much are we considering this nowadays? So these are just one example from here, that other things that we need to look at all our, if I may call it, the oncology ecosystem, and now you can start optimizing this process, identifying the different stakeholders, identifying the best ways to optimize this communication, and that we all will cooperate better. I mentioned the difference between regulatory agencies and policymakers, because this is also another, especially in European context, this can be a very important process. I mean, let's use the example of reimbursement of drugs. I mean, for oncology, you have EMA approval, straightforward, and then in theory, it should be used across countries, right? But then all the blockage that each country can use by their policymakers. I mean, it's not only about local HTAs, but also the government decisions. They can use different mechanisms to postpone the process or to delay the process of accessibility. So it's important to acknowledge that it does not stop in regulatory agencies, and there's different mechanisms that the policymakers can use to interfere or to decide, because ultimately it's a decision from their side on how we may or not have access to innovation in different dimensions, and including this new generation of AI-driven technologies. So the core message from my first intervention is we need to better identify the different stakeholders and to optimize collaboration, and there's a huge work ahead on this regard. I mean, all of us probably already experienced this in several dimensions, and I think this is one of the things we can improve. And finally, we're talking a lot today about data and data quality and big data. I will try to simplify in one word. I think it's the quality of data that we need to be, and it's a lot of work ahead in terms of how we optimized all the process to guarantee that the starting point, the quality of data you're using, is really good. We mentioned rubbish in, rubbish out often here, which is a classic framework for years, but I will not stop there, if I may. Rubbish in, rubbish out, but then you publish it, you use it to discuss with agencies or regulators. They might consider it, they might take decisions based on it, and the policymakers may take decisions based on it. Then you realize there's a problem, and then you step back and you lost trustability here in the process. One good example, learning from recent experience, was with COVID, right? There was a lot of decisions taken based on low evidence, that then there was some step backs, and people say, well, that was the best evidence we have at that moment, and we prove over time when you change. But looking back, maybe that evidence was, if you look a bit better, that evidence was not that good, and we can optimize the way we can generate, assess, and improve the quality of that. And I think this is a core element, improving the data that we are using in the quality and from the different sources that we are using for our research and clinical decisions.
Thank you very much, Luis.
Thank you, Luis. You have just talked about this topic, but from a practical point of view, your opinion, do you think that in the next future will be feasible in short term for European Union authorities such as the EMA to have a framework for AI tested and approved drugs?
Yeah, that's another very interesting and important question. Of course, I mean, it is needed. The thing is which steps we should take on that directions. May I divide it in at least 4 dimensions? One is preclinical. The one will be phase 1 to phase 3 clinical trials, or seamless clinical trials if you want, real world evidence, and eventually we may consider also guidelines or how we use all that evidence processed for our clinical decisions. So the first one, preclinical, I think is somehow straightforward. It's outstanding what many groups are doing already for drug development, drug discoveries, better finding bindings between using AI tools to optimize the binding between new drugs, for instance, ADCs now, and with the target agency, and optimize the chemo component that you use for things like this. I mean, that's outstanding research going on. It's preclinical, so it's more easy because obviously the ethical components are less relevant. But when you move forward the clinical trials, it's also moving so much because it's a challenge. Again, when you look for the ecosystem, it's a challenge in all dimensions. If you are moving a lot and improving the quality of the tools you're using in AI, then regulators need to adjust rapidly as well, because the regulations of today might be outdated tomorrow. And the process, the way we look at it, So we might also be outdated. So we need to all together find ways that regulation will be good enough for the type of tools you're using. The tools are providing reliable and value on the research side, so that we try to optimize all this process. We have already some good tools, for instance, to report on reporting side of clinical trials. Spirit AI, it's a nice one, very well used, and help us, the community, to, when reporting trials using AI, it is a good tool. It's already useful. You need to improve, if I may say something about that, how we standardize and optimize the different dimensions of AI applied to integrated in clinical trials. When you look for observational studies or real-world evidence, the same, because we'll have more and more, and it was mentioned previously, one very important point, that we are moving to more molecular-based and submolecular groups of tumors, so it's somehow more rare-like tumors, so we're having more the need to eventually have more smaller cohorts on research, or eventually having complementary good quality, and I insist on this point, good quality real-world evidence to help for the decision making, and there obviously having better AI tools and better AI quality assessment will be important for not only for the research side, but obviously to increase the quality from the different stakeholders when we look at what the data that's been generated for decisions. And I think one very, very, very important dimension is the last one I was talking regarding guidelines. I mean, we have nowadays a proliferation of data that, when widely processed and with valid tools from AI, it will be tremendous for our clinical practice and help us on clinical decisions. So we are not yet there. I'm convinced that we are going through that direction over the next years, and for the whole community that will be tremendous. That will be may help us a lot to be more updated for the clinical decisions when we are seeing our patients. I don't know if I was addressing your point, or if I missed something, please let me know.
Thank you, Luis. And now we move to patient perspectives, and I introduce with great pleasure Pietro Auletta, that 1 year ago get a role in the executive committee of IPOP. This is our association of patients with lung cancer. So, Pietro, which are the main worries and concerns related to AI in patients' opinion?
Well, thanks first of all for inviting me to represent IPOP here today. Very interesting conference. I would say that people with cancer today have basically the same level of appreciation about artificial intelligence as people without cancer, and that is still quite low. So there is not so much awareness, but that I think it's going to change fast, because artificial intelligence is going one way or another to get into our daily life. So people will start to understand more about it. When attending research projects such as Apollo 11, for example, and required to provide their data and their information to the project, these people will expect data privacy and proper consideration of data protection. This is quite normal. Every one of us has the same approach. They will also expect, more so as time goes by, human supervision of artificial intelligence analysis and tools. The more people will understand about artificial intelligence, the more they will start wondering who is taking the decisions. The system, the tool has to provide, has to become an enabler to provide different point of views, better analysis capabilities, but not take decisions. Nobody wants artificial intelligence to fall in love with him. They want artificial intelligence to support the people who take the decision. But I would say that these are not the main problems. The main problem for people is not the risk perspective or the challenges or artificial intelligence, what they will see are the opportunities. The opportunity to have more quality of life and more life thanks to artificial intelligence and all the use we can have from artificial intelligence, which we have seen today at length. So better targeting of the illness, better understanding of resistance, avoiding cures which are not fine-tuned to the specific of a certain cancer type. All these people can understand, will easily understand. And this is the reason why today they are volunteering to provide their data. And they are more worried about the speed with which this development will take place than with the privacy, which is important, but in the end can be managed. So I think that patients have a lot of expectation from artificial intelligence. Maybe they are even overestimating the speed with which this tool can provide support. They are more than willing to contribute, but they expect very, very practical results. So they want the end delivery of a better cure, more targeted cure, so that cancer can become a condition of life and not a condition for the termination of life.
Thank you, Pietro. And I am very honored to introduce Dario Monzani. Dario is an assistant professor in general psychology at the Department of Psychology, Educational Science and Human Movement of the University of Palermo. His main research interests are in the area of cognitive processes, decision-making, communication, with a specific focus on the medical decision-making, doctor, patient communication, and the use of digital tools to promote health and well-being. So Dario, we are starting now to work with AI and begin to understand and trust it. But in your opinion, how do we get patients and artificial intelligence being involved in the decision of their therapy?
Yeah, thank you, Diego. Thank you for the introduction, and also thank you, Arsela, for putting these things together. It's an awesome event. It's a good question. It's also a great challenge to try to, promote patient trust in the AI. So if you can promote trust, then you can also influence the patient adoption, the patient acceptability, but also the actual use of, AI-based predictive model and also clinical decision support system in the clinical practice. I will say anything new because former speakers have already outlined some aspect that can, for example, promote patient and user trust. So, for example, Alessandra Pedrocchi deal with the concept of the explainable artificial intelligence. So, by promoting, by developing transparent and also interpretable models, then you can promote user and patient trust. But also, for example, Emilia underlined how by following the roadmap to the reliable machine learning models, you can also promote trust. But also, Elisabetta showed that if you can consider possible arising ethical issue, you can also, for example, counteract possible decrease in patient trust in the AI. But also Pietro, now in this speech, suggests some, meaningful aspect that should be considered when trying to promote patient and user trust in the AI. From my point of view, we can, promote the trust by working at different levels. So first of all, we need to consider that the inclusion of the AI in the medical decision process can also lead to a dramatic change in the relationship between patients and doctors. So we, first of all, probably we need to develop good practice guidelines to include AI in the medical decision making. Another level of another important level can be the model itself. So as also Alessandra Pedrocchi suggests, we can take into consideration the insight coming from the explainable artificial intelligence approach. But then also we need to consider the patient themselves. So we should empower the patient. We should support them in trying to understand better the information that can come from the artificial intelligence-based predictive model. We should support them in having a shared decision-making, because first of all, we need to involve them in the medical decision-making process, while also protecting and respecting their, their preferences, their autonomy, but also, as suggested by Professor Pedrocchi, we need to protect also their human agency. First, we need to consider the possible change in the relationship between doctor and patients. So in last decades, we assist to a paradigm shift in this kind of relationships. So we move from a more paternalistic approach in which physicians were used to decide for patients, to shared decision-making processes in which doctor and patient discuss opinion, discuss information, but also share knowledge regarding, for example, treatments, benefit and risk, to make a decision together regarding their treatments. And then, the inclusion of the AI in this relationship can lead to a paradigm shift. So in this case, we are moving from a dyadic relationship to a triad. So we will have the AI, the doctor, and the patients. And then from my point of view, we should develop some good practice, some guidelines to try to understand how to efficiently introduce this kind of model, this kind of support when making decision about treatment. Okay, and then moving to the, I will say, to the AI side, we can take into consideration the insight coming from the explainable artificial intelligence approach. So for example, I'm also referring to the seminal paper by Tim Miller. So from my point of view, in this paper, we can find some meaningful insight regarding how to promote patient trust in AI to make better decisions regarding treatment. So from my point of view, explainable artificial intelligence is not only I will say, a technological IT topic. It's also a hot topic in psychology. Also, as clearly suggested by Miller in this paper, explainable artificial intelligence lay at the intersection of artificial intelligence, but also human-computer interaction and also social sciences. So explainable artificial intelligence is also a psychological topic. So from my point of view, we should try to develop transparent and also interpretable models. When not feasible, when you have to deal with also black boxes, you should consider giving post-hoc explainability. So as also shown by Professor Pedrocchi, but also by Arsela, in the I3 Lung project, we are dealing with this kind of model. And then at the end of the project, we will also deliver post-hoc explainability. So we will try to, explain to both patients, but also to clinicians, how actually the model works, what the model can do and cannot do, and so on. And also in the I3 Lung project, we also trying to go beyond giving post-hoc explanation, and we'll also try to identify the best possible post-hoc explanation for specific type of patient or specific types of clinician. So we will try also to deliver tailored post-hoc explanation to patient first, but also to physician. And then finally, last but not least, yeah, sure, we should empower patient. So for example, including AI in making decision about treatment can be, can have beneficial effect for everyone. But then some research, for example, one recent research from people at the New York University suggests that some patients can be skeptical in including AI when making prediction and decision regarding their health. So for example, this kind of the results suggest that some patients generally prefer having information from a human healthcare provider rather than an algorithm or the AI. And also, these results also suggest they generally prefer to receive information from an healthcare providers, even at the cost of receiving, also at the risk of receiving less accurate information from a human being. So there is a sort of, for some patients, not all, there is a sort of, I will say, algorithm aversion. And then some qualitative study, some, I will say, dealing with focus group and interview with patients, suggest that probably this reluctancy in considering the information coming from the AI can be a result of their beliefs that AI can work very well with the average patients, but then since the AI cannot do something valuable for them because they are unique. Okay, so in this case, also to try to promote trust of patients, for example, we can give some core messages. So, for example, we can develop interpretable and explainable models, but also we should involve them in the decision-making process, and then we should also underline the benefit of having the AI to make decision. And then this is also one thing that we are trying to do in the I3Lang project. So, for example, let me conclude. We are aiming at developing a patient decision aid. In this case, the patient decision aid will be a support for patient to be more informed regarding the available treatment, receiving personalized prediction regarding risk and benefit of available treatment, compare treatment, but also we are aiming at going beyond traditional patient decision aid. And then since in the I3Lang project, we will develop AI-based predictive model, we will also give information regarding how AI works, what AI can do, what AI cannot do. So in conclusion, we can have this kind of core messages. To promote trust, patient trust, we should act at different level. So we should develop good practice and guidelines for including AI in making decision about treatment. And then we must empower patients. We must support them in understanding information also coming from the AI, and then we must include them in the decision.
I totally agree. Thank you, Dario.
So unfortunately, time flies and it's time to close. I think everybody is quite suffering. I'm extremely glad to introduce my close friend again, Arcela, for the take-home message. Please, everybody, claps your hands for her and for his extraordinary job.
So thank you. I'm not going absolutely to give long take-home messages. I just am imagining these, just some key words, and imagine this take-home message as a good pizza that is made here in Italy. So the very good pizza that we ate yesterday, for example, was not in the evening, but in lunch with Alex, was an apple pizza, very good pizza. So to have that, we really need good ingredients. So for sure, Matteo, you feel sick not for that pizza. So because that ingredients were very good, and that ingredients are our data. So the message is our data needs to be good. Our data needs to be also gourmet. We called in also in Milan with gourmet pizza. So quality, high quality. But at the same time, so as we said, we need to absolutely put all these things together, but also these data have to have a common language. So Robert says today that it's important to have, not every time in every case, but it's very important to bring in practice some changes. We need that these data have the same and are encoded in the same way. Otherwise, sometimes not the same data that are reported are the original one. And after good ingredients, we have to have very good cookers. So it means that, yes, we have Naples pizzaioli, which are very good and are the technical engineers, I imagine, or data scientists, etc. But also, I mean, in Rome, I used to live 10 years, and it's a very good pizza. It's another type of pizza, and also here in Milan. And so there are medical oncology, so a lot of interaction between us to build models, because I think that the model builders and model explanators are both these figures, and more next generation bioengineers, data science and technologists, or hybrid. We need to be hybrid. And finally, as other two main topics, we really hope that we are going to accelerate a bit more all the bureaucratic frameworks as we discussed, and also with the help of passion scientists. So I called passion scientists because, for example, EPOP was a very good example within Apollo 11. They build it together with us at the protocol. They write the protocol with us. They write the informed consent and as a scientist. So thank you again. These are some nice pictures that we take from yesterday just to bring you, because I know that you are very tired and we are delayed in 25 minutes, but just to say to you, have a nice trip and be back at home. Hopefully you will enjoy this weekend here in Milan. Otherwise, I really hope to see next year again here to you, all of you. So thank you again for resisting until the end. Okay, bye.